Worthiness creates wealth and enrichment. Enrichment leads to the right conduct, and right conduct brings contentment. Good morning, everyone present in person and virtually. I, Ananya, and team, on behalf of the entire organizing committee, wholeheartedly welcome you to the International Conference on Biotechnology Trends on the Future Prospects to be held from September 13 to 15. 25 years ago, the Department of Plant Biotechnology was established in the campus of University of Agricultural Sciences, Bangalore. This department is popularly known as Advanced Center of Plant Biotechnology, and since then, all of us present here have contributed a drop in the ocean. Backed by the Almighty's grace, majorly, this department has clustered many intellectuals together, forming a globule of knowledge and technology, and has always been working together for the reinforcement of it to benefit the nation. I take the pride to announce and acknowledge the great contributions done by the former leaders of this department in the form of both resources and knowledge. Being backed by the great personalities and perpetual cooperation of the present leaders, we have been able to organize this international conference on the Silver Jubilee of the department to take some time out and channelize our knowledge into substring. In fact, King James once said, "Were I not a king, I would be a university man." With this, I would like to thank the gathering for making it to the conference, both virtually and in person, and wholeheartedly welcome you to the inaugural function of the conference. I invite Dr. Shamla Amma, S. Professor and Head, Department of Plant Biotechnology, and the organizing secretary of this conference on the stage to welcome the gathering.
Good morning and warm welcome to all of you. So before we start welcome address, request our dear students to render invocation.
गणपतिं मनसा स्मरामि महागणपतिं मनसा स्मरामि महागणपतिं मनसा स्मरामि महागणपतिं मनसा स्मरामि वसिष्ठवामदेवादिवन्दितं महागणपतिं मनसा स्मरामि वसिष्ठवामदेवादिवन्दितं महागणपतिम् महादेवसुतं महादेवसुतं गुरुगुहनुतं महादेवसुतं गुरुगुहनुतं मारकोटि प्रकाशं शान्तं मारकोटि प्रकाशं शान्तं महाकाव्यनाटकादिप्रियम् महाकाव्यनाटकादिप्रियं मूषिकवाहनमोदकप्रियं महाकाव्यनाटकादिप्रियं
Thank you, Chaitashri and Grieg, for seeking the grace of indeed. Now, ma'am, Shama.
Good morning to all. Warm welcome to the International Conference on Plant Biotechnology Trends and Future Prospects. I'm happy to invite our guests. And before that, I would like to express my thanks, gratitude to our gurus. This month being the Teachers' Month. Guru Brahma, Guru Vishnu, Guru Devo, Maheshwaraha, Guru Sakshat, Parabrahma, Tasmai Shri, Guruve Namaha. So with the blessings of all our gurus, we are here and we are blessed to organize so many functions after COVID. And out of that, this is one conference to organize in a befitting manner. And I'm happy to invite our Honorable Vice Chancellor, Dr. Rajendra Prasad sir, for this program. And whenever I met him for various things, he has told, ಮಾಡಿ ಅಮ್ಮ ಎಲ್ಲ ಚೆನ್ನಾಗಾಗುತ್ತೆ ತುಂಬಾ ಚೆನ್ನಾಗಾಗುತ್ತೆ ಮಾಡಿ ಅಂತ. So this encouraging words has given us lot of strength, sir, and we thank you very much for your constant support and guidance. And I request our another guest, Dr. Vibha Ahuja, CGM, BCIL, New Delhi. And I met madam in another function in the same venue just 2.5 months back. And that time this conference was just taking a shape and we asked them to support this program through DBT. And she immediately told that, yeah, there is one program, you just apply for that online. And we submitted the application and we got the funds. Thank you very much, ma'am. I welcome you for this program and we are happy to have you in this program as a lead speaker also. And Ramesh, our invitation to be the guest of this function, and also NABARD has supported this conference and we acknowledge sir NABARD support and we thank you very much for gracing this occasion. And we have another our Silvantar sir, and we remember him for so many things which happened on the campus. Out of that, most important one is the wall around the campus, this beautiful campus, and he has helped us protect this campus. Apart from that, so many achievements, and sir will tell that later on. I welcome you, sir, for this program. And also I welcome our former professor and head and dean, former dean PGS, Dr. TKS Gowda, and who was instrumental in plant biotechnology in the US, Bangalore, and also he has guided us in various ways in organizing this conference also. We welcome you, sir. And I'm happy to welcome our another professor and head and present member, Board of Management, Dr. P.H. Ramanjini Gowda. And sir used to inquire about the conference preparations every week, actually. So we were so blessed to have his advice and guidance in each and every step. We welcome you, sir. And also I'm happy to welcome our another member, Board of Management, Dr. O.S. Dayanand, sir. Thank you, sir. And also I welcome our another member, Board of Management, Sri Srirama, sir, for this beautiful conference inaugural program. And I invite our program. And apart from the guests, and also having several teachers and key officers in the row. In that, I welcome our Dean from College of Agriculture, Hassan, Dr. Vasudevan sir. And also I welcome our PGS, Dr. H.C. and Dr. Palani Muthu sir, Special Officer, College of Agriculture Engineering, US Bangalore. And all the invited lead speakers, Dr. Saudamini, Dr. Matthew sir, and Shiv Prasad and all others. And also I welcome University Head and Administrative Officer, Dr. K. Kumar sir. Sir? Director of Extension, Dr. K. Narayan sir, for this conference inaugural program. And I welcome all the delegates who are registered for this conference and all the faculty from different disciplines of the university, all HODs and university heads, and teaching staff, non-teaching staff, and all the students of this university, and also the print and media, electronic media persons, and all the people directly or indirectly to organize this conference and to attain this moment of inaugural program. Thank you, one and all.
Thank you, ma'am, for welcoming the guest and gathering, and we wholeheartedly welcome you.
ಹೇಗೆ ಬೆಳಕು ಕತ್ತಲನ್ನು ಸರಿಸುತ್ತದೆಯೋ ಹಾಗೆ ಜ್ಞಾನದ ಜ್ಯೋತಿ ಅಜ್ಞಾನವೆಂಬ ಅಂಧಕಾರವನ್ನು ಕಳೆಯುತ್ತದೆ ಎಂಬ ನುಡಿಯನ್ನು ನೆನೆಯುತ್ತಾ ಜ್ಞಾನದ ಸರಸ್ವತಿಯನ್ನು ಸ್ಮರಿಸುತ್ತಾ ವಿಜ್ಞಾನದ ಪ್ರಸರಣಕ್ಕೆ ಮತ್ತು ಚರ್ಚೆಗೆ ವೇದಿಕೆಯನ್ನು ಕಲ್ಪಿಸುತ್ತಿರುವ ಜೈವಿಕ ತಂತ್ರಜ್ಞಾನದ ಪ್ರಸ್ತುತ ಪ್ರವೃತ್ತಿಗಳು ಮತ್ತು ಭವಿಷ್ಯದ ನಿರೀಕ್ಷೆಗಳು 2022 ಈ ಅಂತಾರಾಷ್ಟ್ರೀಯ ಸಮ್ಮೇಳನವನ್ನು ದೀಪ ಹಚ್ಚುವ ಮೂಲಕ ಉದ್ಘಾಟಿಸಬೇಕೆಂದು ವೇದಿಕೆ ಮೇಲೆ ಹಾಸಿನಿರುವ ಎಲ್ಲ ಕೋರಿಕೊಳ್ಳುತ್ತೇನೆ.
We request Dr. Vibha Ahuja and other guests to light the lamp, and I request the audience to stand for the same.
I thank all the dignitaries for lighting the lamp. Now, a conference is yet another means for sharing knowledge. For this, I request Shri T. Ramesh, CGM NABARD Bangalore, and other guests to release the compendium of abstracts.
Audio, please.
Good morning to everybody. And Dr. Rajendra Prasad, chief guest of this, and board members and officers and friends. Indeed, it is a great opportunity for me to say only a few words, not about the book and other things. Perhaps books will be there to read you everything about the institution and what I could do here. First thing, most important thing is I am a very fortunate or a great humble living of this institution heritage. And maybe you know that this is the first university in Karnataka. So I became vice chancellor for this university is a great thing for me. Not only that one, it has got some good heritage. Heritage means builders. Those who built the institutions, especially K.C. Nayak, the first vice chancellor, brought from the FAO. Dr. Arkeri, perhaps all of you may not know, you should know it also. He is the man who gave map development of agriculture for the whole country. Even till today, he gave the, as a commissioner of that agriculture development, about 11 volumes are there at that time. till today they are applicable. All those things perhaps nobody knows. Students just see the volumes of Dr. Arkeri Commission, even those till today. And most of the recommendations made in that one brought to implementation in all the countries, especially home science, forestry college, and all other home science college. They are all forestry college, they all come from their recommendation. Such were the people, and they were with Prime Minister for planning all these things. I've seen only one white sitting with the Prime Minister, Dr. Arkeri, planning for the whole country. Such is the rich this one. So I feel I am very grateful to the I am very fortunate to become Vice Chancellor of such a great university. That's number one. Number two, especially it is a strange, I became a strange chancellor for this. Strange in the sense, I could not have become Vice Chancellor for this university on the normal course. President rule in the Karnataka, and all the politicians were on holidays. So at that time, perhaps the merit took the upper hand. I did not meet any of the politician or anybody. I did not influence anybody also. When I came to report to the governor's office, they told me, you are the only person who have come without influence. Then I thought that it is a great thing for me to come to this university. See such a good thing. And see, again, I am fortunate because I do not have any commitment for any. I was a free man, and I cannot hear anybody anything. I want to do what. So I started thinking what I can do as a vision, my vision, what I have to do. Every day I used to think what I should do today. I have come by strange, and God gave me such an institution with heritage, then I too should do something. That every day I used to think what to do and what not to do. And another very important thing is, when I from Dharwad, I thought that it may be very difficult. Everyone was thinking like that. He may not be able to survive here, something like that. But it became otherwise. All the staff and all the students, they were so because I had no friends, I had no groups, I have nothing. I was only one. If I have got a friend, I am the only friend. And if you say, all are my friends, all are my colleagues, all my co-workers, like that I did it. Hence, anybody who want to meet me, they used to. I used to do that. One thing I would like to tell to you, it is a very DBT, all the organizations used to give me whatever we give, you used to give to me. In the sense, something like that, whatever I touch, it used to become gold. Like that, I had a problem of paying the salaries in the initial stage. Then it became within 1.5 years, it is an affluent. And we have to think how to spend the money and how to develop, what development we have to make, where we have to go for construction, where library in other areas. We used to think like that only. In the sense, my period was, my Vice Chancellor period was the golden for me in my whole service, because I could do something for that institution where that gave to me. Then another thing, I don't want to waste too much of your time, because I am a strange here for everything. Then I thought of putting all those things what I did as a teacher, or I was controller, I was administrator. Because of all that thing, my administration was very, very simple for me, and there was no any hiccups for anything. And all officers were very, very cooperating with me for anything. Development. In that case, perhaps I have to be grateful to them, especially officers, controllers, everyone. And another very important thing is when I expressed that I had compilation of all my what I did during my period, then I requested mentioned to the Dr. Rajendra Prasad. So I have got a complete compendium of my work. It is there like this. Then he said, so sir, why can't you publish it? In the sense, why I requested him, I don't want not to publish anything or give anything in that book. If at all, if I did something, they are all there in the record. If few of them, if he reads it, at least few coming vice chancellors or coming officers, if they read it, at least 4 or 5 people, if they get inspiration, that publication of the book would be become a for my heart. In that condition, I have published this one. And at the last, they were mentioning teaching. I tell you now, what I am today before you, it is because of my guru. Rajendra Prasad also know that my guru is Dr. S.V. Patil, who was also Vice Chancellor, maybe after Arcari and other. Right from beginning, from the first year to even I become nearing to the Vice Chancellor, he was the role model. He was the role model in such a way that you cannot find such a teacher during this time. He was a very rich man. White slacks, khaki pant. Rarely you see in this attire. No. Rarely, I don't know, very important. And he was a true Gandhian, and he was role model for me. I am telling to you, I must have imbibed about 10% of him, and I could do many things for the both at Dharwad as well as Bangalore. With this, I am grateful to this institution. Thank you very much.
Yes. Moving forward, it is my honor to announce that this year, the Department of Plant Biotechnology, GKVK, US Bangalore, is completing its 25 years of academic excellence. On behalf of this, I would invite Dr. Anita Peter, Professor, Plant Biotechnology Department, to give the briefings on the accomplishments and history of the department. Thank you.
Good morning to one and all, and good morning to all the dignitaries on the dais. And I'm really privileged and honored to present the 25 years of development of the Department of Plant Biotechnology. And I'm honored, and I thank the department for bestowing this honor on me. And yeah, so yeah, so these are a few points about the department. So this department was established in 1996, considering the need for trained human resources in the use of biotechnological tools for improvement of food, feed, fodder, bioenergy, and crops. So in 1996, after the department was started, it moved to the new building in 2010 with the name of Advanced Center for Plant Biotechnology with an area of 3,380 square meters. And the building now consists of research and training laboratories, classrooms, computer room, seminar hall, auditorium, a library, which was funded by DBT. And the department has both wired and wireless internet connection. It is a well-equipped department, and we have all advanced equipments like DNA sequencer, RT-PCR, HPLC, ultracentrifuge, deep freezer, lyophilizer, and recently through DST FIST funding, we've been able to get a GCMS, a fluorescent microscope, multiplate reader, tissuelizer, DNA fragment analyzer, and the list continues. Yeah, for a brief history of the department, as I just mentioned, in 1996, the Department of Biotechnology started, and this was housed in the old, North Block of GKVK, College of Agriculture. So it started in 1996, and the MSc in Plant Biotechnology program was started in 1996. In 2003 and 4, the PhD Plant Biotechnology program started. In 2005, there was merger of the departments of Plant Biotechnology with Plant Biochemistry and Basic Microbiology. And in 2006-7, the BSc Agri Biotechnology program was started in Hassan. And in 2010, the Advanced Center for Plant Biotechnology came up. And recently in 2021, we have started an MSc in Bioinformatics. It's not changing. Okay, yeah. So this is a brief history of the department. The picture that you see here is where the old biotechnology department was placed. It was, as I said, in the North Block of the GKVK, Agriculture College GKVK. And initially, the department was spread over 3 floors and across in all directions. And later, and this continued till 2010 when the new department came up. So in the ground floor, it was the biochemistry and basic microbiology, which labs were there. And in the biotechnology labs were spread out over in the first floor in both wings. And later, these departments came together in 2010 in this building, which is the Advanced Center for Plant Biotechnology. And it is continuing today. And as we have rightly remembered that this is the Teachers' Day, a number of faculty of this department have actually contributed greatly to the development of the department till today. And at this venture, I would really like to thank Dr. T.K.S. Gowda, who is here, who was the first head of department of this department. And under him, the department started with very meager facilities in the North Block. And along with him, Dr. Tirtha Prasad, and I remember Dr. Tirtha Prasad, who also was here to start the department. And then Dr. Ramanjani Gowda sir, our honorable board member, Dr. T.H. Ashok, and Dr. C.K. Suresh, Dr. Vijay Kumar Swami sir, Dr. H.E. Shashidhar, Dr. Dayal Das, Dr. R.L. Ravi Kumar, Irena, and also Dr. Geeta Ramachandran, Elizabeth Madam, and Dr. Uma Poddar Madam. So here, I would like to just point out a few things. It started with Dr. T.K.S. Gowda as head, but the department really grew because of a collaboration that the department had under his able guidance with the Kirkhouse Trust. And I would like to recall Dr. Southern's contribution here, for the training programs, which built up the initial labs. And of course, later, the lot of funding that was brought in by Dr. Tirtha Prasad and Dr. Ramanjani Gowda sir, because he operated many DBT projects and also was instrumental as chairperson of the DBT HRD program, DBT Hub program, and DST FIST programs. And Dr. Ashok and Dr. VKS, Dr. Shashidhar, all of them have contributed immensely to this department. And Dr. Ravi Kumar sir, Dr. Das, each of them have contributed in their own way. And I would just like to recall Dr. Geeta Ramchandran Madam, Dr. Elizabeth and Dr. Uma Poddar Madam here, because they were all faculty of biochemistry, which later got merged. I have studied both under Dr. T.K. sir and also under Dr. Geeta Ramachandran. And I think the basics that they left for us, even today, it helps a lot. And we're really thankful to sir and to madam and to all the faculty who have really helped us grow in this department, because each of the faculty have contributed greatly to this department. At this time, I also recall Dr. Timaya sir and Dr. Sudarshan, late Dr. Sudarshan, And I think I would like to pay my respects to Dr. Tirtha Prasad, late Dr. Tirtha Prasad, whom we just lost a few weeks back, Dr. C.K. Suresh sir, and Dr. Sudarshan sir. We have lost them at a very young age, but yeah, they have all made a big impact on our lives. And I would especially like to recall Dr. Sudarshan sir, who really contributed a lot in biochemistry. Yeah, so this is the current faculty of the department. It is Dr. Harni Kumar sir, who's our present administrative officer, who has also contributed immensely to this department. Dr. Shamlama, one would have to recall her contribution in jackfruit. Dr. Veena S. Anil, biochemistry, and she's known for her research in compost tea. Dr. Benharlal from biochemistry, Dr. Ningaraju, again from biotechnology, and Dr. Mohan Chavan, biochemistry, Dr. Nagesh, he's a biotechnologist again, and Mrs. Purnima and Dr. Bhavani. So this is the faculty now. So totally, the total number of students between 1996 to 97 till now, we have 575 graduates of MSc who have passed out and 85 PhD in plant biotechnology. And this is sort of a bird's eye view of people who have graduated from this department and who are placed in different places, working and pursuing doctoral studies outside India. Many of them have completed their doctoral degrees and their postdoctoral studies, and they are working in different places outside India, and also doing their doctoral and postdoctoral studies in different labs all around the world. And it is important for us to know that also many of our faculty, they are in national institutes like CSIR Institute. Dr. Dinesh is here, I think. So he is heading the CIMAP in branch in Bangalore. And we are very happy to note that many of our faculty are working as assistant professors in different state agricultural universities of UAS Bangalore, UHS, and UAHS. And also, many of them are working on contract basis too as assistant professors. ICR institutes also. And also I would like to recall here that many alumni from this university and this esteemed department have established industries which are doing very well, and many work in industries too. Banking sector also, there are a lot of students of ours who are there, and they have passed out in different years, right from 2003-04 and till date. Many of them are absorbed in banks too. And Dr. Chandramohan, Mr. Chandramohan, he is with the media, mainly with ETV, and Gangadhar Murthy and Shashikala. These were students from, I think, 2004 batch. They completed in 2004, and both of them are in IT. So we have students in all different fields. And state government, in agriculture department, civil services, we have many students who are there too. And Bangalore Diary, Mr. Madhusudan works there. And apart from that, we also have a number of people in the police department, like Mr. Sunil Kumar and Mr. Sadiq Pasha, ICRISAT, Dr. Yogendra. And of course, very recently, the university has started the Agri-Innovation Center, which is funded by the Bionest. And three of our alumni, Ms. Lakshmi Shah R, Dr. Priyanka, and Dr. Brijesh, they are part of the Bionest. Yeah, and as we come to the end of this presentation, I would just mention a word of obituary to Dr. Tirtha Prasad. He joined the university in August of, he was there in the university from 30th August 1982 to 31st August 2017. Former head, Department of Plant Biotechnology, University head, Department of Plant Biotechnology, Dean Agri, College of Agri Horticulture. At this time, I also would recall Dr. C.K. Suresh sir. He has also immensely contributed to this department, and Also, Dr. Sudarshan. I think many of us who have studied under him will never forget. He was such a good biochemist and a practical biochemist at that. So this department has had many of these esteemed professors who have really been with us. So I thank the department for giving me this opportunity. And as we have seen, this department in 1996 started with very meager facilities. And today it is a full-fledged department. And we have MSc programs in plant biotechnology, biochemistry, bioinformatics, and we have a PhD in plant biotechnology. And very soon, this year, we'll be starting a PhD in biochemistry. So it has grown over from 1996 till now in a very big way. And we hope and pray that God would lead us through the remaining parts of the years. And we thank all the pillars of our department who have, really helped us and helped us to reach this phase. Thank you so much.
Linda Wyatt has rightly said, a silver jubilee is a time to pause and reflect on all the good work done. It is a significant milestone and time to look back and thank every person who has contributed. Thank you so much, ma'am, for briefing all of us about the journey of the Department of Plant Biotechnology. And we all feel privileged to be part of this department. So moving further, it gives me an immense pleasure to introduce and welcome Dr. Vibha Ahuja, Chief General Manager at Biotech Consortium India Limited, New Delhi. She's an expert on biosafety and regulatory aspects, particularly with reference to genetically modified organisms, having more than 25 years of experience in the field. Throughout her long and distinguished career, she has been actively involved in capacity building initiatives in India and throughout South Asia. I request Dr. Vibha Ahuja to address the gathering. Please.
Respected Vice Chancellor, Sir, Dr. Rajendra Prasad, Shruti Ramesh, CGM NABARD, Dr. Ramanjini Gowda, Dr. Harini Kumar, and all the distinguished guests on the dais and off the dais. It is indeed a great pleasure for me to be back at this university. I have had long association of organizing various events and interactions with different faculty members and different departments of this university. The latest one being, as mentioned by Dr. Shamla, was about 2.5 months back. In this very hall, we had this meeting on gene-edited plants. And then after that also had a very good interaction and valuable inputs from Honorable Vice Chancellor, Sir, in another meeting for the animal feed industry, where we were discussing some other aspects with the poultry and the dairy industry. I would like, and it is, as I said, it's always a pleasure to be back here. And I thank the organizers for inviting me and giving me this opportunity to interact with you and inaugurate this very interesting event on the future prospects of biotechnology. So just very briefly, to this August gathering, I don't need to talk about the challenges which are being faced by the agriculture today, but I would like to share with you some of the developments which are going on globally and how we need to move forward. You see, we have seen the use of modern biotechnology advancing like anything all over the world. As we learn the genetic blueprint, the applications have emerged in agriculture, particularly starting from molecular breeding to the genetic engineering plants, and then we have gene editing, and the road continues. We are seeing the synthetic biology, products of synthetic biology coming in the market, and then moving on to another new area, that is the gene drives. So we have to make use of all these things. Even in our country, there are advancements which are happening, and our national biotech strategy, which is for 2021-25, has also laid a lot of emphasis on the use of agriculture biotechnology, dealing with various aspects. But today I would like to draw your attention, with all this happening, to a very important area that we really need to, with all the very good research happening, We need to take these technologies from lab to land. That is one area where, we sometimes miss out, and which is very important if we have to see the fruits of all this hard work come to the benefit of the society. And this is not only important for, our society, but also helping the country achieve the targets. We have all the targets of SDG 2, Sustainable Development Targets on zero hunger, and so on and so forth. But all this will come only if the innovations in our scientific departments reach to the society. And I would like to also share with you here that, there are a lot of opportunities available. BIRAC is there. It was mentioned that BioNest, some facility has also been inaugurated. There are numerous schemes available. Funding schemes are there by BIRAC, right from your idea till the end of your, whichever stage of research you are in. And of late, we have also seen very good initiatives by the government on the enabling policies. Why we had the meeting last time was after a very good notification by the government where they have exempted the certain categories of the genome edited plants free from any regulations, a very simplified process. So it is a very opportune time for all of us to make use of this funding options, enabling policies, and all the positive atmosphere around to take forward the research that is in the labs that you all have done with your hard work, and take it forward for the benefit of the society. I would very briefly like to mention that Biotech Consortium India Limited, my company, we are also the official, we have been designated as the technology transfer office for all the Department of Biotechnology institutions and the projects supported by the DBT. So if there is anyone who wish to take forward, we also provide regulatory support. So if there's any stage of your development that you are looking forward for guidance on how to take it forward, how to generate the data, how to reach out the economic efficiency of the, assess the economic viability of your technologies, please feel free to connect with us, and we will definitely help you take forward. I won't take too much of time. The program that has emerged in this conference is very good, and we have very interesting talks, lead talks by national and international speakers have been very nicely, compiled, and we look forward to hearing from all the speakers and take the scientific learnings forward, identify them, and then take it for the benefit of the society. Thank you so much. Thank you.
I thank Dr. Vibha Ahuja for the inaugural talk. Thank you for giving an insight into the policies, ma'am.
It is my privilege to invite Shri T. Ramesh, Chief General Manager, NABARD, Bangalore. With a diversified experience of 35 years, he has worked extensively all over the country and been associated with developmental projects including watershed development, tribal development projects, self-help groups, and farmers producers organizations. I request our revered Chief Guest Shri T. Ramesh to address the gathering and give his valuable inputs. So please.
First of all, a very good morning to all of you. Honorable Vice Chancellor of GKVK, Dr. S. Rajendra Prasad Avare, Dr. Vibha Ahuja, CGM of Bioconsortium India Limited, Dr. Sheelavantar, and a host of dignitaries on the dais and off the dais, and dear delegates who are participating in this seminar. First of all, let me congratulate the Department of Plant Biotechnology on this momentous occasion of celebrating the 25th anniversary. And on this occasion of Silver Jubilee, I would like to congratulate not only the present VC and all the VCs and the eminent professors who have made this department a proud place in the country. Why I say this is, in fact, of the biotechnology industry in the country, Karnataka holds the first place, and no one can doubt about it. And if that place has come, definitely an important role has been played by this department. In fact, when people were just thinking, what is this biotechnology? The university had gone ahead and established a department, separate department in 1996, and this has really contributed for the success of biotechnology field in Karnataka. I would like to once again express my hearty congratulations to the university for having done this. One thing I would like to admit very frankly in front of you, I'm not a scientist. I'm a financial expert. So I would not speak from a scientific angle, but from a financial point, like I see a lot of students over here, and I would like to brief and see many of you coming to our institution about taking, like Madam was saying, a huge opportunity lies ahead with us. How we can take it this forward and where you can stand in the next decade or so, probably how NABARD can support you. I would be dealing more on those aspects. Okay, with this, at the now all of you are definitely agreeing that with this dwindling resources, not only in India but also across the world, there is a need to produce more for ever increasing population. In fact, global population, which is expected to reach around 9.6 billion by 2050, which is almost 40 to 45% increase from the present level, definitely needs a sustainable increase in production. In fact, the most suitable agricultural lands have already been used across the world, including in India. And this is where this technology is going to be, this biotechnology is going to play a vital role in the next coming decade or maybe decades ahead. In fact, realizing the importance of biotechnology sector, the Department of Biotechnology, Government of India, through its National Biotechnology Development Strategy announced way back in 2015, lays more emphasis on generation of biotech products, processes, and technologies for enhanced efficiency, productivity, and cost effectiveness in the areas of agriculture, food, and nutritional security. Advances in plant biotechnology are making crops more resistant to pest, disease, infestation, and also increasing the agricultural productivity and also contributing to the resilience of the farmers to the climate, or what I can say, environment shocks. At this juncture, I feel we need to play, we in the sense, India need to play a major role to ensure a food security. Not only, of course, we have reached a food security in the country, but world is looking to our nation for food security across the world, particularly in some of the impoverished economies. In fact, there is a need for us to produce more for the world also. In fact, taking this biotechnology for increasing the production, if the present position of biotech in the industry in the country, we rank on 12th destination in the world, and in fact we are the third largest third biggest destination in Asia. And in fact, biotechnology industry as of now has around 3,500 startups, but it is expected by 2025, it is expected to reach around 10,000 startups. And also it is estimated, it is expected the size of the biotech industry is expected to grow to around 150 billions by 2025. I think this gives a vast idea of how this sector can play a very important role, and that is where I would urge upon the young students who can take advantage of the vast opportunity available to you. And in fact, this industry can play, a biotech industry can play a very vital role in ensuring that India reaches its goal of 5 trillion economy in the next decade or so. Coming to the Karnataka, as I have already said, has played a very important role in biotech revolution. And in fact, it is considered to be the biotech hub of the country. More than 60% of the biotechs are based in Karnataka. In fact, if you see the website of MCA, almost 5 to 6 or maybe 7 to 8 biotech companies are getting started in Karnataka every month. every month, I see. In fact, Karnataka is the first state to frame the biotechnology policy. In fact, way back in 2001, it was framed. Right now, the biotechnology policy of 3 aims at maximizing the bioeconomy potential of the state through various measures. In fact, bioeconomy measure, if I have to just explain in a little more. In fact, Karnataka Bioeconomy Report of 2020 states that state's bioeconomy is valued around 22.6 billion, which is almost 10% of the bioeconomy of the country. In fact, it is almost 1/3 of the national bioeconomy of around roughly 65 billion. In fact, when we see at the national level, the bioeconomy is contributing to only 2%, whereas in Karnataka, it is almost contributing to 10% of the state's economy. That really gives you a very important place which biotechnology is holding in Karnataka. In fact, Karnataka government has even set up a target that over the next 5 years, there is a need to reach to 50% of the national bioeconomy should come from Karnataka. That is the policy which government of Karnataka has set. I'm sure this gives a vast scope for each student who is here who can really make a lot of potential exploited. In fact, the role played by the scientists, research institutions, and industrial bodies really gives really kudos to them. And in fact, this sector has made a very good progress. In fact, I am confident that the deliberations which is going to take place in the next 2.5 days will give a lot of thematic areas, including industrial biotechnology, what I see, entrepreneurship in biotechnology, focus on harnessing it. I'm sure it will focus on harnessing the potential available in the sector in the decades to come. I think before I conclude my address, I would like to quickly share what NABARD is doing for this agri startups in the country. In fact, National Bank for Agriculture and Rural Development, which has completed its 40th year of journey. We had started way back in 1982 as a refinancing institution, have moved a lot now, and we are contributing a lot for agri sector in the country. And in fact, last for 1 decade, a lot of innovations in agriculture have been supported by NABARD. In fact, we have been supporting agri startups in both category 1 and 2 since 2004, and we have committed an amount of roughly 550 crores for this agri startups in 22 funds. Directly, we will not be giving. It will be given to an alternate fund, which will be investing in the agri startups, and the commitment given by NABARD is around 552 crores, of which around 460 crores we have already dispersed. And these agri investment funds have in turn supported close to around 1,700 crores across the country. So that almost 3.5 times of the commitment which NABARD has released has been given to the agri startups. In fact, we are also forerunner in supporting innovations across the state agricultural universities, and we have supported establishment of 6 rural business incubation centers across the country. And right now, though we have supported 6 more are in the offing. Maybe a policy is being tweaked to say a little extent. Maybe once the policy is tweaked, we can expect such rural incubation center to come up in GKVK also. That's my wish. In fact, NABARD is also established a separate subsidiary. See, looking into the vast scope available for agri startups in the country, we have decided to establish an exclusive subsidiary called NAB Ventures. This NAB Venture is a subsidiary which clearly or which specifically it invests in venture growth equity funds, which are the agri startups company, which are in agriculture, food, rural business, and agri and rural financial services. These are the sectors for which the NAB Venture is supporting. And in fact, we have committed almost 600 crore in this NAB Venture, out of which we have already released 148 crores. Some of the very important companies which have been supported, I think many of you would have heard of its name. Jai Kisan, which is one of the very well-known name, is the fund supported by NAB Venture. Similarly, Unnati, Krishi Tantra, and Satyukt Technologies, Tender Cuts, you name some of the prominent agri startups which are making a very good vibes in the country. They have been supported by NAB Ventures. In fact, some of the units which are supported range from not only satellite-based agri apps for micro weather data, but also the traceability of the food products, value chains, online marketing platform. You name anything, these have been supported by NAB Venture. I'm sure the students, young students who are sitting here, it will be my wish that at some point of time, some of you will be coming onto our fold, maybe shortly, next 2-3 years. I would be happy to see you being funded by NAB Ventures. Okay, so to conclude, what I would say is, for addressing the multidimensional challenges which are faced by agriculture, biotechnology can play a vital role, not only in ensuring the food security, but also nutritional security. I'm sure taking this forward, all of you will be able to contribute and make a big stride in the economy. And I'm also wish that the findings, the deliberations which is going to take place in this conference over the next 2 days, it's very important that it should reach the eyes and ears of the policymakers. I'm sure we will be able to communicate these findings or deliberations to the policymakers so that the policies also can keep evolving or changing, which can make a wide difference to the sector. Once again, let me conclude by expressing my sincere gratitude to the organizers for having given me an opportunity to share my views with you. And I wish this conference a great success. Thank you.
Thank you, sir, for giving an insight into the ongoing escalation projects in the agri-biotech. And I take privilege to invite Dr. P.H. Ramanjanikoda, the member of the Board of Management, US Bangalore, and the former professor and head of the Department of Plant Biotechnology, to please address the gathering.
It is a very surprise for me that I have not been told earlier. Anyhow, dignitaries present on the dais, Dr. Rajendra Prasad, the present Vice Chancellor, Dr. Sheelavantar, who is my favorite Vice Chancellor. In fact, during his time, I became the head of the department out of turn. They never gave out of turn head of the department, but he recognized me and he told that you should head the department. It was a very crucial time when Dr. Tirth Prasad went for Pune and there were a gap. Actually, he called me and he asked me that even though you are a junior, I want you to take up the task. So I did my best during my time. I thank you, sir. And Dr. Ramesh ji, Dr. Vibha Ahuja, in fact, I know her from so many years, maybe about 20-25 years. We went together to US for some of the DBT programs. In fact, we have arranged a lot of GM crops debates in this auditorium, in fact, and also in other places. And my colleagues and board members, Dr. Dayanand, Dr. Sriram, and our favorite professor, Dr. TKS Gowda. In fact, he is one of the pioneer. In fact, when he started the department, there was nothing actually. He used to borrow from other departments, from microbiology. He was head of the Department of Microbiology. When he came to Department of Biotechnology, he used to get something from microbiology. In fact, I remember, and Dr. Harni Kumar and Dr. Sriram and Dr. Prakash, Dean Agriculture, and Dr. Shamlama, head of the Department of Biotechnology, and people who are off the dais. I cannot name everybody, Dr. Vijay Kumar Swami, Dr. Ashok, everybody is here. I want to tell you a few things about our department. Our department has contributed a lot. In fact, it has not been highlighted. For example, we can say that plant vaccine is the trump card of our department. In fact, we were the pioneers in developing the edible vaccines in rabies, and we were the first people to get the patent, Indian patent. In fact, it was appreciated everywhere. In fact, we have gone up to trials and we could succeed actually. And also about the molecular breeding. In fact, it's in our department they did a very good research on molecular breeding. We have come out with even the tomatoes with high shelf life. And also there are Dr. Ravi Kumar has contributed, RL Ravi Kumar has contributed for maize development using the molecular markers. And also chickpea, he worked on chickpea. And even tissue culture, they contributed a lot. And also the NPU virus by Dr. Anita Peter, jackfruit research by Dr. Shamalamma, the biofuels from Arni Kumar. There's a lot. In fact, we have not highlighted properly. That is the only thing. See, people do little things and they highlight. But unfortunately, in our university, we have done a lot, not only in our department, in other departments also. We have not highlighted. We have done a wonderful work in this university. I am proud to say that I am also this part of this university. And recently, in fact, day for yesterday, I read that the confined field trials have been approved for cotton and maize for herbicide resistance and bollworm in cotton, and also in case of maize also. It's a great success. In fact, you can tell Raichur and Dharwad universities, they are going to take up these confined field trials. As Dr. Ramesh has mentioned, like the thing is, the future is biotechnology. Like you see that lot of lands, especially the paddy lands, or with which are we cannot grow any paddy anymore, like because of the salt problems, and also some of the pests and disease problems, which can be addressed only by biotechnological means. Especially transgenics have been a little problem because of the use of antibiotic genes and other things, which is no more. People are opposing this technology. But when CRISPR-Cas has taken up this place, it has become more easier to either to insert the gene or delete the genes. This is a boon. CRISPR technology is a boon for breeding these varieties. In future, in fact, we need to adopt this technology, biotechnology. There is a very good scope. We have a very good future. I can tell you the biotechnologies, especially the DBT, Department of Biotechnology, Department of Science and Technology, and many of the organizations, they are funding these things. Like now the startups, there are a lot of BIRAC. In fact, BIRAC is funding a lot. NABARD is funding. So there is a very good scope. I wish you all the best. Thank you.
We are really blessed to have you, sir, and your words have truly encouraged and motivated us and will follow your valuable advice. I request Dr. TKS Gowda, Dr. Ramanjini Gowda, Dr. S. Rajendra Prasad, and all dignitaries to release souvenir aggrandise silver footprints on the occasion of Silver Jubilee of the Department of Plant Biotechnology.
I take privilege to invite Dr. S. Rajendra Prasad, Honorable Vice Chancellor, for the presidential remark.
On the dais, Shri Ramesh ji, the CGM NABARD, Bangalore, and our mentor and earlier our Guruji, Dr. Shilwantar Saab, the former Vice Chancellor of this esteemed university, and my dear respected Board of Members, Dr. Ramanjini Gowda, Shri Ram, Dr. Dayanand, and the founder of this biotechnology department, Dr. T.K.S. Gowda Saab, and Dr. Prakash, Dean, College of Agriculture, and Dr. Shamlama, the head of the department, and all the officers and the dignitaries, and also my dear students, friends, and the media. First, I would like to congratulate the Department of Biotechnology for organizing this biotechnology trends and the future prospectus to commemorate its silver jubilee and put across the few of my thoughts on these auspicious occasions. Friends, when the green revolutions took place, so there at that point of time, the thinking and the promotion of the yielding varieties, quality seeds, and inputs. So after the success of the green revolution, the ICR organized, at its 50th year of completion of the green revolution, they organized the one brainstorming session how we should go for the second green revolution or evergreen revolutions. What are the agenda or what are the priority we have to set to address these challenges? So during that time, I was the director of the Indian Institute of Seed Science at Mau. I was also called from the seed point of view, what is my vision and what should be the things. At the same time, there are a lot of people, not only from the academicians, there are also people from the industries, policymakers, so many people. And the whole day there was a presentations when the DG at that time, Dr. Ayyappan was the DG, and they asked how it should be the priority area for the different set of group of people. Then many things have been listed. Of course, the oilseed crops, pulses, and also in terms of technology, hybrid technologies. And among them, the one technology was emerged as a biotechnology. Yes, many speakers already mentioned why we have to focus on biotechnology. Yes, now the populations is going up and up every year. To address the security, food security, we need to go for that. At the same time, the cultivable area is shrinking because of urbanizations. Under that situations, how the technology should be promoted so that we should address the food security and also the now presently more focused on the nutritional security to be addressed. So one of the suggestions and the thing is nothing other than the biotechnology, mechanizations, so many things. And that is how this technology, that is biotechnology, has emerged. If you look at the progress and why we started about 25 years back, during that time, there was a need and it was an emerging technology. And the university at the time, the vice chancellors and the policymakers in the university thought that we should have it. So with that intention, department was started, and today we are celebrating the silver jubilee. I must thank all the professors, the faculty who toiled to achieve a lot more things from this department. As rightly pointed out by Sri Ramesh ji and also the Dr. Ramanjini Gowda, many things have been emerged, but how it should be translated, that is the most important thing which we have to address. So that way, not only developing the biotechnological tools, at the same time, we should have a strong extension functionaries which should promote this technology to the end users so that we can address the today's challenges. The friends, I'm not going to name the people who are really toiled because they're all sitting here. Dr. Ashok and Vijay Kumar Swami, Dayal Das, TH, Shashidhar, and so many people are there who have taken the lead. And recently, Dr. R.L. Ravi Kumar, and during my tenure, and he established the FIST program, and really wonderful facilities have been created in the department. Just I wanted to recall one thing during the, my association as a, PA of the 6 projects have been sanctioned from the RKVY. So among the 6 projects, mine was the, seed project. The other one is the biotechnology project. Always, when they ask the progress, the biotechnology department was, shy to, I think Ashok is there here. So he used to say, what I should present, how should I present? Because always this RKI funding objective is immediate returns to the farmer. That is the objective. So that way it was taking time. But in our case, my project is produce some seeds, produce some technology, give it to the farmer, straight away goes to that. So in that way, among all the 6, our project and the marketing project was really doing a good work. Under that shelter, Dr. Ashok is to take the progress of this biotechnology. Though they are doing the progress, but the showing the progress to the policymaker, it was a little bit difficult. Today, I must thank, at that time, I think one Ramaswamy was the, the principal secretary who strongly supported all this project. Because of this, that today we have that, the building, that is biotechnology building. So just I wanted to recall at this point. The another thing which I would like to mention here is many things have been, emerged, as our earlier speaker mentioned. Why the another, just I wanted to mention few things about the thematic area which you have selected here. I really was impressed because this was similar to what we have worked recently on the CAST project, that is next generation technology for the adaptive agriculture, wherein many components have been included here. So here the crop improvement by molecular and biotechnological approaches. Today we are witnessing how the climate is changing, and we are addressing flood, we are addressing drought. But at the same time, we need to provide the varieties suitable for different planting windows, different planting, the environment. So that way, I think we need to take the support of the biotechnological tools. And I hope today, you people, there are so many presentations I heard, they are listed here. Around 300 participants are there physically, and about 170, I believe, are online. So your deliberations, as many speakers mentioned, should be focused, and you should come out with some kind of recommendations for the various stakeholders. That is most important thing. The other one is the environment and biofuel biotechnology. This is, when you say environment, I mentioned about the climate change and other things. And the other one is the endophytes. This is a one area which was not maximum and uncast, tapped. So it should be one of the area to address both biotic and abiotic stresses. And Honorable Prime Minister was also mentioning about we should go for the natural farming, organic farming. So in that situation, in that context, I believe the endophytes play an important role to address these biotic and abiotic stresses. I think biological tool has to be, address these, resources. Then the biocontrol agents, then the biofertilizers and PGPRs and biofuels. In fact, our university has established one biofuel laboratory, biofuel testing laboratory. Yesterday, it was, fully equipped and managed and under the support of the HAL. So why we have to? Because this is the one, the green technology that is, biofuel we would like to replace with the import of so many oils, at least partially. In that context, we have established, I think there is a huge scope for the biotechnologists to, make use of these facilities and come out with good technology in this field. The another one is, we are talking about the IFS models, because our country is having more than 82 to 84% of the farmers are marginal and the small farmers. So for the sustainability for their livelihood, what should be the this? We are recommending the IFS model. When you say IFS model, what are the components? And other than the agriculture, horticulture, we also have the fish and the animal components. So this is the one important. In the animal sector, the technology has been emerged by the biotechnology. Look at the vaccines. How many diseases can be controlled by using the vaccines, by using your technology. In fact, in the North India, there is a lot of the animals are dying now. Now it is a challenge for all of you to develop the vaccines. You identify what exactly it is and come out with the things. So this is one area where you can deliberate and see that some kind of the recommendations should come. The another thing is, you are already witnessed the COVID situation. Under that, our own alumni, Dr. Krishna Ella, has developed the vaccine. Again, he has used the Bharat Biotech. So he's the one of the, icon in the country, not only at the national level, at the international level. So he has used this tool and he has addressed the important the diseases which was devastating many of our programs and the different sectors where your biotechnology has come into the rescue. So like that, there are so many opportunities where you can. Then the last one, which I would like to mention about the entrepreneurship in biotechnology. Yes, when you talk about the entrepreneurship, I could see a lot of people are there. So our Sri Ramesh has mentioned about 3,500. So our target should be, entrepreneurs should be around 10,000 in the near future. So that means you just imagine how much scope you people have as being a biotechnologist, but only thing is a tap. So again, when you talk about the biotechnology, we are also looking at the agricultural biotechnology. So there are a lot of things. This is the one area, agriculture biotechnology. As a whole in the agriculture, many people have not tapped it. This is a big area to become an entrepreneur, and so that you can not only serving the people by way of giving the good technology, at the same time you are also employing many people. So this is one area where I wish you should. So lastly, I would like to mention few things about our university has made. They have listed a lot of things. Again, the one thing which when I was saying about the crop improvement, it is not only the food security. I wanted you to also think about the nutritional security. So in that context, how we have to address using the biotechnological tool. In fact, today, though we have producing sufficient food, but still the malnutrition is there. So to address this, the ICR have taken initiative to develop a lot of fortified varieties, but it is less. But still, though those varieties have developed, but still it is not, utilizing by the end users. So this is one area where we can think of. Then the BT, yes, we have made a big impact by developing the BT cottons. Today, how much resistance it was in the beginning, but later on 95, more than 95%, the cotton in India is BT cotton. So our neighboring small state has developed the, brinjal, BT brinjal. So now they are doing. So that way, there is a huge scope for so many, the crops, even including the food crops. So only thing we have to address the security. So that I think Dr. Uja Madam is going to speak on these issues in the coming, sessions. So with this, I would like to once again, congratulate all my colleagues. And another, thing mentioned by the Sri Ramesh, it is not only, he was saying, just he mentioned, you see, I am not a scientist, I am a financial advisor. Sir, I'll tell you, to do anything without finance, we cannot do anything. So without money, nothing will happen. So our scientific advance, for every scientific advancement, your presence, your money is required in that way. So you are positively correlated with the scientists and the evolutions. So that way, thank you so much for all the support which is extending to our university. I wanted to mention recently for most of our colleges outside the Bangalore, he has supported like anything 45 crores worth for this year itself. Thank you so much, sir. And also earlier, you have mentioned you have supported for the establishment of hostels and the infrastructure. So thank you so much. And another, my request, you have already mentioned, I wish there will be a incubation center. Sir, we have submitted a proposal, I think, to the worth of 19.5 crores. I believe it is in the final stage. I thought it will be materialized before my, tenure, but still it has not happened. Even though my own professional chairman is there sitting in the NABARD, our own, professional man, C technologist. So of course, I believe it is going to happen shortly. Thank you so much, sir. And last point, which I would like to mention about Dr. Sheelavantar sir, the vision book. One day he came, you see, we're all working for 3 years, 4 years, and we'll go back. Once we start working with this and the positions, we'll come across with so many ideas, but we'll not have the opportunity to implement the total ideas. So why don't you put those ideas on the records so that the future people who take over as the vice chancellor can make use of those ideas if they like it. So that was his, idea. Then I said, sir, if that is the case, you please let me know what you have written. So I'll see that our publication center is going to publish. This should become a routine so that the coming vice chancellor will get a chance to analyze what is required by the university and what are the things to be done. That way I agreed, and you have made one contributions. And I would like to thank you, sir, profusely for your vision document. I think this vision document is going to help our, the next, the people to take it forward. So with this, I once again congratulate and all the best. The final advice or the request is to the organizer, all the proceedings and the recommendation should not be in the book or in your shelf. It should go to the respective departments. If it is a policy, you make the recommendations based on the different stakeholders. If it is on the policy, let it go to the government. And at the same time, it is for the farmers, it should go to the farmers or the departments. If it is for the scientific community, it should spread across the scientific community. If it is for the social, so it should go. So that way you make your points, even if it is a one point in each, the sector, that is good enough. And see that after this one, you should follow up and see that at least a few points which emerge from this, international seminar should come into a implementation mode. So with this, thank you very much. Have a good deliberations during these 2.5 days. Thank you.
Thank you, sir. Thanks for your kind remarks. And as you suggested, we all will try our best to come out with the suggestions from each thematic area. Moving forward, as said, gratitude is not in the words, but in the heart which expresses it. With this, I would like to invite Dr. Harini Kumar, AO, Professor and University Head for the deliverance of vote of thanks.
Thank you. Good morning to all of you. Once again, welcome all the participants from all over the country. to have a nice stay in Bangalore. This occasion, actually, our Honorable Vice Chancellor, Dr. Rajendra Prasad, is a very supportive. When we met him in the first, we want to organize 3 months back, sir told you, is this possible? It's a short time that. The question was raised by him. Then we said, sir, we'll put our effort and make it successful. I hope today you're looking at the participants and our arrangement. I think you have done good work on that. Sir, thank you for supporting for all the ways. Always you say yes and go ahead. The word always you can remember is a go ahead. And you are done, sir. Thank you so much for accepting our invitation, sir. And done things, sir. So in this occasion, Dr. Vibha Madam is always with us. We have conducted so many programs, except last one program we missed with the biotechnology. I hope we'll continue the same in the future. Thank you, Madam, for accepting our invitation. And thank you so much for delivering the good lecture on that. Actually, when you come to the administration, my role model is Dr. Shilvan sir. When you come from Bangalore to GK, from Monday to GKVK campus, sir has given a good responsibility. And when look at his name in the program sheet, I'm very happy to with us, sharing the dais with him. Sir, thank you so much. And your vision and your idea is also with us, sir. We are following till today, your administrative logic and other. Thank you so much, sir, accepting invitation and be with us. Sri T. Ramesh, sir. Actually, when I met him, I thought, sir, from other part, I always look Nabad with from other people. But when he starts speaking in Kannada, I was so happy. Sir is from Karnataka. And also, sir, always with us and supporting all the program. And thank you so much, sir. Always with you. And we'll conduct few more program with a wonderful talk. Thank you so much with us on delivering a good lecture. Particularly, we all the scientific field think only on the research, but economy was we never thought of it. But today has given very wonderful figures, facts about how the biotechnology and role in the things. Thank you so much, sir, for with us and delivering wonderful talk. I need actually we can invite one more talk and deliver the talk to our students to gain lot of knowledge on the biotechnology. So it is a great pleasure to my beloved teacher and the mentor. When actually after completion of degree, I didn't have a job. Means not a job, means it is not easy to get a job like assistant professor. Sir told the future is always there. Dr. T.K.S. Gowda, my mentor, and us. Thank you for with us, sir. Thank you so much. And sir is going to deliver a wonderful lecture for you. And thank you so much for coming this program. And thank you, sir. So, and also thank Dr. Prakash, Dignitary, always supporting and very dynamic and supporting for this program. Thank you so much for the. It is a great pleasure to thank my beloved teacher and also mentor and inspiration for me, Dr. P.H. Ramanjanagoda, sir. Always support our departmental programs for this today's occasion. Thank you so much with us, sir. And our honorable board member, Dr. Y.S. Dayanand, sir. Thank you for your support. Thank you, sir, be with us and supporting for the program. Another board member, Sri Ram, sir. Thank you, sir. Thank you so much for our supporting for this. So, apart from Sri Brunda, ABM, NABARD for their kind support. Thank you so much. Yeah, Madam Brunda, Madam is there, please. And also for the success of the program, you always the blessing and the support of our Dean Dean Agri, Hassan, for supporting through the student participation and others. Thank you so much. And Dean PGS and also Special Officer And D also with us, always supporting for the programs and particularly media and others persons who are involving here. And also my HODs and the teachers, Dr. Ashok sir is with us. And also Dr. Vijay Kumar Swami and all other faculty members who are supported for this program. Thank you for participation, sir. I'll also like to thank all the speakers, both from national and also international. And Dr. Kishore from Korea is alumni of US Bangalore. Now he's with us. And also other speaker also from all over the world. They're going to deliver the lectures. And I'll thank all the participants who registered both offline and also online. And also like to thank all the members and the faculty of and the staff of the biotechnology and also agriculture university and all other departments. And like to thank Dr. Shamlama, nicely organized, and his team. They work day and night for the success of this program. I thanks once again all the participants and media persons and HODs from the different department. And also again, once again, thanks all the dignitaries on the dais for their support. Thank you so much, sir.
I invite Dr. Shamla Maes, Professor and Head of the Department of Plant Biotechnology and the Organizing Secretary and the entire Department of Plant Biotechnology for felicitation.
I'm very happy to announce that Dr. Rajendra Prasad sir, our Vice Chancellor, will be retiring from the post of Vice Chancellor shortly. So on this occasion, we want to felicitate sir. Sir, please accept our felicitation. Thank you very much, sir. So I request all biotechnology faculty to join the program. Sir, thank you. Sir, please, sir. Please, sir. Please, sir.
Hereby I take the privilege to conclude the inaugural function and request the gathering to rise up for the national anthem. Once again, on the behalf of the organizing committee, I thank the gathering wholeheartedly and I request everyone to join for the high tea outside the auditorium. And let us all assemble by 12 p.m.
I request all the delegates who have registered for the crop improvement, kindly display your poster. It is from 10 to 4. The poster display, it is near the corridor. So kindly display your poster.
Hello.
Okay.
Hello, everyone, and a good noon to all of you. So we would initiate the sessions on the lead talks. So the first would be on crop improvement by molecular and biotechnological approaches. The first theme would be on crop improvement by molecular and biotechnological approaches. So I would request this session to be chaired by Dr. M.K. Matthew, and a brief introduction about him. Please come on the dais, sir. So a brief introduction about him. He was trained at IIT Delhi, and then he completed his PhD in molecular biophysics at IISc. And then he moved on to work at University of California, followed by Columbia University, and then at California Institute of Technology before coming and joining NCBS. And there he was the head of the academics for the initial 13 years. And also he was the convener of the board of subjects for biology for 5 years at the TIFR University. So his specialization is on membrane biology, and his interests are in neuroscience and plant physiology. And after retiring, he's been with his broad experience at national and international lab. He's continuing his teaching, and the most blessed are the students or the scholars of ISAR, Tirunananthapuram, and TIFR Hyderabad. So we welcome you and request you to chair the session, sir. So next I would welcome the co-chair, Dr. Veena S. Anil, so who is a professor of biochemistry. She completed her PhD at IISc, and then she was a visiting fellow, TIFR visiting fellow at Dr. Matthew's lab. And then after that, she worked at Monsanto for 3 years as a senior scientist, and now currently she is the professor of biochemistry at UAS Bangalore. And then I also request her to co-chair the session. And I would call upon Dr. Benher Lal, Associate Professor of Biochemistry, to be the rapporteur for this session. And the speakers for this session would be Saudamani, Professor NCBS, who will be speaking about computational biology. And then Dr. Utpal Nath, Professor at IISc. who will be talking about plant development, and Dr. P.V. Shiv Prasad, who is Associate Professor at NCBS, to be speaking about plant epigenetics, and Dr. K.K. Narayanan, CEO of AgriGenome, Bangalore, who will broadly speak about molecular biology. So now the session is open. So I would ask Dr. Matthew to take over and chair the session. Thank you.
Okay, thank you. And we'll get the show on the road. But first, the chairman has a prerogative for 2 minutes to hold forth about life, the universe, and everything. Okay. 25 years is a significant milestone, and it's great to achieve that. But 25 years of accomplishment, which is reflected in posters that I understand are getting put up even as we speak, is even better. So congratulations. Yeah. But I'm reminded of a time closer to 30 years ago when there were a series of essentially interminable meetings which were debating the guidelines for this new department to come up in US, which was to be the Department of Biotechnology. Professor T.K.S. Gowda was there, very much so. And it was chaired by the founder director of NCPS, Ubaid Siddiqui. I happen to be also part of this committee. And a lot of the discussion was on very mundane business like student intake and curriculum and so forth. But really the idea, and this is something very much Ubaid's idea of the committee as a whole, was that the purpose was to get all that was known at the very boundaries of biology and make that available within this department to address issues of agriculture. And the extent to which that has succeeded, and it's an ongoing enterprise, we will see in the course of the next couple of days. Yeah. This inaugural session is very nice because it addresses really a breadth of what we would not have imagined in those days, 30 years ago. Yeah, almost nothing that will be presented in this session was thought of in any great detail at that time, ranging from computational analysis of genes of interest and specifically involved in tolerance, stress tolerance, and looking at the regulatory elements there, which may well become targets for manipulation in due course. We will also see that microRNAs have played an important role in the development, not just of parts of plants, specifically the leaves, but also the plants themselves, the morphology, getting them to stand upright, which has a major role to play in the domestication of rice, for instance. And we will then go on to, we will also look at the application at the laboratory level, where one can make modifications in which genes are expressed or not expressed and to what extent. And this will become increasingly the way in which in the inaugural session we saw that you need to address the issues of productivity of plants in different ways. Our session today has been rearranged a little bit. Instead of ending with the laboratory manipulation, we will start with that to give you a jolt, okay? And KK Narayanan will do that. We'll call you up in due course. Let me list. And after that, we will hear about leaf development from Utpal Nath from IISc, and then go on to Professor Saudamani, who will talk about the computational aspects, and finish with another microRNA talk from Professor Shiv Prasad. Now I will hand over to Professor Veena to introduce our first speaker.
Matthew. So I'll be introducing the speaker. I'll also ask him to please come up. So Dr. K.K. Narayanan, many of you know him here, is an academician turned entrepreneur who is trained as a plant breeder and molecular biologist. Yeah, yes, yeah. He graduated with a PhD from TNAU, Coimbatore, and a postdoctoral program he completed in Stanford University under the Rockefeller Foundation Fellowship. He started his career as a scientist at the SPIC Science Foundation, Chennai, before moving on to lead crop transformation of the Monsanto Research Center in Bangalore. Of course, he started in 2002, he started the famous MetaHelix Life Sciences, and I'm going to cut short a bit in between what you have done. And now he is the director, CEO of the Agri Genome Labs. Dr. Narayanan has been a member of several committees and advisory bodies of the DBT and task forces. He is also a member of the Vision Group of Biotechnology and from Government of Karnataka. He is also a member of the Executive Council of the Association of Biotechnology-led Enterprises, ABLE. And also heads, part of board of some of the leading companies and involved with several government initiatives and to promote entrepreneurship and mentor several startup companies. We're really happy to have you, sir, here, sir. Please, yeah.
Yeah, it's working now. So good afternoon once again. It's always a pleasure coming back to UAS. This time it's more so because I'm getting to meet some people whom I have not met, but have interacted long ago, but I'm meeting now. For example, the chairman of this session, Dr. Matthew. Many, many years ago with my colleague, Dr. George Thomas, was the first time I met him. And when I realized that he has worked in Charles Cantor's lab, I used to use the Cantor developed Chef pulse field gel electrophoresis system for analyzing the rice mitochondrial genome. So I immediately thought I'm seeing somebody whom I have known for some time. Anyway, nice meeting you and nice meeting many other people like TKS Gowda and other people. We used to interact quite well and often till some time ago. So I think in the program, I was given 20 minutes plus 5 minutes for discussion. Since we are running late, I was told that if I can compress it to about 15 minutes. Okay, so I may be rushing through some of these slides. I will be around for some time after my talk, so we can catch up during that time, if it's okay with some of you. So the topic that I have chosen or suggested to me was gene editing for crop improvement. I was on a contract with Agri Genome as a director and CEO, which got ended a few days ago. And it was a one-year contract. And during that time, we did do some things on gene editing. So I am going to share some of that results with some of you. And the major people involved in the bench research in that work are all acknowledged in a paper, the citation of which I will be presenting as we go along. So genome editing, gene editing, I'm sure many of you are aware what it is. That's the new in thing now. You know, genetic modifications, let's focus on crop improvement of crops have been there since the advent of settled agriculture. And deliberate efforts, right from selection to Mendelian use of selection to transgenics, and now it's gene editing. And, it's a method by which you can change specific bases or correct mistakes, specific mistakes in the genome, the book of life. I think that's what in substance gene or genome editing is. And I must say that the methodology, so now it's fashionable to talk about it, and it's become routine in many labs now using the CRISPR-Cas system. I think it's almost 40 years ago that people have tried to attempt making specific changes. And one of the initiatives or initiators of people trying to look at making specific changes was the discovery of many proteins which bind very specifically to certain motifs in the DNA. So if you can, the idea was that if you can tag it along with certain nucleases which can cut and then induce the cell's own machinery to repair that cut, you can create certain deletions, or you can certainly create knockouts. So some of the first attempts, which was, sorry. Why is it not going back? Can you go back? Both the buttons are going forward. Yeah, that's the one. That's the one. Yeah, that's the one. So in the 80s, I think there were discoveries of the zinc finger proteins which bind to DNA. They're called zinc finger because there's a zinc cofactor involved with that protein. And the side chains appear like fingers. So it's a zinc finger protein. And a few of them have been very well characterized as to what their binding motif is, all that. So if you, the first attempts or the first successful attempt of generating genome edits is using this system where a nuclease from Fulvobacterium species was actually engineered. That's a type 2S type of restriction enzyme where it has a recognition site but cuts about 40 or 50 bases downstream of that. And then that was the first system that was employed. Without going into too much detail, I think a few successful events have been reported using zinc finger protein, but still cumbersome. Not every lab could do it. It required, the limitations were many. For example, there were only few zinc finger proteins. Now, to sort out some of those issues in the 90s, people started looking at transcription activators. So transcription activator like enhancer nucleases. So TALENS was the other system that was developed. We all know that there are cis acting elements which are acted upon by transcription factors in the expression of genetic regions. For example, the typical, we have the Tata box in the promoter region where some of the polymerase and the subunits and other things come and bind. Transcription factors initiate the transcription. So those kind of regions specifically bound by these transcription factor-like activators. I think they were again, a similar technology or similar approach was taken. This Fulvobacterium-based nuclease was by then quite common and people were familiar with it. So they actually engineered the same nuclease and which were TALENS were actually developed. And this is a system which is still currently being used by some people, even though it is not as easy or as facile as the CRISPR-Cas system, about which I will be discussing the rest of my talk. So because of the patent issues, IP issues and stuff like that, there are, this is certainly an improvement over the zinc finger-based nucleases, but still has many difficulties because multiple proteins are involved and there are limitations in terms of finding out the sites where these can bind, many issues. So what we are going to talk today is the CRISPR-based system. So clustered, randomly interspersed palindromic repeats. So these are very common sequences in all prokaryotic systems. In fact, they were recognized as early as the 1980s. In fact, Charpentier, who actually got the Nobel Prize along with Jennifer Doudna, for actually devising this system of gene editing using CRISPR-Cas9. Initially started our work in trying to analyze, and people didn't give much thought about it, even though we had sequencing since the 90s of almost, they found these CRISPR sequences, and interspersed between them, they found these spacers, which are inserts of the viral sequences or something. So there was some indication that they are all mechanisms, part of the mechanism to create an immunity against viral infection for the bacterial system. So that was leveraged to develop the CRISPR-Cas9 system. So major the Cas9 is one of the CRISPR associated proteins. In fact, the real breakthrough of the CRISPR-Cas9 editing system is the Cas9 part of it. Let me delve on it a little more about it. Cas9 is a nuclease, or a CRISPR associated protein 9 is a nuclease. The good thing about that, there are many other Cases, because many other CRISPRs are associated with proteins which have nuclease activity. The problems with them are they don't act in a single fashion. They have to be in complexes. There are multiple proteins that need to be activated. They have to be associated with RNA and other things in different ways. Cas9 is very simple in that way. The second important thing is Cas9 is also multifunctional and assembled in a modular fashion. So I sometimes use this analogy of your JCB or the excavator, So if you have a bucket, you can use it to dig pits, whereas you can remove the bucket and put a jackhammer, and then you can use it to demolish things. Or the other end of it, you can, like that. The Cas9 protein has got a nuclease activity in one domain. It has an activation activity in another domain. You can chop off one domain and then introduce nickase or some other activity, which you will see how it has been leveraged to develop the CRISPR-Cas9 and improvements over the original CRISPR-Cas9 editing systems. No, it's not moving at all. Thank you. Anyway, so I think I will use this only as a pointer. You can move it for me. This is the CRISPR RNA, the CRISPR associated proteins, the direct repeats. Without going into too much details, what happens is the CRISPR RNA activates the Cas protein. It creates a nucleus, and there's a guide RNA part of it, which becomes guide to the activated CRISPR protein to actually bring it to the site where the cut has to be made. And if there are certain motifs that are present, and I forgot about it, the Cas proteins need a protospacer associated motif, PAM motif, to actually make the cut at a certain distance from it. The PAM motif for Cas9 is very simple, 3 base pairs. And out of that, 2 of them are redundant. So it could have NEN or something like that. So you can find such protospacer activating associated motifs very easily in the genome. So designing a CRISPR-Cas9 based editing system is much simpler compared to designing something with some of the other Cas proteins. In fact, I want to leave a thought with you. Maybe I'll do it in the end about this Cas protein. Yeah. So when you actually design in the laboratory a CRISPR-based editing system, what is required is 3 components. So one is the editing the template DNA, so which has to be edited. There has to be a RNA, which is a guide for the Cas9, activated Cas9 to bring it to the portion. There has to be a activating RNA, which actually activates the CRISPR Cas9 protein, the nuclease, so that it becomes active. See, you don't want the Cas9 to be active all the time. It's a nature's mechanism by which, only when the CRISPR, trans-CRISPR RNA is expressed and processed into the activating RNA, the Cas9 protein becomes active as a nuclease. Otherwise, it will be chopping the genomes all the while. So that's a natural mechanism. And what you can actually do is you can compress it into a 2-component system by actually co-transcribing the guide RNA part along with the activating part. So that's the interesting part of it. Yeah, if I can have the next slide, please. So this is a classical CRISPR-Cas9 method of gene editing. Now, the initial experiments are the one that is most commonly used is essentially to knock out a function of a gene. So the Cas9 will specifically cleave both the strands at a specific position, and then the cell's inherent DNA repair mechanism will take over in fixing that break. Now, this DNA repair mechanism is error prone. So you will have a good chance of getting either a deletion or an addition. Now, what happens to a reading frame if there's a deletion or an addition of one or a few bases? The reading frame is shifted, and oftentimes the gene function is actually knocked out. So along with this, you need genome sequencing methodologies to identify the correct ones. Many times it may be restored also. You may not get a knockout, but it doesn't mean that the CRISPR has not worked. CRISPR has worked, but it has repaired itself correctly, in which case the gene function will be restored. So that's the classical CRISPR-Cas based system. Now improvements over that, and these are being perfected in different systems as of now, as we talk. I am seeing more and more increasing number of publications in these aspects. One is the base editing. In base editing, it is not based on non-homologous end joining where mistakes are possible. It is based on specific bases which are replaced. For example, C2U changes. So cytidine deaminase. So the Cas9 protein is modified. So the double-stranded breaking function of the nuclease is knocked out. It retains only a nickase function. That is, only one strand is broken. And in addition to that, I don't know if you can see it properly, a cytidine deaminase enzyme is actually incorporated or fused into it. Like you can now take out the bucket from the JCB and now put a jackhammer or some other contraption. You can actually take out some function from the original Cas9 and then introduce a cytidine deaminase enzyme so that it will act on the specific base. And what happens is cytidine is deaminased and it's converted into uracil. Now, initial experiments were not very successful because people found that even though there was conversion, the uracil was again being glycosylated. It was being converted back to cytidine by the, again, cell machinery, which is a repair mechanism. So they have actually introduced one inhibitor for that reverse conversion so that the reaction will proceed in one direction. So these are some ingenious techniques which people have used, and these are being perfected. It's not available off the shelf like you can get reagents for CRISPR-Cas now, but these will take some time before. There are some labs which are specializing in some of these. Now, an further improvement over that is actually prime editing. I think this is different. I want to talk about. Can you go to the next slide, please? Prime editing is an advancement where you can introduce specific base pairs in the region where you have created. See, one way was earlier experiments was actually introducing a template strand. After you knock out or do the double-stranded break and introduce a template strand, hoping that when the repair mechanism happened, the template strand, but that was not very successful. But the real success came when the guide RNA, in addition to the activating region, has got the template also with the edits that you require. So it's a single RNA, and the Cas9 is now fused with with a reverse transcriptase function as well. So the Cas9 will, through the guide RNA's action, will be guided to the region where the action has to take place, and the reverse transcriptase function can take over, use the RNA template, and then reverse transcribe the corrected edited strand. Please go ahead. Next. I will switch gears now and talk to you a little bit about our initial experiments at AgriGenome on editing, demonstration of editing in a crop like tomato. We used a variety called PKM1, Paramagudi 1. And next slide, please. So, we wanted to select obvious traits so that you can easily identify the edited mutant version from the natural version, wild type, if you want to call it that. So one of the thing is tomato's color. The red color is due to a pigment called lycopene. It has got some nutritional value. But this experiment was clearly not to develop a nutritionally enhanced tomato, but to actually demonstrate that specific editing can be done. There is a pro-lycopene conversion to lycopene. There is an enzyme that is pro-lycopene isomerase, which is involved. Now, thankfully, this enzyme is present in one copy in the tomato genome. If we can go forward, this is a big gene. It's got multiple exons and introns, but the exon 1 is relatively large. So we actually designed guide RNAs to create edits or knockouts in the 5' untranslated region, hoping that the transcription itself can be impacted. And of course, mistranslation by actually editing 2 positions in exon 1. So guide RNA 1, 2, and 3. Next slide, please. Next slide, please. I can see it here, but it's not coming there. Oh, it does. Oh, thanks. So now I am taking you ahead by about 1 year. Okay, 1 year of work, 1.5 years of work. This is the results of that. Guide RNA 3. So you can see when lycopene is present, the tomato will be red in color. When the lycopene conversion is inhibited, when it is pro-lycopene, it will have a tangerine color. So I'm not sure if you can see the color difference. So these are all mutants selected out of by sequencing in a specific region, but 2 of them are actually showing the mutant phenotype. So these are number 42 and number 1, but I will just try to explain. I'm not going into all those. 42, what has been the changes that has been made. Please go ahead. So you can see that at this position, there are 2 alleles that has been created in the break repair kind of cycle by treating it with CRISPR-Cas. And you can see that in one of the allele, there's been an A insertion. I'm not sure if you can really see the chromatogram, but you have to believe me. Whereas in the other, there's been a G deletion. Both of them have shifted the reading frame and created premature termination of the expression of this gene, and then leading to accumulation of pro-lycopene compared to lycopene. And that's why, it's tangerine in color. Well, the others have also been analyzed, but I'm not going into the details there. Okay, next slide, please. Next slide, please. I think you skipped a slide, but it's okay. No, it's okay. So I think this is the chromatogram. That's the lycopene peak. And you can see that that's missing in the mutant, whereas the accumulation of the precursor is happening much before that. And these are you can actually visibly see it in the color of it. Next slide. Well, in other respects, I think the plant phenotype is similar. Flower, the sterility, it was also stable over the generations. Next slide. So these are the T2 plants. T0 is the regenerated plant. T1 is the first sexual generation, because the designation has to be clear. This was our designation. T2 is the second generation of selfing. And you can see that it is almost segregating like a Mendelian segregation of a 3:1. And you can, this is again, the color difference is corroborated by the next slide, please. Yeah, by the chromatogram. So these are the people really involved in the work. I think the guy whom I went with to meet Matthew is also here, George Thomas. And I think Bonnie Kuriakos was the leader on the bench. while doing this work. If some of you are interested in looking at more detail, I think this paper is available. Next slide. I think the final segment of my talk, I think gene editing is coming of age. If we can go to the next slide, there are many, many reports of useful products being made. Now, I put this in because this is one of the examples of using, back. Suddenly this has started working. I know it can be weird. So here they have used talents to, and then replicated the same effect with CRISPR-Cas. So bacterial blight resistant rice is a useful trait, but this is not such a useful trait. There are these sweet genes. It's an indirect method for controlling bacterial leaf blight because bacteria can use the sugar and then that promotes the growth. But I'm not sure how important that is. They wanted to find some reason, but what is more important is they actually created edits in the sugar transporter sequence. But this was done in the pre-CRISPR days using talents. Next one, please. This is a very important work because high GABA tomato is the first commercial gene edited crop that's available in the world. And which country commercialized it? Japan. Japan, which is very careful about gene editing of this one. They were the first ones to commercialize it. I think that was probably the inspiration for our own government to actually relax some of the rules that we have. The onerous conditions were actually relaxed for SGN1 and SGN2. Here, GABA, gamma aminobutyric acid, is a nutraceutical. It is produced in tomato, but the gene that converts glutamic acid to GABA, in that pathway, the gene itself has got in the carboxy terminus, there are certain domains which actually inhibit the overaccumulation. So as the tomato fruit ripens, the levels of GABA comes down. So in these fruits, what they did was they have edited those sequences so that it no longer inhibits or there is no self-limitation of the accumulation of GABA. And it's a very interesting paper. I think you should look at it to understand the logic of what they did. And so this is now sold by a company called Sanatech. So I think some Rouge is the name of the tomato that they sell. I believe it's a very expensive tomato and in great demand. A seed of it costs about $5 or something in US dollar terms. If I can go to the next slide. Well, I think we all know about domestication, and now with the omics technologies, whether it is the evolution of maize or tomato from Solanum pimpinellifolium, we know how many genes have been altered, whether it is Zea mays, parviglumis, or Thiosynthe to maize, how many genes have been modified to actually create the edible or the cultivated maize of today, either in their structure or in their expression. But today we know that many of those changes are only incidental because it happened through, but then the crucial genes which actually created the change could be 4 or 5. So they have discovered that in tomato from Solanum pimpinellifolium, or now it's called Lycopersicon pimpinellifolium, to Lycopersicon esculentum, which is the cultivated tomato today, 6 genes are crucial for making the changes, that is reducing the solanin content so that it becomes less toxic, for increasing the size of the tomato, to make it sweeter, to increase the TSS and stuff like that. And by gene editing, these 6 genes loci have been actually modified to make it the cultivated or the Lycopersicon esculentum type. So this is forced evolution in a much shorter period of time and making only the changes. See, what often happens is when you make these gross changes in nature, while the fruit may become bigger, it may lose certain properties like disease resistance or pest resistance of the wild form. So in this way of forced evolution, you can retain those traits while actually getting the changes that you require for human consumption. Next slide, please. So this is a hot and There you go. So I've come to my last or penultimate slide. This is a very interesting area of research. The previous slide, please. Because I'm sure there are some budding entrepreneurs here, and I want to make a pitch about how we can be job creators rather than always job seekers. So CRISPR-Cas is a hot area or a sexy area of research today. Okay, lot of things can potential. It has got great potential. Like Norman Borlaug once famously said, you can have potential, but you can't eat it. Somebody has to work towards actually realizing or manifesting that potential. And that's where some of you can actually contribute as entrepreneurs. In fact, I want to list, these are a few companies which have raised over $500 million in venture funding globally. In India also, many companies have raised funding, but not at this scale. In fact, some of them are what they call as unicorns. And some of them are working on, I don't know if you have heard about it, non-browning potatoes, polyphenol oxidase, which actually oxidizes and then creates brown color in the potato. They knocked out that function, and non-browning potatoes. Potato, when you fry it, there is a possibility of creating acrylamide. So some of them by knocking out specific genes. Similarly, there's great potential today with climate change and other things. There are things that you can actually manipulate without going through the entire gamut of transgenic technologies and regulatory systems. You can develop it. So this is a good area for entrepreneurship. I would encourage some of you to actually look at some of these details and then work out specific. And even in refining some of these techniques, if you develop a good platform for base editing or gene editing, or I mentioned to you, I'm going to tell you something about Cas9. Cas9, why should we be dependent on Cas9? Because when everybody asks, what is the IP situation? Yeah, IP situation is pretty complex. Today, we don't know who owns it. California and Broad Institute had a fight. And now the latest decision is that California Institute doesn't own it, but it's Broad Institute. So many people who licensed it from California Institute, Jennifer Doudna, they don't know what to do. They have paid the money. And Broad Institute, so it's a mess. We have so much of bacterial or microbial collection around us. Why don't some of us take it upon us? Of course, it's a lot of grunge work. Let me be very clear about it. Nothing without pain. Why don't we take it upon ourselves to find out whether we can find another? Most of the IP around this CRISPR-Cas9 is around the Cas9 protein and its ability and the characterization and stuff like that. Can we find another Cas protein, CRISPR-associated protein from some other organism, which may have similar properties, and then not worry about licensing or in-licensing or Broad Institute or the cases that goes on around it? So that's where I want to leave you. Next slide, please. So there is also work in agrigenome on rice. We have worked on the starch branching enzyme. So I just put this slide to suggest to you that there is more to CRISPR-Cas than just tomato and PKM1. Thank you very much. Thank you.
Thank you. And I think we have time for just 2 questions. Shiva.
You can have the lights now. Well, I would think that in a few generations, the fruit size would come back. There is always this lingering effect of tissue culture and some probing and poking that you do on the tomato. In fact, I cannot find a logical reason to think why lycopene content would impact the fruit size, unless there is some other pathway or something else also that is being affected. We have not extensively scanned the genome to figure out whether there's been any non-intended effect or something like that. Unlikely with the limited sequencing that we have done. So I think the little fruit size that you need, because everywhere the scale is also not given. So don't judge by just the pictures that you see.
Okay, another question, last question.
So thank you for your wonderful
Sorry, I
presentation.
had to really rush, and in spite of that, I overshot by some minutes, I think.
Thank you for your wonderful presentation on genome editing. I have a question. See, if you mute some genes, how will be the related effect on the plant? And also where you are targeted, both the upstream regulatory region or exon, in combination or separately?
Well, if you mute some genes, what will be the impact on other genes? In some cases, it's very well known. If it's a gene which is involved as a transcription factor or something like that, there will be pleiotropic effects. There will be multiple genes which are influenced in their expression. But certain genes may not have that much of an influence over the other genes. Now, giving a general answer may not be appropriate in a scientific forum like this. It has to be dealt with in a case-to-case basis and based on research and studies that has been done. So I rest my case on that. What was the second part of your question?
The editing is a separate event. In your case, you have presented one case study, edited at upstream regulatory 5' upstream regulatory sequences and also exon, whether it is separate or both the places been edited?
They say depending on the guide RNA you use, your target region for editing is different. So we used 3 target regions. One was the 5' and 5' upstream regulatory region, and 2 in the exon regions. One is towards the 5' end of the exon 1, one towards the 3' end of the exon 1. In the cases where we actually saw a phenotype, we saw genotypes in all the things. But to get a phenotype, you should have either disruption of the expression of that enzyme. So to see the phenotype, we had 2 instances. One was 42, even number 42, which I mentioned to you, where we had a phenotype that was in exon 1.
Okay, I think we'll have to stop at this stage, although I'm sure there are a large number of questions. I myself have several. So if we have the time, we'll have a chat.
Sure.
Yeah. But I think we now have to thank Dr. Narayanan for that stimulating talk.
Thank you, Dr. K.K. Narayanan. So I would like to ask Dr. Matthew to hand over a token of appreciation as a memento to Dr. K.K. Narayanan.
So we'll have the next speaker, Dr. Utpal Nath from IISc.
So I'll call Dr. Utpal on stage now. Dr. Utpal Nath is a professor at the Department of Microbiology and Cell Biology, Indian Institute of Science. He completed his MSc at TNAU. He's actually an agriculture graduate. And then he followed that up with a PhD in protein folding at NCBS TIFR Center, Bangalore. He completed his postdoctoral fellowship on leaf morphogenesis in plants at the John Ean Center, Norwich, UK. Dr. Utpal Nath's research interests are on developmental aspect of plant organ and size and the molecular basis of early events of plant development such as patterning, meristem, and specifying organ identity. He is the recipient of the R.B. Ekbote Prize, Maharashtra Association for Cultivation of Science in 2016. He is a fellow of the National Academy of Science, India. He is a fellow of the Indian Academy of Science and a fellow of the Indian National Science Academy. Dr. Utpal?
Yeah. Okay, I'll get started. Yeah, thank you. Congratulations to the department for completing 25 years and the people who actually made it and sustaining. And special thanks to Dr. Veena Anil, who is a friend of mine, for calling me. If you can't hear me properly, I will open my mask. And if you still can't hear properly, open your mask. Right. So I'm going to talk about some problem which plant faces. I mean, we keep facing problems throughout the day and our life all the time, but they also face it.
during the development, especially when a very small, unsuspecting, simple leaf like this faces problem of growth. So I have named it like this, and this essentially, explains what I'm going to talk about. And so so this is the question that I want to ask: that a leaf at maturity has certain shape and size, and that is very specific to the species that we are talking about. This is an Antirrhinum majus mature leaf, and this is the shape of the size. My question is that how this leaf attains this shape and size. The talk that I'm going to, we are going to discuss now may not be very useful for the, the agricultural point of view, but who knows? I find it interesting. So the question is that how it attains the size of the shape and the shape. Now, this is the final product of it. You have to see where it started and how it took the entire path of growth, right? If I take an early leaf, this is how it started. Do you see this? This is a 2 millimeter long leaf. This is a 70 millimeter, this is maturity. If I take this as starting point from here to here, my question is that how does it travel this path? How does it grow? So you take a photograph, like when a baby grows, you take a photograph every year, arrange them. You will know how a baby grew. This is something like that as a baby leaf, how it grows. You took a photograph at different time points. The length is given here. You see nothing much changes except size, right? If you take this one, this shape of this one, early leaf, is pretty similar to the shape of a mature leaf. Put them together, and this is how it looks like. This is a small leaf, this is a big leaf. Looks pretty similar. Shape doesn't change, size increases. The question that you ask is how does this small size goes to a big size, right? Each region looks very similar. It looks homogeneous field, right? How does it expand? If you want to know, because there is no molecular marker, or there is no morphological marker that you can see, you can introduce morphological markers. If you look at the sky, you can see the star, right? And if the universe is expanding, the stars go away from each other. This is how it was found that the universe is expanding. Here, there are no stars here. Suppose this is the sky. How do you know the sky is expanding? Put some artificial star there, right? If you put some artificial star, which is not coming, hello star. So, yeah. So, yeah, anyway. Never mind. So these, if you put some stars, right? And the stars don't go away from each other. They stay there. If the space in between, interstellar space on a leaf, if it expands uniformly, then this will be the distribution of the stars, right? Which is correct. This is very simple experiment. However, I can argue that I can argue that the leaf is not growing uniformly. The leaf is growing only from the periphery here. The internal region is not growing at all. Even then, you can achieve this shape, this size. Isn't that correct? Now, what will happen if that is correct, that it is growing only from the periphery and not throughout the leaf? These spots will stay where they are, right? They will not move because it grew only from the periphery, and this interstellar region that I'm talking about did not move at all. So by doing this simple experiment, which I have spoken at least by now several times in this campus and in NCBS, you probably know, so what happens actually? How does the leaf grow? So you do the experiment. You take a leaf, a tiny, nice leaf, still stuck to the plant. Go to the microscope, take some favorite colors, put some dots, put the plant back into the growth room and see what is the fate of this leaf or of these dots when it matures. The same leaf, when it matures, this is how it looks, okay? Something is unstable. So not me, internet, okay. So just clarify. So this is the mature leaf, okay? So now, where are the dots? So these are the dots that we had put this along the line. And this is the fate of the dots here, right? Okay. This is the lag, no? I think there's a time lag. Okay, so I won't press too many times. So see, these are the dots. These dots from all the way from here to here, but all these dots have been collected only from the top half. What does it mean, right? All these dots which is throughout is only collected towards the top half. Remember, the cells do not migrate in plant. They stay where they are, unlike animals. Much easier to work. So that it means that this small region where there are no dots has given rise to this half of the leaf, right? You see these dots are far away from each other, but these dots are close together. What does it mean? It means that the maximum growth here and minimum growth here. This leaf is not growing uniformly, right? So none of the things that what I said before actually happened. Neither like that, nor like that. No, it happens a very new way, which is called vesicular growth. These are not included in my 15 minutes. Huh? Okay, so this is what it is. Yeah. So that means that there's a growth gradient. There's maximum growth here. There's a minimum growth here. Right? And the growth usually is fueled by the cell division. So that means the cells here should behave very differently from the cells here, right? This is the young region, baby region of the leaf. This is the mature region of the leaf. So you see how the cells look. You see dividing cell, tiny, small cells, mature cells, which is already the stomata are already made, differentiated. And these are cells which are in between, stomata is being made. So there's a gradient of maximum growth, minimum growth. There's a ultra gradient of differentiation, maximum differentiation, minimum differentiation, right? You look at a leaf, you don't know so many things different things are going on here. And see, if you do a reporter gene analysis, you all know what is Gus reporter gene analysis. This is a cell division marker, right? Which is a B cyclin. See, maximum cell division is going on here. That's why maximum cyclin here, and there's no cyclin here. My question here now is, you want to ask a question? Huh? Huh. Oh, I should speak on this. Okay, fine. All right. So now my question is that in how this field, apparently homogeneous field, is divided into two domains or two zones. One is the proliferating zone, one is the differentiated zone. Now, not that there is a sharp boundary in between, but doesn't matter, right? Now, this leaf is still growing. If it grew more, this is 3,200 micron long. Now on, I'll only talk about micron. And this, when it grew, the boundary came down. That is okay. When it grew, when it's earlier, it didn't grow that much, 1,200 micron. The boundary is here. Boundary is moving. Doesn't matter. My question is how. So that means that initially, when the leaf is even younger, the whole leaf was growing, right? Throughout the leaf, the cells are dividing. If you have a small leaf where everything is growing and dividing, how is it being divided into one differentiated one, this one? The question is that how you divide a homogeneous field into two different heterogeneous domains. That is the art of dividing. Not a very nice thing. We should be, we should have unity, but I'm talking about how we divide. If you want to know what happens in a very early leaf, look at an Arabidopsis plant very early on. This is where the leaves are being initiated. Shoot apical meristem. You're seeing the top view here, right? And if you take a scanning electron micrograph, this is what it looks like. These are the leaves. These are the leaves being initiated. And this is the meristem, right? Which is never get converted into anything. Those are stem cells. Now, this is a leaf. How that grows. If you take this, dissect this, this is the cartoons that actually the leaf photograph which is made to cartoon. This is the pseudoapical meristem, and these are the leaf being initiated. These are the micron. This is the length of the leaf, 75 micron, 150 micron, 250 micron. The leaf, the photograph that I showed you here, you thought that is very early leaf. Huh? This is already quite mature. So what you want to know, what is happening here? These are the regions where the entire leaf is dividing. All the cells are dividing, homogeneous field, how it is divided into two. Now, if you want to know how a homogeneous field is divided into two, this is the homogeneous, suppose, and this is the heterogeneous, you have to come up with some hypothesis, right? So one hypothesis is this, see whether it works or not. This is a homogeneous field, everything is growing, everything is dividing. And you surmise that there is a factor called it will come. Excuse me. Yeah. So there is a protein G which is expressed everywhere. Everything is growing. So there is no problem. It's a homogeneous field. The question is how it is divided into this one. You can do that. What you can do this is imagine that there is another factor which is R, which is expressed only in one region, and you have got divided into two. But that is not good enough, because both G and R is there. So growth is happening. So remember, R is stopping the growth, right? So that means the growth will reduce, but it won't stop. How will you divide discrete domain? Now introduce one more thing. Tell R that you hate G. The moment R starts hating G, the G will disappear. Right? This is the hating. Huh? If you didn't know the hating signal. This is now it is only R. So this entire region, there is no growth factor. It is only stopping of the growth, only R. We have already divided it. Because it is not growing at all, now you have a strong, growth differentiation zone or growth stopping, and the growth continues here. You have already divided this one. So what is the molecular mechanism that I've spoken about? One gene promotes growth, and another gene which hates that growth promoting protein that inhibits it in certain region, right? So G is, so now you have divided. So this hates it, and you can maintain a boundary. Of course, you can do that. Look at what is happening in the western front of India. The boundary is very sharp. We hate each other. So yeah. So by instilling hate into one group of molecules, you can divide a whole country. We have done that in 1947. Anyway, so there are molecules which behaves like G, like this microRNA. There are molecules, so this is promotes growth. It's a growth promoting microRNA. It's known. I mean, we haven't isolated this. There is a transcription factor which is expressed here, and it is known that this transcription factor suppresses one. And look at the expression pattern. So nice. It is only here and only here. Interestingly, this microRNA suppresses, degrades this transcript. So this one hates this one, right? Now, so now does it mean that it is actually this microRNA and this is G and this is my R that I'm talking about? I'm more or less explained the problem, and I can stop here, no problem. So this is known that this microRNA inhibits this one. I told you, right? MicroRNA should degrade a transcript, and this is its target. How do you, so I told you that if you hate each other, I hate you, you hate me. We are already divided the room into two different domains, right? So does it mean that this transcription factor also hates this? Then you can maintain a nice boundary between the two. You can divide this homogeneous field into two heterogeneous fields. This is already known that microRNA inhibits TCP. People have shown that this is a wild type leaf. When you microRNA overexpress, it becomes much bigger because the TCP is gone. Okay, that is known. Now, what I am hypothesizing is that TCP also inhibits this one, microRNA, in this domain. Mutual hate, you can divide into two. This is called double negative feedback loop. I hate you, you hate me. You can divide an area into two domains, or you can divide an area into two different time zones. Okay. So how do I test it? If you reduce TCP, then microRNA green domain should increase, right? If you increase the TCP, then green domain will reduce. It's possible to do it by genetic manipulation. And how we do the manipulation is not important. Techniques are not that important at this point, at least. So this is what we did. So this is, I want to study what happens. So this is a homogeneous field. You are divided into two and see what is happening here. At a very early stage of leaf growth, this is the meristeme and these are the leaf, 75 micron long leaf. This is a 50 micron long leaf. MicroRNA is everywhere. So division has not happened here. So initially, the growth promoting factor, which is microRNA, is everywhere. What happens later on? You dissect it and take photograph. You see microRNA everywhere, 50 micron long leaf, 85 still everywhere, 120 suddenly disappears. 50% there is no microRNA. Why is not there? Why is it not being maintained here? 150 micron long leaf that is totally cleared off. 50% is cleared off, right? Now, see, is it TCP is expressed here? My hypothesis is that TCP transcription factor is hating this one, is inhibiting this one. How does the TCP is expressed? So what we did is we made it to binary, not very difficult in ImageJ, and then measure this much and this much, and then plot it, right? How do you plot it? This is, it has gone beyond the field. Anyway, this is the leaf length, okay? And this is the, how much is the microRNA is expressed. So this dot means the leaf is this micron long, which is the x-axis disappeared from here. And this y-axis means, okay, I'm done. I'm done rather. So y-axis means that this is the express domain. Okay, you do that for many leaves, and this is how it looks like. So this is the leaf length, and this is the gas domain. So you see, initially 100% gas domain when the leaf is in this, and suddenly it comes down to 50%. It's a real drop. It's a free fall, that you do sometimes when you do a bungee jump. So sudden drop. So that means it's a two-state process. Either there is 100% miRNA or there's 50% miRNA. Of course, it keeps on decreasing after that. That's a different kinetics. What happens in the TCP? TCP protein is expressed initially here at the, so not there. This is microRNA is there, no TCP. It started receding, TCP starts appearing here. So this is protein, and this is TCP mRNA or promoter activity. Not there, little bit is there, protein is not there. But so whenever the TCP promoter is active in the distal region and protein is expressed, microRNA is gone. So that probably that it is the TCP protein that is hating the microRNA. MicroRNA hated TCP initially anyway. Something else turns on the TCP. So is this 15 minutes or is it 20 minutes over and the ding dong happened? 15. Okay, so do I have another 2-3 minutes? 5 minutes. I'll very quickly go through because rest of stuff is very boring, not important at all. Once 50% of a scientific investigation is raising the question and explaining it. Rest is not very important. So this is the so when the microRNA domain is falling down, you see TCP initially is here and suddenly it is here. So the same thing we did. We measured where the TCP is from here to here. So here it is 50%, and then it keeps on going down and so on and so forth. You see, initially there is zero TCP, no TCP here, and then suddenly TCP appears here in 50%. So one domain where all microRNA, no TCP, suddenly gets divided into 50% TCP, 50% microRNA. This can happen by this mutual hate or the double negative feedback loop I'm talking about. And later on, it has some other kinetics, as I told you, but that's not important here. I want to concentrate on the initial part. How does this is what, so if the TCP is actually hating this one, then reduce TCP and increase TCP activity, I told you before, and that can be done by genetics. This is wild type. This is where microRNA is. Mutate TCPs. This is the TCP mutant, 3 of them. You see, microRNA domain has been extended distally towards that. No? It is increased. Increased TCP, it has come down. In the wild type, I have increased TCP, it has come down. You see this quantification. This is in the wild type background. Less TCP, it goes up. And increase the TCP, it goes down. Increase the TCP in the mutant background, it goes down. So whenever TCP is less, microRNA gets extended towards the distal region. When TCP is more, it comes down. So it is doing it. Indirectly or directly, we don't know, but it is doing it. So that means it is done by the TCP only. Just forget that. And how does it do it? TCP is a transcription factor. It's a DNA binding transcription factor. So we analyze the upstream region of the TCP and then see, I'll just come down here. So this is the microRNA and this is the upstream region. This is the whole locus. Okay, this is the upstream region. And we already knew from our earlier work that TCP binds to this sequence. So we scanned this long region to 2.3 kb region, and there are discrete regions where this motif is there, where TCP potentially can bind. So we tested that. Does TCP bind here? This is called electrophoretic mobility shift assay, or EMSA. Some of you may know. What you do is you make a small DNA corresponding to this region where TCP, you think TCP will bind, right? This sequence is there. And you add some radioactive, something there, phosphorus or something, and run in a gel. Okay, I'll just put the whole thing here. Yeah, run in a gel. This is the one. Only, the DNA oligo, it runs here. Okay, no problem. Do the same thing, but add some TCP protein. You see, it is now the band is here because now the DNA can't move because protein is sitting there. It's not letting it move. So it has moved only this much. And then, you can add competitor and all to show it is specific binding. Basically, this is to show that in vitro, TCP protein can bind to this DNA, right? And probably it is, that's how it is hating it, or it is, and it can bind in the yeast also. This is yeast 1 hybrid assay. In the yeast, you put TCP binding site and then microRNA promoter, and you have some sort of reporter gene. And if TCP binds here, in the histidine negative background, it will express whatever it is. It doesn't matter. So, the East 1 hybrid test also shows that TCP protein can bind to this one. I told you that this microRNA hates TCP, and now it looks like that the TCP also hates it. Okay, so TCP specifically binds to this upstream region, and by chip also, chromatin immunoprecipitation. This is what I showed. EMSA is the in vitro. In the test tube, who cares what is happening? What happens in the organism, that is in the plant. So in the plant, whether some protein is binding to the DNA or not, you do by chip experiment. And this, if taller this building is, that means it is binding, okay, the protein. So the TCP is binding in this R1 region here, but is not binding in this region. So TCP binds here. In plant, I'm talking about, in the plant nucleus. And what is doing it? What is it doing? What is doing is that some sort of methylation, which is an inhibitory mark, okay? So it is introducing methylation, this histone 3K27Me3 mark in this region, this R4, R5, somewhere here. So TCP is binding here and increasing the methylation mark in this region. These are all known negative marks, which inhibits, represses the activity of this locus. So done. I'm finished. I have finished, sorry, not I am finished. What happens is, initially you have a homogeneous field. Everywhere there is growth because no TCP, only microRNA. MicroRNA promotes growth. Suddenly, somebody turns on TCP in this region. Not only that TCP, somebody, X factor, turns on in this region, which is not known, but TCP ensures that microRNA is excluded from this region by suppressing the microRNA promoter activity. I will stop here. I just want to tell you that you can divide a homogeneous field by a double negative feedback loop. It's possible. So don't learn from molecules. Not good.
Okay, a couple of questions. Yes, no, at the back.
Hello. Hey, good afternoon, sir.
Yeah.
Sir, I have this question that that means that TCP and this RNA promoter, they are interlinked. And do you mean to say that the small size of the link, small size of the leaf, sorry, maybe due to the increased TCP when the leaves are small in size?
Yes, yes.
Size
So
of the leaf is linked with
that
the
is true, because when you remove TCP, the leaves are bigger.
bigger.
TCP loss of function, the leaves are at least double the size.
Right, sir.
Yeah.
So that do you think that the role of this TCP would be able to control the tumors in leaf? I mean, the introduction of this TCP.
I got what you were saying. Tumor, cancer, those are the things. Torch. Tumor, cancer, those are the things which is happens in a mature organ or organism, right? It's an aberration. I'm talking about a developmental growth, not tumor growth. So in plant, tumor happens, we don't know. But it's definitely suppresses development-related cell proliferation. Only that much I can say. Interestingly, later on in mature plant, there is some microorganism called what is that bacterial-like microorganism that doesn't have cell wall? Mycoplasma, thank you, phytoplasma. So in fact, the phytoplasma, when it infects plant, the phytoplasma protein called SAP1, it interacts TCP and degrades it. And now we start seeing there is more growth. So yes, TCP is also used by microorganism to modulate the growth, but that at a later stage, mature stage. I'm talking about normal development. TCP suppresses development regulated proliferation. I will, yeah. More than that, it will be
second question.
stretching too fast, too far. Yeah.
Dr. Nath, it was an interesting talk. So I just want to know whether this mechanism is also conserved in flower development.
good point. In flower development, see, I'm talking about only growth, right? Not pattern formation. The petals only grow from the tip. That is known already. All the petals that is known till now, the growth is not at the base, at the tip.
Right.
Whether TCP actually regulates that or not, I don't know. But there is somebody who has isolated a mutant where the TCP is resistant to this microRNA. In arabidopsis, I'm talking about. And that has a different petal shape.
And
so yes, it regulates the petal growth as well.
And is this conserved in all the plants?
Sorry?
These two genes, are they conserved in all the plants?
These two, starting from Physkomitrella, Markantia, all the way to Arabidopsis.
Okay.
MicroRNA is also there. TCPs are also there. Interestingly, in my Markantia or Physkomitrella, I forget, the TCPs are not targeted by microRNA. So the link is not there. So maybe that thing doesn't work in algae, a moss, but it later probably it was a developmental innovation in higher plants.
Thank you.
Okay, I think we'll stop here.
Yeah.
Because we're running rather late, and we'll thank Utpal. I wish we had more time, because that was a really fascinating talk, and there was a lot which he had to skip through, but
yeah, as I said, those are boring stuff, so it's okay.
boring is in the eyes or the ears of the beholder, so to speak. Yeah. So I thank you very much.
Thanks, Matthew. And by the way, 50% of the speakers in this session are from TNAU. I'm also from TNAU. So I didn't know that Narayan is also from TNAU. Yeah.
So thank you. We would not look the leaf at the same way like we used to see. So, yeah, and I would do like Dr. Matthew to do the honors. Thank you.
We'll welcome our next speaker, Professor Saudamini from NCBS.
Okay, I call Dr. Saudamini on stage. Saudamini is a senior professor at the National Center for Biological Sciences. She joined NCBS in 1998. She received her basic degree and master's in chemistry. Her PhD from IASC was on the modeling and analysis of disulfide bonds in proteins. She worked on fold prediction and protein domains during a postdoctoral tenure, first in Birkbeck College, London, and later in University of Cambridge. Her research interests of Dr. Saudamini's laboratory at NCBS has been in analysis of protein structural similarity and distance relationship among proteins. Her group has interest in protein-protein interaction, protein-ligand interaction, and in plant genomics. Saudamini was a Wellcome Trust Senior Research Fellow and DBT Career Fellow. She is a Fellow of the Indian National Science Association and Indian Academy of Sciences. She holds the J.C. Bose Fellowship. Dr. Saudamini.
Thank you. Thank you, Veena. And thanks to all the organizers who have considered me to also talk in this session. It turns out, like Utpal said, that I'm also a tiny bit connected to TNAU because we have an MOU with that. Yeah. So today I'm going to share some of our long-term interests on plant stress management and how we have tried to understand this from the computational perspective. So what we have in here is a little bit of time that we can spend thinking about how plants deal with stress. And for this, we consider a typical time spent by plant in the field. And here, yeah, so the plants are constantly under different types of stress: sunlight, UV, and then the heat, cold, salinity, whatever, and then there could also be biotic stress. So it's not able to move away from it, right? So it has to just deal with it in such sometimes harsh environments. But the good news is that they are endowed with some molecular strategies by which the plant can manage this stress. So what has been hypothesized? What is actually well known is that plants use some of their transcription factors whenever they are subject to the particular type of stress. So these transcription factors are not only required for the upregulation of genes in general scenario, in a constitutive condition, whether it gets translationally modified or not, such genes are also prepared or expressed then and there and enabled by the transcription factors. Okay, so this being the case, we then asked a question. Since there are many stress-specific transcription factors in the plant genomes and their binding sites upstream of the genes are rather well understood computationally, if we create a hidden Markov model of the accepted binding sites and then line them up, and then when you have genes of interest, which we know are stress upregulated, we could ask the question, which of these transcription factor binding sites as already encoded in the hidden Markov models are observed upstream of the genes. And when we do this, we assign scores. So then we know how good these nucleotide stretches are to the genes of our interest in comparison to the known binding site patterns for the transcription factors. And in doing that, we can also realize and compare with a regular scenario, that is that of a constitutive gene, which is shown on the left-hand side, and what is shown for a stress upregulated gene. Now we have applied our algorithm, which we call as STIF-AL, and we see that the stress upregulated genes have twice as many helpers, namely the transcription factors, going by this algorithm. It's almost like, you know, you go walking past people and they hardly notice you on a regular day. But imagine if I fall down, there are people who gather from nowhere, and then some of them might offer me a cup of water. And if I'm badly injured, some of them may even bundle me and then take me to your hospital. So unlike what Utpal was saying, it's not about hate here. It's about some kind of a transient love for a practical reason, right? So these transcription factors are out there to help the plants to enable the production of certain genes. And this might happen in twice the frequency as that happens in a regular scenario. So do these transcription factors have a spontaneous response? Or are there any master transcription factors which are nowhere near the site, but already dictating these transcription factors to just go upstream and bind to the stress upregulated genes? These are aspects that would definitely help the farmers, because if we understand this, then maybe we can include master transcription factors. And some of these sort of questions have been addressed in Dr. Shiva Prasad's lab. I don't know whether he will talk about it today, but their group has done some very excellent work on master transcription factors. However, as bioinformaticians, we like to learn device rules and apply these as guidelines for a predictive purpose. And for us, it's very important to have statistically significant numbers to do this. So all this sort of sweet data can be grown up, and we have tried to do this by forming, first of all, a database. A database is important, then only we can apply and learn our rules. And for this, we call this a StiffDB, and there's a second version also of the same. And the StiffDB, as the name suggests, is a repository of stress upregulated genes and their transcription factor binding sites, as the example shown before, upstream of the genes of interest. And for this, we collected a number of well-known transcription factors, and then using the Z-score thresholds, we began to include information from all over, like different microarray databases of different sort of stress upregulated genes, of course, in Arabidopsis thaliana, because it is the model organism that has been very well understood. And then we run our stiff algorithm and then try to accumulate and properly organize the data. So the data can be transcription factor centric, in the sense to ask how many of the genes are these factors simultaneously capable of helping. The other question could be somewhat gene centric, where we ask questions such as what is the sort of biological function of the genes that get upregulated? What sort of transcription factor binding sites do we see using this sort of a computational approach? And then we can also ask a little further about the transcription factors and whether a particular gene gets chosen again and again for a variety of stress, like salt stress, dehydration stress, and so on. So this is a gene-centric approach, and already you must be thinking in your mind, all this is fine, this is what Stifal tells us, but what happens in reality? So to ask this sort of a question, we collaborated with Dr. Karaba's group in GKVK. In fact, even the Stifal was a collaboration with GKVK many, many years ago with late Professor Uday Kumar. And when we asked this sort of a question in a system like Mulberry, we decided to go after certain genes that we see are getting upregulated, but their functions are not known. So we devised a computational pipeline which essentially uses a combination of sequence search algorithm and fold prediction tools to then make the best out of the sequence, so that we can begin to predict the structure, which in turn might suggest a few things about the biological function. And so we focused on 3 such genes, and then asked a question: what happens if we were to subject the plant? In this case, this has been infused into nicotina, the tobacco, and then subject to 2 types of stress. One is a salinity stress, another is a oxidative stress. And we find that these 3 genes have a different type of stress response scenario, right? Some of them have significant upregulation. This is the time point, 6 hours, 12 hours, and so on. And these are the 2 types of stress, yeah? And then some of the other gene, on the other hand, is an early stress response gene, and the other one will show up itself in terms of higher gene expression only after 6 hours of subjecting them to stress. This suggests that the gene expression profile is also going to be interestingly different. Not only the fact that you have many transcription factors apparently rushing to the scene to help the plant in upregulating such genes, right? And to address this question, we did something more, which is very, very interesting, I thought, because this is now in collaboration with the group at Ley Bones in Norway. And here, still the system is Arabidopsis thaliana, but we decided to apply, rather the collaborators decided to apply combined stress, which is not only 5 types of stress, cold, heat, and so on, but cold plus heat, light, drought plus some salinity, and so on. So these sort of combinations helped us to discern or better understand what sort of transcription factors come right away, irrespective of the type of stress. And these are like basal stress responsive transcription factors, and what are the factors that would appear only in a very specialized manner, only for cold, only for dehydration, and so on. And this led us to, first of all, recognize that the set of stress upregulated genes themselves include around 250 transcription factors, clearly suggesting that there are master transcription factors out there which recruit different transcription factors to come over to the sites upstream of genes of interest. And then it also helped us to compare or take it through the transcription factor and target gene interactions. And that led us to nearly 10,000 such interactions. And this is a network that kind of shows them all. And you can't see it very well, but the transcription factors are shown in triangles, and the target genes are shown in filled circles. And some of them are upregulated. Occasionally, some genes also get downregulated. And then what we have on the right-hand side is to now only take out a biotic stress response. And we see that here also there are transcription factors, although shown in here. And the next slide will show you in some better detail. And you can see that there are specific transcription factors, and some of them we can recognize. For instance, the WRKY, which is known actually more for cold stress response. But you can see that for this biotic stress, which is applying some flagellin, the plant is already using these factors, and as a result, many of these genes are getting upregulated. So this sort of picture or a computational read-through helps us to understand what sort of transcription factors are vitally required, irrespective of the stress response, and what sort of transcription factors get recruited in a very specialized manner. And it also helps us to understand what are all the primary stress responsive genes, because there are some universal stress responsive genes. So you can do a transcription factor centric analysis or a gene centric analysis. So with this, I would like to really stop, and I would like to acknowledge the people who are involved. And here, what happens, okay, so what we have up here is late Professor Uday Kumar. He's unfortunately not here with us, but induced by the initial motivation from Professor Matthew, I don't know whether he remembers, back in 2004, we had a DBT grant, and then Veena Anil has been throughout there because she would engage and recruit some of the MSc students such as Yarini and Anya, who are in the latest batch, and the many more from GKVK whom we have been fortunate to host. And also our recent collaborations with Dr. Karaba on the Mulberry continues. And these are the people who had collaborated with us on the combined stress in Arabidopsis thaliana. And these are the people from my lab. Shamir and Mahantesha and Uman were the early players in the DB creation and some of the analysis, whereas Shafi and then Sajivan in fact is from GKVK. No, in fact, actually, all those who are from GKVK have tried to put it up in a green box. Just like how Utpal was trying to find a pattern with the TNAU, here I am trying to find a pattern with the GKVK collaborations, which have always been very healthy and strong. So with this, I would stop and take any questions that any of you might have. Thank you.
Okay. We have time for a couple of questions. So, Salami, you pointed out that there are a large number of transcription factors, and many of them seem to be upstream of the same genes.
Yeah.
So how is this now regulated? Because do you have a pattern of the activation, or is it that any one of them activates? Or, you know?
Yeah, in this handful of instances, we know that there are, just like how there are favorite stress-specific transcription factors, there are also genes that are universally upregulated during a variety of stress. So what we have done for a handful of genes is being able to follow. The gene may be the same, but for cold stress, the combination of transcription factors that sit upstream could be different from that of another type of stress. So although the binding sites are all there, it's almost like a genome transcriptome sort of difference. The inscription for a binding site is there, but only certain transcription factors are available, are recruited enough for a type of stress. So that's maybe happening.
Shiva.
Transcription factors, the ones which are related to stress, they have a feedback themselves going repressing compared to others.
Yes, yeah, from this combined stress where we had nearly 10,000 interactions, we were able to identify some which act as repressors. Nearly 1/5 of them, of the interactions, are repressive in nature. Yeah.
Okay. Right, I think we can. Is there one more question at the back?
Thank you for a nice talk. I was just wondering that Arabidopsis itself has thousands of accessions, ecotypes, strains, if we can use that word, that grow in different climatic conditions in different ecosystems. So is there any sense in extending this study to see that whether these accessions will differ in their response to a particular combination of stress?
Yeah, I did not mention it, but even in this analysis which we pursued with the Norway group, 10 different ecotypes were chosen for the Arabidopsis. And in fact, we only looked at the 500 common genes that were universally getting response. We were getting response from all the 10 ecotypes, and only those were taken up for further analysis. So I'm sure there are regional specific some response which will be very interesting and very applicable for farmers to know what sort of genes could be potentially taken forward for a long-term analysis or upregulation so that such plants can survive in harsh conditions. Thank you.
Okay, I think we'll come to an end for this talk. Thank you very much, Sadami. It's enlightened us a fair amount about these rather complicated interactions between regulatory elements, which may not have been entirely obvious before. Thank you.
So we would like to thank you, ma'am. And I am one of the beneficiaries of your lab from Dr. Late Professor Uday Kumar. Thank you. And please accept your token of appreciation.
Okay, we will move on. Our last speaker for this session is Professor Shiv Prasad.
So, Dr. Shiva Prasad, please come on stage. Dr. Shiva Prasad PV obtained his PhD from the Madurai Kamraj University in 2005. This was followed by postdoctoral work at the University of Basel, Switzerland as an EMBO Research Fellow and SNF Postdoctoral Fellowship. He later undertook a second postdoctoral fellowship in the University of Cambridge, UK. He joined the National Center for Biological Sciences in 2013 and currently serves as an associate professor. Dr. Shiv Prasad has extensive research in plant molecular biology and currently works on aspects of small RNAs in rice, grape, and other plant species. He is the recipient of the prestigious EMBO Fellowship and Swiss Society for Psychiatry SSP Award. He is also the recipient of the Sir C.V. Raman Award in 2019, Government of Karnataka. Shiva Prasad.
Good afternoon, everyone. Thank you, Veena, for the introduction and also for inviting me. So I'm going to explore a bit more of this love-hate relationship, so which both Professor Utpal and Professor Saudamini mentioned. So, okay, if you don't get time to ask me questions, you can always contact me here. So title of my talk is Epigenetic and Small RNA Mediated Process in Crop Plants. So we mostly work with all these plants which make many interesting things for us. So this is the pathway that is central to what we do. So it's like the hate pathway you can call. So the central to this is small RNA, one of those Professor Utpal mentioned. It is a microRNA that he mentioned. So these are all tiny small RNAs that cannot make a protein. So they are made in the genome in hundreds and thousands in almost all part of the genome. And these are processed by proteins called dicer-like proteins. So they cut this double-strand RNA to make these small molecules. Once these small molecules are made, they get associated with set of proteins called organelles. And here the hate relationship comes. So small RNA, when it gets associated with the right organelle, it can go and cut this RNA into two. So imagine this is TCP that Professor Utpal mentioned. This is the microRNA 319. So this gets cut into two, and this cut RNA cannot code for any more protein. So though it looks like cumbersome energy wasted process, this is very common. Almost you'll see almost every gene is regulated this way. So in animals, this hate relationship is slightly different. The small RNA binds to the 3' untranslated region and induces translational silencing. That means protein is not made, but RNA is not cut. But why we work with plants, actually why we love plants, is because of sort of this capability. In small RNAs, when they associate with certain organelles, can induce changes in the DNA called epigenetic changes. These are at the level of DNA methylation or histone modifications. This is heritable, almost like a Lamarckian fashion. There are in fact many people who think that Lamarck should have used plants as his favorite animal, favorite organism instead of giraffe. Okay, so we use this. We try to understand all these processes in plants. In the last 9 years or so, we try to find how these small RNAs are made, how they act, and what happens when they regulate when they hit certain set of these proteins. Okay, so let's go back one step back. Why we appreciate plants? Plants give us food, plants give us shelter, they give us medicines and 100 other things which we use whether we knowingly or unknowingly. But why are they making all this? So they're making all this mostly to entertain the animals as a part of a collaboration between plants and animals. So if you look back 100 million years ago, during the time of all these nice dinosaurs, there were no flowering plants. This is when plants thought, let's collaborate with the animals. They started bribing animals with the colorful flowers and nutritious fruits and seeds. And this provided nutritional security for all the animals. They also evolved very nicely, but really dramatic is the evolution of the flowering plants. So even for somebody like very famous people, so you don't see, they can call this evolution as a abominable mystery. And this interaction went on for 100 million years ago. It evolved, helped to evolve all kinds of forms until this balance was broken by this thing. So this is birth of modern agriculture. Here plants targeted us because we knew how to move. We knew how to literally remove everything else from the earth so that we can pamper very few plants. The plants we really pampered are cereals. These produce plenty of grain with very little inputs, and they have very few competitors. So these are also making a lot of carbohydrates. Carbohydrates can stay longer. That means animals who depend on them can live longer. We very happily store it for in the off season and so on. So in this coevolution bargain, there is more grains for us, but dominance in numbers and pampering really goes for the plants, especially some of these rice and probably wheat are the most abundant macroorganisms on earth. So here, if you look at rice, the history of rice, so how exactly rice that we know now has evolved to that form. So the wild relative of rice, which are still found in the edge of lakes, so they are sort of prostrate. They make few leaves, they have this rhizome, and they make a couple of seeds, especially in December, 2-3 seeds, which falls off and starts germinating. But during this last 10,000 years, we have converted them to these plants, which have sturdy stems, many stems, and panicles. Sometimes panicles can be almost a foot long, and these panicles can hold up to 200 to 300 grams of grain per pound. Compare that to wild species. So it's a huge dramatic change, and we don't know how exactly this change was brought about. Now, indica rice that we use predominantly came from Oryza nivara. So most of the Japonica and Javanica rice came from Oryza rubipogan, same as some of the indica rice also came from rubipogan. As I mentioned, these are still found in the edge of the lakes in many parts of, including Karnataka, so you can easily see them, but you might not recognize them. Okay, so now what has changed during domestication of rice? So many, I don't know how many groups are really interested in this topic. So the idea is that if you know what changed, you can sort of make this process better and get better yield, maybe recover some of the lost properties. So obviously one has to go and look into the genome. Genome is archive of every change. But what is surprising is that very few genetic changes have been associated with domestication of any crop. So especially from Rachel Mayer and Purganan work, we know that genetic changes are not proportional to the phenotypic diversity. So this holds good not just for crops, for us as well, except in Africa. If you compare genetic variation in humans, we are almost similar, but we look very different. If you compare to, let's say, orangutan populations, they will show much more genetic variation. So one example of this is this. So we know around 200 yield-related QTLs. So for this campus, you don't need to be introduced to what QTLs are. So these are large unknown regions in the genome that somebody associates with the trait like yield. And in rice, we know 200 yield-related QTLs, but we know only 8 genes. We knew only 8 genes that are associated with the rice seed. So the reason is most of the time people could not find out genetic variation in these regions. So we thought maybe there is something else. The process I mentioned, small RNA and epigenetics might be involved. To do this, we collected rice from different parts of the country. We got 2 wild species. We got land races, which we were all eating until 1970s before we got the Green Revolution. We got 12 high-yielding rice varieties that is from Gene Revolution lines. And we did the extensive phenotyping and selected 12 lines for whole genome analysis. Here we performed, looked at the abundance of small RNA, abundance of large RNA, that is mRNA, looked at the change in the DNA, DNA methylation, and histone modifications, then started asking, what has changed during the domestication? So one example I'm going to give today is largely comes from a very really charismatic, really good PhD student, Shweta Chenna. What she found is that in wild species, you get a lot more 22 nucleotide base small RNA. That is extremely unusual. You don't get to see this in any other plant. Typically in plants, you get a lot of 21 and a lot of 24 nucleotide RNAs. So this is how you expect it, but in wild species, you got more 22. So this you can see in this graph very well. In wild species, or Resinivora, you have a lot more 22 nucleotide reads compared to, let's say, land races and cultivated lines. So now the question was, where is this coming from? Where is this extra bit of lot more abundance of 22 nucleotide comes from? So when she looked into the genome, she found it is in chromosome 2, one single region, which you can see makes 100,000 reads per million. That's really a lot of small RNA coming from one region. Wild species, very high abundance of this small RNA. In cultivated species, almost nothing. And between these 2 markers, we found a new microRNA. So now this new microRNA seems to have been lost. So during domestication, wild species, very high abundance. Rubipogon, somewhat little less than Nivara. Land races, intermediate. And in cultivated species, almost negligible amount of accumulation. So what are the targets of this microRNA? What kind of RNAs this microRNA hits? So the RNA this hits is codes for lactases. So these are very important enzymes. So these come in pathway called phenylpropanide pathway, which starts with phenylalanine. This is a very important secondary metabolite pathway, where we also make colorful substances, anthocyanin, flavonols, and so on. So to convert these monomers of alcohol to polymers of lignin, so this is the second most abundant organic polymer on Earth, you need lactases. Okay, so lactases are the ones which are required for polymerization of lignin, and lignin, as you all know, provides mechanical strength to plants. Now, the microRNA we found, it can target most of the lactases from rice genome. Rice has 24 different lactases. They're all quite different from each other, but even though they are different, they are still targeted by microRNA, because microRNA target site of the 21 nucleotide has a very conserved sequence across these lactases, and this conserved region codes for a peptide called Inaugural, and this peptide is seen only among lactases. So with different molecular techniques, we found that most of these lactases are indeed cut by this or hated by this single microRNA. Now, the result of this is the following. In wild species where you have a lot of expression, high expression of microRNA, the target lactase gene is not expressed or expressed at very low levels, intermediate levels in land races, and very high expression in cultivated rice lines. So the manifestation of this RNA expression is in the accumulation of lignin. Wild species that doesn't have this accumulation of lactase makes less lignin compared to cultivated lines. In stems especially, you can see this by fluoroglycinol staining, low lignification in wild species compared to cultivated lines. So these are glycoproteins that means we could do some biochemistry, we could purify with concanaline columns. And when we did that, again, we could see cultivated species has more abundant expression of these lactases compared to wild species. Now, this is the kind of message we got from this analysis. Wild species has very high accumulation of this small RNA. lacases are targeted very effectively, even though there are many different lacases. Result of this is there is low lignin, plants are prostrate, they have closed panicles, and they experience seed shattering. But during domestication, there is a major change. Now microRNAs don't express, but lacases express, which support high lignin, and plants are sturdy, they are rigid, they can help with grain filling and shatterproofing. So to prove this, we have to bring this microRNA into the cultivated and see whether now the cultivated becomes like the wild species. That's what happened when we express this microRNA in cultivated rice varieties in 2 different backgrounds. And here we have the transgenic lines with the high expression of microRNA, and the plants, they are like shabby, they don't have mechanical strength, and they did not make any seeds. But if you now express this lacase, the enzyme that can make lignification, the plants became sturdy, they grow better, they also made much more seeds than controls. So all it suggested is that this is like a major regulatory module that is involved in rice domestication. So to see why people miss this, we went back to all those 200 QTLs that I mentioned and started mapping all the unknown QTLs. Actually, one of the QTL was found in this campus. When we did that, what we found is that lacase and microRNA, they all map to 26 different QTLs. So if I make sort of a pie chart here, these are all the 200 yield-related QTLs in rice. These are the 8 genes accounting for 20 different QTLs from previous work. And in one go, we found microRNA and lacases. They're all part of missing unknown QTLs. So some of those QTLs you can see have only lacases with them. So we got very good coverage. And in plant cell, this was for 2.5 months. This was the most trending article. Okay, so we do similar stuff with another very interesting plant that is grape. In grape, what we found is that all these colors that you see, whether it's in Bangalore blue or red globe, they are regulated by a microRNA, which has to target set of transcription factors called MIB transcription factors. So the module works like this. During domestication, again, we and animals, many birds, for example, we all like colorful fruits. We selected these more. That's why plants which can make colorful fruits have many more MIPs and many more microRNAs that regulate them. And because of which, if you now have the microRNA, you get the right MIP to activate and make anthocyanins that are the colorful substances. But if there are many plants like this Dil Kush grape, microRNA is not present, you make the repressors to act and they change the pathway, start making flavonols, which are usually not colored substances. So this is another example of coevolution. We selected for these characters and plant responded with this, having this regulation. Okay, so in the last couple of minutes, I'm going to say where we are. So just like in phones, we are in the 4G design breeding stage. So you can read our 1G is really pre-green revolution. So the one which we just passed is the second green revolution, where we used biotechnology, marker-assisted selection, etc. We are in this stage now. We are in the biotechnology, but we use genome editing and design by large data, something like similar what I mentioned. But we are mostly moving towards genome editing, and this is required to feed this population. This is possible only if we develop climate resilient plants. So one of the things we do in the lab, we have done in the lab, is to improve the nitrogen use efficiency. You all know if you add a lot of nitrogen, you're going to get tons and tons of yield. That has happened throughout the world, but there is a problem. Plants cannot take up a lot of nitrate because nitrate has to be taken up through roots, and you need the many different things to come together so that you absorb the right amount of nitrate. So the problem is, when you add a lot of nitrate, it goes out. Plants don't have this efficiency to take them up. In rice, we did some screens with small RNA and large RNA, then started comparing what happens during nitrate stress. We found a small RNA molecule, which is called MIR444, and this 444 goes up under stress, and it can go and regulate one of the genes. It has a hate relationship with one of the gene. That one of the gene we found is MADS27. It is a MADS type transcription factor. And if you express the plants, express this gene in plants, we got a lot more roots, and the plants became very happy. They also made much more yield. And how this worked? So this transcription factor has sort of a transient love in certain part of the genome, around 1,300 such regions in the genome. And this goes and activates set of genes. And there are 3 types of genes where it can go and regulate them. First is nitrate transporter, which help with taking up more nitrate. Second one, it can manage auxin biosynthesis and transport so that there is more roots, there is better absorption. The third and most interesting, probably very unusual thing is it can regulate also many stress responsive genes that are major stress responsive factors, so that when it is expressing, it can also offer stress tolerance. So these plants, so just to summarize, when you have the optimal nitrate, so all these modules are up. That means plant not just make a lot of roots, they can also manage with the stress. If you mess with, for example, if you have less nitrate, now the expression of this gene is reduced, and so is inability to cope with the stress. Okay, so that's where probably I want to stand. Do I have 1 minute? So just to continue the similar theme, so we are also in the CRISPR bus. So we have generated around 12 different CRISPR-Cas9 lines, almost like the SGN1 and 2. And here we found a domestication associated aquaporin, and we generated these lines with many different lines. So these, if you see this picture, you can realize what the change we have done. The plants have more chlorophyll in them. They are sturdy, they don't bend and fall off. Plus, they seems to be having more yield. They also have altered secondary metabolism, such as here you can see accumulation of specific anthocyanins. So I'll stop there. I would like to thank my lab. So I mentioned work of these people here. So this is the current lab members. They all call themselves epipepis, and I never learned why they want to call themselves that. These are 2 of my source of inspiration. David is the one who discovered small RNAs. Professor K. Velthambi is my PhD mentor. And we also have many people like Matthew and Saudamini and Professor Uday Kumar, whom we dedicated one of our papers. So these are all our collaborators, and funding came from DAE through TIFR to us or through one of these grant agencies. Thank you very much for your attention.
We have time for 2 questions.
Thank you. Nice presentation. So I have a couple of questions. However, I will make it a small one. The miRNAs are generally regulated through stress or some environmental factors. So when you targeted lactase with one of the miRNA, whether they are involved from the starting of the seed development to until the maturity?
So first of all, most microRNAs are not associated with stress. They're all mostly developmental checkpoints. So if you want to make a seed to move to germination, you need set of them. From germination to vegetative state, you need some of them. But there are also some microRNAs which go up under stress and mediate some things like the microRNA that we mentioned. So the change is, it happens only in certain stem sections. So you have high expression and low expression of lacases. So, and not in different, or not in all parts. Okay, so the microRNA 397 is well conserved, but it seems to be expressing in different levels in different plants. So somewhat similar relationship we also found in Pimpinellifolium, the tomato, wild tomato that was mentioned in the morning, and cultivated tomato. So there again, production of more stronger plants is very important. This again by our selection. So yeah.
Other question? Question in the back.
What happens to the 22 nucleotide long microRNA in the cultivated varieties? Was that local?
It's lost. It is hardly made. So now we know why exactly it is lost, which I will talk next time. So it's connection to certain growth habits we have done, and the way we started growing the plants, rice in Padu. That's like paddy grown in, irrigated system after preparing the land. This changed accumulation of certain nutrients, and this is actually led to the change in the accumulation of microRNA and in turn in the rigidity of the plants.
So you worked that out as well. So just one, so the fact that it happened to be 22, so that turned out to be a lucky thing because you could identify it, or?
No, we have pipelines to identify anything that looks very different. But 22, that I didn't mention what 22 does is 22 is like one of those, in mythology you have Raktabija, right? You drop off false, it will go and make new. This is what exactly that 22 nucleotide small RNA does. Any 22 nucleotide small RNA in plants is a special thing. It just hit one RNA, but anything that has that Watson-Crick complementarity derived from the first target. So you target one lacase, you get those population of small RNA from that lacase, and these small RNAs can go and regulate other lacases and beyond. So it really works like a very crazy thing. And that's the that's the importance of 22 nucleotides. Actually, very few small RNAs in plants, microRNAs, are 22 nucleotide in length.
I think we'll stop there. Both Saudamini and Shiva will be here over lunch. I think lunch, yeah. And so much more extensive discussions can go on at that point. So at this point, let me say thanks to Shiva for this enlightening talk. And I'm sure that it has set off a lot of inquiries. Shiva.
Thank you. And yeah, I request Dr. Matthew to hand over the token of appreciation. And I request Dr. Veena to hand over the memento to Dr. Matthew for chairing the session. Yeah, thank you, sir. So this brings us to the end of the session 1, and we'll have lunch. The lunch has been arranged at the parking lot of Department of Plant Biotechnology, which is 2 to 5 minutes walk from the auditorium. And the next session will start at around 2:30, 2:35. So please have a quick lunch and assemble back here. Thank you.
Yes. No, yeah, it's now on mute. Yes. So can I share my screen? Can you see my screen? Yeah.
Everything is set.
Yeah, I shared my screen.
Yeah.
Genomics, linking genotype to phenotype, genomics. Further, he has received recognition for outstanding contribution in reviewing in Journal of Ginseng Research and has been awarded with the overall winner award. And he is also a graduate. He is also a member of the Graduate Scholarship for Excellence for Foreign Studies, and at National Seoul University, Korea, and outstanding award he has got from Korean Society of Ginseng, Korea, and graduate scholarship for excellent foreign students, that is again from Seoul National University, Korea. So we welcome you for this talk, sir. So your timings will be 15 minutes plus 5 minutes for question and answer session. Jai Kodi, please.
Yes, yes. Yeah, can you all hear me now?
Yes, yes, we can hear you.
All right, thank you. Okay, so for check, can you all hear me?
Yeah, we can hear.
All right. So you all can see my screen as well, right? Okay, so can someone confirm that you all can see my screen? Yes. I think the chair is muted. I can't hear. Anyway, I think I'll just go ahead. If you cannot hear me, just type it in the chat.
Carry on.
That would be okay. All right. I think finally, after some hiccups, finally I'm able to make it. So it's afternoon in India. So very good afternoon, everyone. Actually, it's my first of all, I would like to thank the organizers and Professor Nagesha for the invitation. And it's also my pleasure to talk in front of our Indian audience. And today I will talk about gene bank genomics, or the title of the talk today is Activation of Plant Genetic Resources for Breeding and Research. I could show one case example from Bali. So the key idea is like the gene banks are holding large genetic resources, which are useful for modern breeding program. But the key question is how these resources can be extracted, or how interesting genotypes or genes can be extracted from the gene bank that can be utilized in modern breeding programs. So that is the key overall theme of this talk. So before I get into the topic, for those of you who don't know where IPK is, this is located in a small village called Kattersleben, which is in central part of Germany. So there are evidences saying that this village is one of the old and early farmers lived here, because the surrounding lands are really good for agriculture. So this is one of the reasons why this institute is located here. And the interesting point here is the institute has one of the largest gene bank, which includes more than 150,000 accessions from over 3,000 species, and they belong to over 700 genus. So if you classify our collections, most of them are cereals, followed by legumes. In cereals, mainly wheat and barley. So you could see more than 10,000 accessions from wheat and barley. So the key question here is you have thousands of accessions from major cereals. So how to find the promising genotypes that can be used in modern breeding program, or how can you mine or extract interesting genes or desirable genes that are associated with certain phenotypes, and how can be utilized in modern breeding programs. So this is the key questions that we often ask. So we address these key questions using a genomic approach. So already we call it, or we coined the term gene bank genomics, meaning that we are characterizing the entire collections that are stored in the gene bank using genomic approach. And in the end, you can have the molecular level passport data. So usually gene banks have passport data that gives the information about the genetic material. But here with the gene bank genomic approach, you can have molecular level passport data to identify its genetic background. So already such studies have been implemented in major crops, for example, rice, maize, even wheat and barley. So here I will show you one example from barley, because barley is one of the major crops around the world. Currently barley cultivation has been going on in different agroclimatic conditions. In IPK, we have more than 20,000 barley accessions that are living in the plant, in the cold room in glass jar. On the right, you can see the plot shows the representation of or these collections. So we could see our gene bank material includes or has a good representation of global diversity. So we wanted to characterize these entire collections using a cost-effective sequencing approach, a so-called genotyping by sequencing. So the overall workflow, we from each accessions, we select single seeds and we grow them in the greenhouse and we extract DNA at the young seedling stage, and then we go for sequencing. So here in each accessions, you have many seeds, that means many genotypes. And from this, we select one seed, that means we work with only one genotype. So from this SNP matrix, you could understand the genetic background or the population structure of these whole collections. So here you could see the principal component analysis of these entire collections. Here you can see the red and blue dots that indicates the distribution of domesticated genotypes versus wild genotypes. And if you closely look at this figure, you could also see some red dots are clustered with blue. That means some of the domesticated accessions are misclassified as wild genotypes. So this is the first example that you could curate the gene bank materials using this kind of genomic data. So for example, they collect the data from different resources and then they just record it based on the conversations, but they don't really understand at the molecular level. But from the genomic data, we were able to curate the gene bank record. And on the right, you can see the distribution of the gene bank material based on the different gene pool or different geographic regions. So in our collections, we have identified 12 subpopulations that are corresponding to different regions of the world. And the second key point that we observed from such a gene bank genomic studies is identification of duplicates. So we receive material from different resources, but we don't know whether we are receiving the same resource or a unique resource. But with the genomic data, we can also identify the genetic background, and based on the genetic identity, you can determine how many are duplicates and how many are unique. So in barley collection, for example, we identified around 33% were duplicates, which is around 8,000 accessions. So this kind of duplicate identification is very important for gene bank management, because if you duplicate, if you propagate or if you maintain the same accessions multiple times, which needs human resource, energy cost, and so on. So you can reduce such a cost if you're able to identify such a duplicate. So overall, this data set really helps to implement efficient gene bank management. So this is for the support of gene bank management. But if you look at the research aspect, from this data set, we could also extract some we can perform some meaningful research, because here we selected based on the single seeds. That means we are making a highly homozygous lines, and that homozygous lines can be used for various phenotypic assays. So in barley, we have generated we have expanded this study from gene bank genomics to pangenome work. So for those of you who don't know what is pangenome is, so pangenome is like selecting the genome that represents the different gene pool. And we are making more comprehensive reference genome so that we are able to capture different classes of genetic variations, both not only SNPs, but all the large structural variations and chromosome rearrangements. So if you want to really catalog multiple classes of genetic variations, so then you have to really sample the wide diversity. So from the barley case, from the 22,000 genotypes, we selected 1,000 genotypes based on the genetic distance, meaning that this 1,000 can represent the diversity of these 20,000. And then from this 1,000, we selected nested core set of core 200 and core 50. And we generated the different level of subset to implement different level of sequencing strategy for our analysis. For example, the 1,000 diverse lines can be sequenced at low coverage for a threefold sequencing coverage. And these data sets are really useful for genome-wide association studies and also population genomic studies. And if you generate 10-fold or even 50-fold coverage for a small data set, this can also be useful to validate the large structural variation as well as genotyping. But with the resequencing data, you cannot really find really large structural variations due to the read size limitations. So we have to depend on the chromosome level genome assemblies. So here we developed we called a discovery panel where we selected a minimum number of accessions. For example, in here we selected 20 diverse Bali accessions. We manually selected the accessions from different edges of the PCA, meaning that they can be represented as they can represent a good diversity. And from these 20 lines, we implemented the first pangenome version in Bali. So we generated chromosomes level genome assemblies for these 20 genotypes. Then we compared them each other, and then we cataloged the large structural variations. For example, here it shows the distribution of presence absence variations that are over 50 base pair in size. So as a summary, we have more than 1 millions of large structural variations. In addition, we also catalog the chromosome rearrangements, for example, inversions. Well, inversions are very important for breeders, especially because if they want to select parents to make crosses, they have to be clear whether they have any conflict regions. For example, if one of the parents have their large inversions and your candidate gene is located here, then you cannot really break these regions because in this large inversion, the recombination is mainly suppressed. So you cannot really break the gene, and you cannot make effective breeding decisions. So breeders are very much interested in having chromosomal inversion or a catalog of inversion as well as translocation for Bali, and such a pangenome studies is really allowing to catalog it. And next, we also demonstrated how this pangenomic or the large structural variations can be associated with phenotypes, because already the emerging evidences are saying that not only SNPs, but also large structural variations are majorly influencing the phenotype, not only in plants, as also in human as well as animal. And in Bali case, we found one interesting event. We identified 16 kb deletions. And this deleted fragments includes a gene, and the genes contribute for the seed hullness in Bali. So in the wild types, you have hulled barley, and the deletion of this gene causes this hullless barley, also called naked barley. So here you see this visible phenotypic difference, just one gene deletions. So this is the one example or demonstration that why do we need more reference genomes? Because single reference genomes cannot capture the diversity, but you need more reference genomes to capture or associate the variation like this. So we already realized the importance of this crop or importance of these pangenomic studies. And so we're now expanding these activities into more genotypes. So we are also expanding our studies into a wild gene pool, because the previous version, we mainly focused on domesticated lines, but now we are also expanding into wild gene pools. Now, currently, we are generating more than 70 genome assemblies to catalog all types of structural variations. And these structural variations will be genotyped in thousands of diverse Bali genotypes. And these markers mainly used to study disease resistance. So for now, currently, we are collaborating with different breeders in Europe, and we are scoring phenotypic related to different diseases. And we already associate these pangenomic variations to diseases, and we identified some casual or structural variations that are associated with this disease resistance. So the next key point is how to mine these valuable alleles, for example, that confer disease resistance, and how to bring this allele into modern breeding programs. So this is another key task, and this is one example from a wheat, but I think the figure looks really complex, but I just give you an overview or overall idea how this can be done. So we have both the elite material as well as the genetic resource. And then we compare the allelic frequency in both or allele proportion in the both panel. And then we mainly look for alleles that are present only in the genetic resource, but not in the wild gene pool. So for example, you have a genetic resistance and then resistant allele present only in the genetic resource that are stored in the gene bank, not in the modern elite gene pool. So we try to target those kind of alleles, and then we transfer them into modern allele pool, and we have already done such things, and currently the field trial activities are going on. So we have also generated a huge data set, but the data set should be accessible to all scientists, including breeders and other researchers. So we have also developed web portals where users can, which is also user friendly. So user can access this portal, and then they can get the SNP data or other structural variant, not structural variant, only the SNP data. And they can check the data distribution, the data of origin, and also we included the phenotypic data related to the particular accessions. So to summarize this whole story in short, the main activities is like we are mobilizing the diversity from the gene bank to modern breeding program. But if you want to mobilize, two steps are very critical. One is characterizing these collections at molecular level. So genomics here play a major role. And next one is we should also do phenotypic data to link the genotype to phenotype. But phenotypic is always bottleneck because we cannot really phenotype thousands of accessions. This is a highly laborious and time consuming, or also cost a lot. But when you have this kind of genotypic data, you can make a subset based on the genetic distance or other measures based on the trait. And this will simplify the phenotyping assay, and we already demonstrated such cases in barley and wheat. So the whole summary of this talk, so conventionally gene bank captures the genetic diversity. It's an original state, like they just keep it wherever they collect it. But in gene bank genomic studies, we are utilizing genomic approach to utilize this diversity in more meaningful way. So for example, from the accession based, we are going forward with the genotypic based on by choosing one single seed. And in barley, we have already generated molecular level passport data for the entire collections that are stored in gene bank. And this data set also allowed us to make subsets for our phenotypic experiments, not only based on the neutral diversity, but also you can make trait customized selections. For example, in the thousands of genotype data, you can choose based on the trait that shows a highly segregated or high diverse variability. And this kind of genotype and phenotype data help us to understand the relationship between genotype to certain phenotype. And this also allowed us to identify the potential novel alleles that can be used in modern crop improvement programs. All right, so this is the overall summary of the talk. And finally, I would like to acknowledge people who are involved in this project. Actually, this is a huge project. This includes various research team in IPK, as well as from other external partners. And I would also like to thank the funding bodies. And finally, I would like to thank you for your attention. Sorry, maybe I would be a little faster due to my other commitment. And I'm happy to answer your questions.
Thank you, Dr. Murukarthik. We shall have few questions from the audience.
Karthik, thanks for your wonderful. I request our chairperson to convey the best wishes to you. You have to come here.
Hello. Thank you, Dr. Murukarthik. You have given excellent presentation. We shall have few questions from the audience. Now, you are able to hear?
Yes, yes. Yes, I think now you're.
Hello, you are able to hear?
Yes, yeah. Yes, I can hear you.
Hello, hello.
I think you are muted now.
Hello, am I audible, Dr. Murukarthik?
Yes.
It's audible. You please go ahead with the
Yeah.
question, sir.
First of all, I congratulate you for having given a very good, nice presentation. My question is a little technical. When you went for GBS of 22,000 genotypes, what was the depth and width of coverage? Number one. Number two, based on this, is it possible to arrive at core set? How
Okay,
could
so
you distinguish between duplication based discovery of the presence of sequences? How could you attribute it to the inversion? Thank you.
okay. So coming to your first questions, we would choose the enzyme. For example, we choose PST MSP1, which has a good genome-wide coverage. We could get the SNP matrix along the SNP along the chromosomes, and the coverage, I mean, is like at least we need to have 2 reads to cover 1 SNP. And because poly is highly homozygous, there is not much chance for the heterozygosity. So at least 2 reads cover 1 region would be sufficient. And the second question is, how did you identify the duplicates? Yes, from the SNP matrix, you can perform identify state analysis, which will gives you what are the 2 genotypes are highly identical, or how similar or how dissimilar. Yeah.
Yes.
Am I?
Yeah, please, Ravi Kumar.
Is it not losing the heterozygosity within the line?
Sorry, I couldn't fully hear your question.
If you are taking 1 seed from each accession,
Yes.
in case of wild species, if you take only 1 seed, are you not missing the heterogeneity within the accession?
I mean, here the point whether you need to know the heterogeneity or not. For the sequencing analysis purpose, we mainly need a homozygous line. Yeah, so if you want to make a informed selection, or if you want to make the solid conclusions, you should be very clear, like whether we are working with the homozygous material or not. And second question, yeah, we also assessed the heterogeneity in some accessions. Yeah, but we found most of the accessions shows very less heterogeneity, just because this is a selfing species.
Any more questions? So Dr. Murukarthik, thank you very much for an excellent presentation. Thank you very much from the university. Thank you.
Thank you, yeah.
Dr. Vibha Ahuja, Chief General Manager, BCIL, New Delhi. Now I request Dr. Shambalamma to give brief biodata of Dr. Vibha Ahuja. Please, ma'am.
Dr. Vibha Ahuja, she has a doctorate in microbiology from Punjab University, Chandigarh. She is presently serving as Chief General Manager at BCIL, New Delhi. And Dr. Vibha Ahuja has been working at BCIL since 1993 and has more than 30 years experience in understanding the projects for biotechnology commercialization, particularly with respect to regulatory issues. She has been dealing with projects connected with biosafety and regulatory aspects pertaining to GMOs and other genetic technologies, as well as biodiversity, conservation, and environmental for industry-related biotechnology. She has been actively engaged in the Indian regulatory framework and contributed to preparation of the guidelines, DBT GMO guidelines, and she is well versed with the discussions towards implementation of the Cartagena Protocol on biosafety and participated in various meetings related to Cartagena Protocol. She has been coordinating the capacity building activities in the areas of modern biotechnology, and also she is imparting several training programs, and seminars, workshops, national and international level training programs. And also she has prepared several publications related to these biosafety issues. And she's widely traveled and has taken up projects in Asia and African countries. We welcome you, ma'am, for the talk.
Minutes, yes. You can switch it off. You can switch this off. Yeah. Thank you so much. Thank you, madam, for your kind introduction and also inviting me to give this presentation here. As I mentioned in the morning, we had a similar meeting a few months back, 2.5 months back, and it is really a pleasure to be back here. So friends, you all have heard about the various research activities going on with respect to genomics, with respect to gene editing, and maybe onwards you will hear from Dr. Gowda about the genetic engineering products also. So it's very important that all these products, as I said in the morning, reach to the field. And for reaching to the field and to the farmers, there is another step special for these genetic technologies, and that is the biosafety considerations. So we'll quickly go through some of the guidelines. This is a very kind of a presentation giving you an overview of what biosafety is, why we need to know about these policy considerations, in addition to working in the lab. But beyond that, it doesn't finish here. It is more of a sensitization. And after that, you have to really go deep into it if you are into product development. And as I said, at any stage, any of you needs any help, there are lots of resources available, and we can guide you through specifically for your projects also. So very quickly, I will run through this slides. This is the one you said, no? Yeah. So just very quickly about what BCIL is, maybe some of you know about it. We are a company which was promoted by the Department of Biotechnology and set up by the All India Financial Institutions for commercialization of biotechnology. BCIL is not a government-owned company, but we have all the Secretary DBT, Secretary DST, DGCSIR, DGICR, all these people in our board. But our funding comes from the All India Financial Institutions. It's a very unique consortium and well thought of way back in 1990. So you could think that there was a discussion really regarding the technology commercialization at that stage itself. So which direction should it go? Here or there? Okay. So biosafety, when we started in 1990, when you have up and other things, but you also need biosafety considerations. And that's one area which we picked up also to provide support for taking forward these technologies. And as Madam said, we have been involved in a lot of activities. In addition to what all said, one very important area that we have taken up is to support the public sector organizations in preparation of the regulatory dossiers, So genetically engineered mustard, genetically engineered banana, potato. There are, for some of these crops, we are now working closely with the researchers, the leading research scientists in the country to prepare the regulatory dossiers, because it involves a lot of discussion and lot of data generation, unlike research. So as you heard in the morning, and you all are, since all students of biotechnology, the crop improvement has techniques involved right from conventional breeding, then came the genetic modification, transgenic crops, some cisgenic crops, and now we have gene editing. You've already heard about it, and I'm going to talk to you about the next step, once you have the technology. So GM crops grown all around the world. There are more than, I think, 20 plus crops as of now. And now the range of crops is very variable. It is beyond those 4 conventional crops that we had, the commercial crops. And very interestingly, lots of countries in Africa, Brazil, South America, Philippines, they are coming up with newer and newer products as per the local needs. So as I said, to start with, we had only four, major crops. That was the canola, soybean, corn, and cotton, because these are commercial crops. And the technology was so heavily regulated that it was the companies only who could invest, and they had interest only in the commercial crops. But as I said, now we have a second generation of crops coming up in terms of traits also. The initial crops were mainly related to insect resistance and the herbicide tolerance. But now there is a lot of crop, whether it is for the farmer, drought, now nitrogen yield, consumers, fortified, healthy oils, pharma, then processor crops, biofuel, feed, and industrial processes. And I tell you, all these products are there in the market as of now in the developed countries. Then came the gene editing. Now gene editing also, edited crops also have already hit the market. Started with a mushroom getting a deregulation. High oleic soybean oil is available in the US markets. So all these products are very much there. Then came this, the Japan. In Japan, Japan was one of the first countries in the Asia actually to approve the genome edited tomato, which is the high GABA tomato. It reduces the blood pressure, that is the claim. And then they have also, approved 2 types of fish. And all these products are already in the market and freely sold. So now this is a report by an international group which says that global crop biotech seed market are going to change. So you can see the blue color is breeding, which will continue to be static. We will have that particular products by the conventional market. And the red one is the GMOs, and GMOs are also slowly increasing. But as you can see, gene editing is another one which is in the market, and they are going to capture a larger share of the market. That is the projections by 2031. So now we will come to our point of why do we need biosafety assessments? Because in the genetically engineered plants, there are 2 or 3 basic requirements. One is when the GM plants are made, we are trying to introduce a novel or a modified characteristics, and this needs to be tested. Why this needs to be tested, I will tell you in the next slide. And the second would be the biosafety regulatory requirements. The genetically engineered products and the gene edited and all those genetic technologies, they are regulated as per law. And these regulations started way back in 1975 when these products came new, and when scientists realized that they are going to take genes from the various organisms, from not just from inbreeding, we had plants to plants, but now this was a powerful technology where we could take from bacteria, virus, fungi, animals, and that is why the governments started regulating it. So when we say regulating it, there are of course laws, but what is the scientific considerations and how these are regulated, how the biosafety is assessed? The key principle behind the biosafety assessment is the comparative assessment. When you have a whole food, you cannot test the foods that we eat today, whether it is any of, just now we had the food, any of the crops and all, they all never went through the toxicity or allergenicity or all those studies. And when the genetically modified crops came, then the scientists realized that those kind of paradigms which were there for chemicals will not be applicable here. So this whole thing, for about 10, 12 years, there was a lot of discussions. And finally, the agreed, principle was the substantial equivalence, which means the comparative safety. So what we try to do when we do a biosafety assessment and we say that a GM plant is safe is to compare it with its counterpart. So when we say BT brinjal is safe, we say BT brinjal is as safe as non-GM brinjal. Or GM mustard is safe means it is as safe as the non-GM mustard. It is never a whole assessment, but it is not like an alone single product being assessed, but always in comparison to its counterpart. The second very important point is it is conducted on a case-by-case basis. The crop and the trait combinations are very different, and each of them will require different safety considerations. So we need to we have to understand the crop, we have to understand the trait. For example, golden rice versus a BT cotton, both of them will have a very different biosafety testing requirements. So the guidelines that we have are very generic, but they have to be applied to your crop trait combination or your GM plant. And when you do the biosafety, you will not only consider the characteristics of the plant, introduced trait, and also the receiving environment. So these are the very important considerations which are the basis for this. And one other very important point to know in the biosafety is that, that the biosafety of GM crops is always event-based. So what is that event? When we do the plant biotechnology, we take a single gene and we insert it at a particular place. So if you have the same plant and the same construct, but it is inserted at a different place, it will be a different event, and the whole process of risk assessment or biosafety assessment and approval starts again. So that is why when you say BT cotton is approved, we know 5 different events are approved. MON 531, MON 15985, like that, there are certain names given to them. The second point that we have is the regulation of GMOs. So in India, we have regulations which are under the Environmental Protection Act. And there is there are what we call the rules for manufacture, use, import, storage. So the name itself indicates that, almost entire spectrum of activities relating to the research, development, and use are regulated. So remember, these rules were made way back in 1989. And at that time, all these technologies were new. There was no experience. Different countries were coming out with regulations, and every activity was regulated by most countries. And our rules say that we will, of course, as I said, manufacture, import, storage, and see the last line, new gene technologies will also be covered. These rules are implemented by the Ministry of Environment, Forest and Climate Change, because these rules were notified under the Environmental Protection Act. And that is why that is the ministry which regulates it. But to provide it science-based support, the Department of Biotechnology is the one which is jointly implementing, and the states have a role in monitoring. There are various committees, as in other cases of regulations. So we have, for the approval process, Institutional Biosafety Committee. Every institute has a committee. GKVK also has an Institutional Biosafety Committee. So we have almost 500 plus such committees in our country. Then comes the RCGM, which works with the DBT, and GEAC, which is the final approving authority. There is some problem with this. Okay. So as I said, there are, these are various committees. Can you help? This is going backward. Your previous one, yeah. Why don't you do it for me? I won't use it. I will see. Yeah. Okay. So these are, as I said, various authorities. I won't go into too much of details, but just to let you know that RCGM is the one which does the scientific research risk assessment, but Genetic Engineering Appraisal Committee is the final authority which will give the approval for whether it is a trials or the release. Next slide. Yeah. So as I said, Madam said that we have also been involved in preparation of some guidelines. So rules are there, rules are way back made in 1989, but then there is continuous advances in the research. So how do we move forward and provide up-to-date information to our researchers, regulators, or various applicants, whether they are from companies? So every stage of this of the genetically engineered plants, whether it is the contained use or field trials or food safety assessment or environmental safety assessment, there is a defined set of guidelines provided, and one has to generate data according to that particular guidelines. Now, it is not very difficult to do, because if you plan properly, then in your system of evaluation itself, by taking care of due precautions and planning these protocols, you can continuously generate the data and prepare a dossier out of that, which will be seen by the Genetic Engineering Appraisal Committee. Next slide. So this is the procedure where one has to have applied to IBSC, then go to RCGM, GEAC. And so what the message here is that you need to have a knowledge of this if you are working on genetically engineered plants. So every step, which guideline to follow, that you have to systematically do, and then only you can commercialize your product. If you miss out on those things, then you will be in that circle and you won't have enough data, and the product will not be able to pass through. Next slide. So the third point which I had indicated was that there are international organizations which provide guidance in this. What do they do? You see, having a process, whether this committee, that committee, how to go step by step is a sovereign right of a country. Every country has a system. But the scientific principles behind those assessments are always the same. And that is why these organizations like Codex Alimentarius for food safety, OECD for providing the basic information about the biology, about the for the familiarity principle, and then Cartagena Protocol on biosafety. These are the institutions which work, and they provide the guidance at the international level so as to have a harmonized set of guidelines. You know, you generate a data, but your country wants to export it to 10 different countries. So it doesn't mean that you will keep on generating the data differently, then the trade would be affected. Can you go fast? Go very quickly, yes. So you heard about the gene editing. So this is up to the genetically engineered plants. And then we come to the gene edited technology, which is the buzzword, and everybody is talking of its potential. Regulatory systems are risk-based. So if there are genes, or there were no regulatory systems for breeding techniques. So when the gene editing came, then people said this is a precise form of mutagenesis, mutagenic breeding. So this should also be exempted from the regulations of the GMOs, particularly the SDN1 and SDN2 categories. And that is where we have worked towards, and we have our guidelines. Can you move on to the next one, please? And also in gene editing, the final products are indistinguishable. In India, when we looked at the gene editing, it was thought that now I will take your attention back to the slide that I said, new gene technologies will also be covered. So technically, all new gene technologies were covered in our rules. However, next slide, please. However, the government has taken, the Department of Biotechnology set up a process, and during that process, please move on the slides. Yeah. So government has taken note of it, and they have exempted these genome edited plants from the provisions of biosafety regulations. This happened on 30th March after a long process of 2 years. And it is a very promising development so that the genome edited products can move very fast through the regulatory process. Please, you can do fast. So this clearly says that if the SDN1 and SDN2 are free from any transgenes, then they are, once you demonstrate that they are free from any transgenes, they are exempted from any further regulation by all those committees which I mentioned, RCGM, GAC, and so on. Next, please. Yeah, this is the same what I said, but once you have demonstrated, they will be like any other law. Next, please. I have only 2 slides. Yeah, so after that, Department of Biotechnology has further brought in guidelines which provide for what kind of data is to be generated, what is the role of IBSC, what is RCGM, and what are these definitions. Next, please. Yeah, this is the detailed processes that they have given. If you are developing SDN1 and SDN2, what you have to follow. If you are doing SDN3, what you have to follow. Next, please. Can it be done from here? Okay. So just to conclude, as I said, understanding biosafety regulations is very important if you want to bring your genetic technologies to the field from your laboratory. Biosafety guidelines are in place for various stages of product development. Gene-edited plants which are free from exogenous introduced DNA are typically exempt from biosafety assessment, and they will be regulated in the same way as products of conventional plant breeding. There is, with this notification particularly, and with some recent decisions by the government for easing out the field trial requirements, etc., we have a very good enabling policy environment for local researchers and developments. And that is the key to development of improved crops, and more crops coming from the public, more research from the public sector coming for biosafety regulations. These guidelines are, going to be more user friendly. Thank you very much. If you have any questions, I'll be happy to answer. Thank you. Digitization kind of presentations. They are introducing you to all this. And subsequently, if you have any questions, we can go through in depth those guidelines on a case-by-case basis.
Questions?
Hello, sir.
More than very good afternoon, madam. It's a good presentation. Congratulations. More than a question, it's a sensitization type of issue I want to bring forum. Actually, originally, when the biosafety regulation was started, the purpose was to ensure safety to the consumer, to the domestic animals, and to the ecological balance. Now it has come. It has now boiled down to technical level. Suppose using CRISPR-Cas mediated or TALENS mediated genome editing, if I can edit the sequence to such an extent that it is exactly identical to exogenous gene, then this rule application based on the SD1, SD3, how it will be relevant? This is my concern. In my opinion, zeal to regulate too much, it has been derailed and it has been too much distorted. And there is no technical basis now.
And it is not that it has been exempted. There is the institutional biosafety committees, which will be regulating it till it is free from exogenous introduced DNA. But if you see the kind of guidelines which have been indicated and the SOPs, what mutations are you making, what genes are being done, what you're talking of is in hypothetical scenarios. But we also know that 1 or 2 mutations which happen in like the conventional breeding or mutagenesis breeding are not going to start producing a different protein. The kind of situations you are talking will require a lot of science and lot of, when the time comes, everybody keeps watch on what is happening. It is not a complete deregulation. Institutional biosafety committees have been authorized, have been asked to give a, review what all research goes on, and once they will be the ones. The only thing is, what they're saying is once it is free from it, then you don't have to, for doing the field trials and other things, you don't have to take permissions and do. But there is definitely a regulatory oversight. Minutes of every IBSC meeting, along with in gene editing, there are specific requirements. The decisions that they take, you will see if the SOPs will come out and they will indicate they will be going to RCGM. So there will be definitely somebody who is keeping a watch on, the extent of modifications being done.
Hello. Actually, see, when you do the CRISPR-Cas, you delete or add the gene. But suppose it goes to field without even informing the IBSC or any other agency, how can they identify whether it's like a mutation? How can a person can identify it is through the CRISPR technology or gene edited technology?
Yes. So, sir, the main thing is that when you will start doing in the research in the laboratory, any recombinant DNA technology work in any institution, whether it is company or institution, they will have to inform their IBSC. So it will definitely be in your records that this person is working on these kind of things. So there is definitely a watch, sir. But definitely what you have said.
Yeah.
Yeah, what you have said is that if somebody releases it, then there is no check. It cannot be distinguished. That is because that is the technology is like that. No.
I am one of the DBT nominee for IBSC. I won't name the private company. For regulatory and file purpose, they make IBSC. But what exactly they do from commercial point of view, they won't inform to IBSC. Yes, they won't disclose. So they will show the IBSC as a proof or a flag, and they do their purpose to avoid all the regulatory.
There's a lot of data that has to go along with that. You will see the SOPs will come. It is not one line decision on that this gene edited has been approved. There is a full-fledged little dossier which will have to go and be submitted to RCGM.
As a remedy to avoid such kind of.
It is not a remedy. That is the process they have.
No, it should be made online.
Yes.
You see, madam, IPSC is a representative of public interest, no?
Yes.
What is wrong in putting every data online? IPSC only representative of the public interest. All public can
There
see
are also
it.
business interests of people, no? People will copy each other's work. So there are other considerations. So
No,
we can
since
talk
you are
about
in the
that.
helm of the
But now I just want to reiterate what is the process which has been issued by the government that everyone has to follow. Beyond that, what should be there or what should not be, that one can always make representation to the policymakers. But there is a lot of discussions which have gone into, and these are the processes. So my message to all of you is that whenever you are doing it, you have to follow all this, number one. Number two message that I want to give you is that don't think that so much of paperwork is there. It is quite simple once you start doing it and understand a little bit about it. Thank you. Thank you very much.
Thank you, madam, for excellent presentation.
Thank you, madam. I request chair, co-chair and rapporteur to give a token of appreciation for the wonderful presentation by Dr. Vibha Ahuja, madam, Chief General Manager, BCIL New Delhi.
Presentation from Dr. Kishore, DS, researcher, Seoul National University, South Korea. He will be presenting on fast track breeding for higher beta carotene content in cucumber. Is it right? Please, Mr. Kishore. Biodata will be read by Dr. Shamlamma.
Thank you, ma'am. So Dr. Kishore has obtained his doctoral degree in crop science and biotechnology from Seoul National University, and he has a research experience in the field of plant breeding, molecular plant breeding, transgenics, genomics, bioinformatics, and data analysis. And he has been awarded with the Chinese government scholarship as well as Korean government scholarship for his PhD and as well as MSc programs. You can have this one.
Good afternoon, everyone. Firstly, I would like to thank Professor Arun Kumar and Professor Veena Madam for giving this opportunity to present today at GKVK. So today I will be talking on one of my research work, which is a fast track breeding for higher beta carotene content in cucumber. To knowledge and what is the content of my presentation. So I will be giving some general introduction to understand my research topic and the materials objective and what all like the workflow we have used for this research. And also, I will present results and some of the supporting research paper for the discussion. And finally, we will have a question and answers. So what is fast track breeding? So So upon the availability of next generation sequencing, we can now sequence the ecotypes and we can generate the millions of SNPs, and we can use it these SNPs information for either QTL mapping or the GWAS studies. For QTL mapping, we do for using the biparental population, and genome wide association studies. You can conduct the genome association studies among the unrelated individuals. So as you know that, so forward genetics, what it is like aims to screen the ecotypes of phenotype ecotypes that are genetically different, and understanding the relations between this genetic polymorphism and the phenotype variation among these ecotypes is one of the fundamental interests. And this basic relationship is extensively studied in many cropland, since Mendel has showed that this relationship is inherited. So revealing genetic factors underlying simple and complex traits. So it requires some understanding of the allelic variations of specific locus level, which control the phenotype and genetic architecture of the given trait. And usually, once you have the sequencing data, you can use the sequencing information as SNPs information. You can use use the SNPs information for mapping the genes, and the association mapping. You can also try to identify the genes or the marker associated with a particular trait. So for the genome sequencing, so I'd like to give some introduction about the genome sequencing. So when you do the sequencing, like species like Viola, so which doesn't have reference genomes. So in that case, usually we make de novo assembly, where we make two different kind of, we can make the scaffold like counting construction between 200 to 800 base pair. Another one is scaffold construction with relatively largely to 40 kb, and this will be assembled to obtain the unique quantics using the Illumina platform. So once you construct the scaffold, and which can be ordered and direct into super scaffold, and you can order your order the genes, and you can also show them physical mapping physical map of the genes by genetic mapping. So in another one, the resequencing. In the resequencing, once you have the reference genome, you can directly sequence the ecotypes like cultivars you want to sequence, and we can compare the reference compare with the reference genome. In case of rice and cucumber, the reference genome is it's available. So this is the platform we have been followed. So once we sequence and we are mapping to the reference genome, and we are also performing the SNP calling steps to identify the some of the significant SNPs using the many different tools like Picardo, GATkey, and the gene information we can add with the SNP-CF. And once you identify, we can consider these are the reads obtained from the different accessions. So we can compare with the reference genome, and you can identify the, like for example, A changes to T or something. You can also try to identify the insertion and deletion events by comparing with the reference genomes. So another one, genotype by sequencing. So this is a genotyping based on sequencing technology. So here we are using a specific, we are targeting specific site. It's enzyme based, and usually your sample you are digesting with a specific DNA methylation restriction enzymes, and you will be this will be ligated with enzyme specific adapter, and this will generate the unique barcodes for each sample, and this will be pulled here, and we will further conduct a PCR amplification to make the GBS library. Once the GBS library constructed, it goes to the Illumina platform to obtain the reads, and the sequencing reads will be demultiplexed and to separate the FASTA Q files, and you can further use this FASTA Q file for further statistical analysis. And you can use this SNPs information, like you can obtain the high quality SNPs, and you can use it for the mapping. So in the today's presentation, so I will be giving the brief introduction about my crop, which I am working. It's a beta carotene rich cucumber. So as you know, cucumber is a major vegetable crop. It is about have the two-way number is about 40 and belongs to Cucurbitaceae family, and it has a lot of economic and nutritional benefits as well. And the cucumber as fruit has about 96% of water, and it has contain mineral, vitamins, proteins, and a wide range of antioxidant as well. So these most cucumber varieties has a significant morphological difference in fruit appearance, shapes, color, flavor, and so on. And it has three different, if you look at the cucumber fruit, it has three different parts. One is the exocarp, and one is the, this part is called endocarp, and this part is called as a mesocarp. And usually the fruit length of this cucumber varies between 5 to 40 centimeters, and mostly like round to cylindrical in shape. And the as I mentioned, that the exocarp, which has a various green, white, and yellow skin color, most of you guys have observed that. And here it is a flesh color. The color of this, what we call mesocarp, endocarp, is one of the important quality trait with the nutritional and economic benefits. So in the previous study, so it shows that the flesh color of these fruits is mainly depend on the amount of beta carotene. So beta carotene, which is a serve as precursor of, as you know, the vitamin A, which has a numerous health and nutritional benefits. So in this research, they have performed, classified the different cucumbers using the segregating generation. Like they have also tried to analyze the beta carotene content in mesocarp and endocarp. Like orange, it has about 2.72 microgram per gram, and like you can clearly see that the color of the fruit and the beta carotene concentration in mesocarp and endocarp. So usually the carotenoids, they are the natural pigments. Usually they are formed through isoprenoid condensation and synthesized in many fruits and vegetables. Usually this starts with MEP pathway and using the pyrite and the glyceraldehyde 3-phosphate as a primary substrates. And this will followed by phytene formation from the GGPB molecules. And further, these two enzymes, PDS and ZDS, which will catalyze the zeta carotene, and which will finally lead to the lycopene. From lycopene, alpha carotene and beta carotene will be produced by the epsilon cyclase and the lycopene beta cyclase. And from here, from the alpha carotene and beta carotene, which will be hydroxylated to form the xanthophylls like lutein, beta carotene, zeaxanthin, viloxanthin, and neoxanthin. And this is the biosynthesis process. And once the biosynthesis happen, and it will be accumulated in the chrome plush. Here, the non-colored plastic will be converted into colored plastic. At it via regulation of the chromoplast biogenesis. So in cucumber, the first so far there's only one gene which has been reported, and this is called as and in this research they have collected about 150 lines sequenced in the which has the wide geographical distribution. About 70, it consists of 77.2% of total diversity. It also consists of East Asian, and this is specific group which has the orange coloration, endocarp coloration, and which is from the China, from the Yunnan province, and the Eurasian Indian. So they have sequenced it, and they have also performed the they obtained a lot of SNPs information, and they performed the structural analysis. And you can clearly see that at the K level, K3, K4, you can clearly see that the Indian, the cucumber from the Indian, which has the highly, which has the genetically heterogeneous compared to the Eurasian and East Asians. In this particular, in further, they have also performed by considering this East Asian, and by comparing this East Asian Eurasian among the cucumbers, they could identify the gene which was previously mapped on the chromosome 3 in the Zixiongbana cucumbers, which is from the China. And they also found that the single SMP allele to asparagine at residue 255 in conserved fatty acid, which is caused for large amount of beta carotene content in this group of cucumbers. So in our material, so we got a new cucumber which is CSB, and another one is semi-white cucumber breeding inbreed line CSA, which is bred by Sejong University in South Korea, and another one is CSB, which is selected from So PI 163217 through 3 cycles of self-pollination, which is in turn we have collected from USDA, and is basically which is from India, from Madhya Pradesh. It was collected in 1948 from USDA, and which has the orange coloration endocarp. So we perform the analysis, we have tried to analyze, we tried to develop the population like BC1, F1, F2 by crossing with CSA, CSB, and reverse. And also we have tried to analyze the carotenoid content in the fruit flesh of both CSB, CSA, CSA as the white endocarp, and CSB as the orange endocarp, and also in the F2. So we also try to perform the GBS using the F2 population, and we perform the linkage to identify the gene responsible for the endocarp, right? So in order to confirm our mapping, so we also perform the whole genome sequencing of the both CSA and CSB, and we try to identify the SNPs by perform the comparative analysis between these two lines. And after obtaining the SNPs information by comparing with the carotenoid biosynthesis pathway via KEG pathway analysis, we could find a lot of non-synonymous SNPs, and we also perform the HRM, high resolution melting analysis. It's an next generation PCR. We perform in a real time PCR, and we perform the multiple sequence alignment, and finally perform the quantitative QRT to check the expression level at different stages of fruit development. When we look at our results, so we are these are the P1 and P2, and which is the CSB, and this is the CSA, which is the orange endocarp, which is the. So we wanted to know what is the genetic mechanism controlling this orange coloration in the CSB line, and we made a lot of crosses, and our analysis shows that this gene is segregating in the 3:1 ratio, which is a single recessive gene. In the cucumber, previously it also identified the gene from China, which was identified. It's also this trait has been proved as a single trait controlled by single recessive gene. So after we perform the phenotype evolution, we have also tried to identify the carotenoid content in the different stages of the fruit development after like anthesis, like 10 days after anthesis, 20 days after anthesis, and 30 days, 40 days among the parental lines. And you can clearly see that the beta carotene content in the endocarp, which is quite, there is no any significant difference, but when it goes to 20, 30, 40, there's a huge significant difference between the CSA and CSB line. CSA as the white color endocarp, and the CSB as the orange color endocarp. So we also try to use using the F2 population. We try to conduct the GBS by individual plant in the F2 population. Here we have used about 206 plants which were sequenced, and we got about reached about 585 million around the read line, and the length of read is about 59.2 GB, and raw SNPs we obtained about 96,000 around, and we have filtered these SNPs from the raw SNPs based on the quality parameter. About 67,000 around SNPs we have obtained. So using this GBS, using these SNPs, high quality SNPs, so SNPs which is segregating in 1:2:1 ratio, we have selected in F2 plants between the cross between CSA and CSB, and as a result, we got about 160 SNPs in the phenotype endocarp from 206 plants for used for linkage mapping, and totally we got about 7 linkage group, and in the chromosome number 7 on 7 chromosome, we could identify, we could map this gene here between 100.9 centimorgan to 160.4 centimorgan on linkage group 19. So within this mapping region, we try to look through in silico analysis, and we got 2 candidate genes The one gene which is OR gene, CSOR gene, and another gene which is also associated with a carotenoid biosynthesis pathway, which is mainly involved in the lutein biosynthesis in Arabidopsis reported. And the another one is CSOR. We are detected in 1.6 megabase per encode for DNAG-like protein and known to be responsible for IL beta carotene accumulation in orange cauliflower and melon. It is a known gene, and we have identified in the cucumber first time. So we try to confirm these two candidate genes within this mapping region, and we try to sequencing and we compare them, and we also perform some comparative analysis using the KGG pathway and NCBI protein database, and we could get about 7 genes, and all the non-synonymous SNP we have also obtained, and we perform the, and among the 7 genes, only 2 genes it is known to be involved with carotenoid biosynthesis pathway, and one which is involved in the lycopene, and we also perform the HRM, and also the another one gene we have identified from the GBS based linkage mapping with the same gene, but in the GBS we have we did mapping in the cucumber genome reference 2, but here in the resequencing we have compared with the cucumber version 3. So that's how why the gene ID will be different. So finally, we have validated through the with the HRM PCR. We can clearly see that these are the F1s and these are CSB, all the F2 plants, which is clearly we got a 2 clear peaks and CSB line and CSA, and which is all segregated in the 1:2:1, and we have performed with about 195 F2 plants. So which is evident that, and the first we got overall like 4 SNPs in the OR genes. The first 2 SNPs, which is near to the N-terminal region, which is co-segregated with the phenotype. And this result evident that this is the these alleles are associated with this orange endocount. And finally, like we also did the multiple sequence alignment, and we can clearly see it is located in the first exon of the OR gene. And we also try to compare them with other species, and only the cucumber genome has this mutation. T one is changed to G, and another one is T also changes. AT is changed to the ACC. So we try to also do the check the expression level of these to different stages of fruit development. And we can clearly see that between both endocarp and mesocarp, we can clearly see the significant difference was observed among these 2 parental line, and which our results evident that the OR gene involvement in the beta carotene accumulation in the CSP line cucumber plant race. So in the previously in the melon also, it was evident that the RG9 okay, can you go back? Yeah. In the arginine changed to histidine in melon, it is also caused the it also shows that this OR gene is controlled by single recessive gene, and is also co-segregated with the endocarp phenotype in melon. And the next can you go next? Even in the cauliflower, there are some evidence of genetic engineering. They also perform some of the functional studies, and they shows that the overexpression of mutated ORF protein, which shows the orange coloration in the mutant cauliflower. Next. In the finally, like Arabidopsis, in the Arabidopsis as well, our SNPs were identified in the protein near to the N-terminal region, and there are some evidence that the OR protein and the phytane protein, which positively it has involved in post-respiration regulator and probably accumulation of carotenoid in the Arabidopsis, and they have confirmed. They have also performed through some functional studies, and finally. And finally, the conclusion of this study, and we have identified the new allele, OR allele, which is a different from the cucumber, which has the orange coloration from the Yunnan province, China, and the breeders and this allele, new allele can be used for marker assisted breeding, and also by combination of this BCS gene from the Yunnan and also from the OR gene combination, we can also use we can use these two alleles and use it for marker assisted breeding and to develop the nutrition rich cucumbers. Thank you.
Thank you, Dr. Kishore,
Yeah.
for your good presentation. Now we shall have a few questions from the audience.
Dr. Kishore,
thank you.
It was a nice technically motivating work, and also it is evident from publication. First of all, my question looks silly or funny, but academically very important.
Yes.
We have been in the recent past hearing buzzing words like accelerated breeding, speed breeding, fast track breeding. Are they linguistically synonymous only or technically stand for different meaning? That's one first question. Second question is, to call it as a speed breeding, accelerated breeding, or fast track breeding, what should be the time limit?
Time
By
limit,
gain of
that's what-
how much time we can say, or it gets qualified as speed breeding or fast breeding?
That's what we are using the next generation sequencing technologies. That's we are
No, I'm
incorporating both.
asking fundamental academic question. By gaining how much time my research or work gets qualified as fast breeding, fast track breeding, speed breeding, accelerated breeding?
Yeah.
See, in achieving the breeding objective, certain time is required
Yes.
in a traditional method. And you are applying advanced technology. But by what? Simply by application of advanced technology, whether it gets qualified as a fast track breeding or it requires to gain certain critical amount of time advantage.
Yeah, we have already the markers for the OR, and you can use it that, and you can develop. It depends on the.
Sorry, my question is not answered. It's a food for thought for everybody in the room.
No, his question is very clear. You have used modern technologies,
Yes.
fine, for getting your results. But when you talk about fast track breeding, we do have in traditional plant breeding, we
Yeah, I
need
got it.
many
I got
years.
it.
By using these technologies, what is your
Use,
the
yeah, we
speed
can,
with which you have
yeah, we
achieved
can
the
identify
goal?
by using this technology. We are identifying the novel genes, which is ultimately used for the traditional breeding, right?
That's
That's
fine,
what
but the
fast
time, we are talking about the time which
So
is
we can
required.
you can incorporate other different strategies like omics
Okay,
and all.
okay, fine. Any other question? Okay,
Okay.
thank you, Mr.
Thank you.
Kishore, for your excellent presentation.
I'd like to thank Dr. Kishore DS, researcher, Seoul National University, South Korea, for his wonderful talk. And I request chair, co-chair, and rapporteur to present token of appreciation for his talk. With the permission of chair, I would like to announce there are parallel sessions going on at two other places than this. One is session 2, that is biochemistry, environmental biotech, and animal biotechnology at Dwarkanath Lecture Hall, first floor. And then industrial and entrepreneurship, Dean PG, PGS conference hall. So those who have oral talks, I request the oral speakers to move to their respective places.
Thank you. Now the fourth speaker, Dr. R.L. Ravikumar, who is a retired professor and head from Department of Biotechnology, US, Bangalore. We will be speaking on mapping and fine mapping of Fusarium wilt resistant loci in chickpea. Now I request Shamlama to read his brief biodata. Ravikumar, please. Please take the chair for a while.
This is on only, sir. This is next. Previous. This is a pointer. Okay. Wait for a few seconds after press 1 10 press. First of all, let me thank the organizers for giving me this opportunity. I am a retired professor of this same biotechnology department. Basically, I am genetics and plant breeding background. After coming here, I started working on biotechnological aspects, particularly with reference to molecular markers. Okay. So I'll be, thank you, Shamdamma. So I'll be talking on some research, a small research area where we have worked for about 8-10 years with the help of students. And this is where, through this, honestly, through this project, I have also learned a little bit about molecular markers. Otherwise, I'm from a classical plant breeding background. Okay. So mapping and fine mapping of fusarium wilt resistance loci in chickpea. This is a review of the work we have carried out. So as all of you know that to wait, it seems. So fusarium, it's caused by fusarium oxysporum. It is one of the major diseases of chickpea actually. It causes up to 90% yield loss. And another important thing is, because chickpea is grown in most of the peninsular India, this fusarium has spread to almost all the chickpea cultivating regions of Karnataka and also in southern India. That's why it has become a very widespread disease. And although there are many races have been reported in case of chickpea, actually, the race pattern is not very clear because there are not many differentials that are available. And race 1 is considered to be most important, and people work on race 1 only, actually. So as I told you, in case of fusarium wilt, there are actually, we can classify the wilt. There are early wilt, actually, wilt which show wilting symptoms within 30 days. That is considered as early wilt, and followed by late wilting. Late wilting, it is anywhere between 30 to 60 days. At 60 days also, there is a lot of wilting, and both these causes a severe yield losses in the crop plants. This is late wilting actually. At later stages, it will show wilting, and another one is resistant. And so the resistant sources are available in the germplasm. Okay, high level of resistance is available. So then people started working with classical genetics. They started looking for genes for resistance, actually using stable resistant sources. And classical genetics, when they have classified into resistant and susceptible groups, actually they have observed there are a lot of 2 to 3 genes which are controlling resistance. However, now the concept is there are many loci which are responsible for wilt resistance. That's the reason why the people have started approaching wilt resistance as some sort of a QTL. However, in the initial stages, classical people, they have considered it as major gene resistance, although there are major QTLs that they have identified. So once they know that the major resistance sources are available, people started looking for molecular markers for resistance. Actually, initially, as early as in 1997, they have identified one of the allele-specific marker for wilt resistance, and that they have linked to one of the loci, that is H1 loci. We also initiated work on this, working on this H1 loci. We validated this H1 loci across large number of genotypes, and it is found to be working well, actually. So once after working with this, actually, then we started looking for, we have also mapped this, H1 loci, and it also showed even in the segregating population, it appears to be working. So that is where this H1 locus, which they have reported earlier as allele specific marker, which is also one of the important marker for chickpea breeding. So once we have identified, it explains about, this is our study where it explains this locus, which has been reported earlier, it explains about 26% of the phenotypic variance. That's the reason why it is considered as one of the major loci for resistance. Then we started looking for the other QTLs as well as genes for wilt resistance. In the process to work on these things for linkage mapping, we have developed 2 specific mapping populations. One is between early wilting and late wilting. Another one is early wilting and resistant. Another one is late wilting and the resistant genotypes. And the RILs are available now, and we have started working with these RILs. So another important thing is phenotyping of these RILs is another critical things, and working with wilt resistance wherever soil-borne diseases, it is not easy. So we had to take the help of for phenotyping. We had to take the help of ICRISAT. There is a well-known sick plots are available, and we have phenotyped our RILs in for 2 seasons in ICRISAT wilt sick plots. So apart from this, we have also worked with part culture techniques. We have only developed all these wilt sick plots here. Actually, you can see that all the plants are showing wilt symptoms. This is the genotype which we have planted, which is highly susceptible to wilt, and all the plants were uniformly showing wilt actually. And see, whenever we have screened our RILs, we have also used one of the susceptible check in between. So these are the plants which show early wilting, and they have also killed along with all the other susceptible genotype, that is JG62, which is in the between. These are all the ones which are showing either resistance or late wilting. So you look at this, the susceptible plant is dead, but the other plants are not killed actually. This is how we have developed a very good wilt sick pots, and we have screened all our RILs using this wilt sick pots also. Along with this ICRISAT data, whenever we have used for mapping, we have also used this pot culture data also. So with this, we started working. Initially, we started working with RAPD markers, because that is where I have also learned through the process. We started working with RAPD markers and mapping. And one of the RAPD marker which we have worked, this one of the RAPD marker has been shown linkage with this wilt resistance. So, and with this RAPD marker, then we have cloned this RAPD marker, sequenced and converted into CAPS marker. So this is how we have cloned this RAPD marker, and we have converted this into CAPS marker, and this CAPS marker has been validated across several genotypes, and it is found to be working very well for us actually. And we have also used this CAPS marker for mapping studies. So this is where we have observed that the CAPS marker and the markers which are linked to wilt resistance are also working. So apart from this, we have also developed another screening method, that is pollen-based screening method. This has also been very well accepted, even by ICRISAT. Also, they're including in their protocol of screening for screening, pollen-based screening also. So this is the RAPD marker which showed linkage, and we have validated this marker. Then we started looking for mapping using SSR markers. Then we this is the next slide. So then we started using SSR markers for mapping these loci. Next please. So we have also mapped. So the point I want to tell is that we started working with this mapping populations, and we started using SSR markers and to map the loci. And in the process, next please. So so this is a combination of both RAPD as well as SSR markers. In the process, we have identified some of the QTLs which are major QTLs by using these linkage mapping populations. Next slide, please. Similarly, we have several students have worked on this mapping population using different sets of SSR markers. So like this, several students have started working on this QTL mapping, and they have identified large number of QTLs for wilt resistance actually. So similarly throughout the world, people also started on working on wilt resistance, and several people have published work on QTL mapping. And along with that, we have also identified large number of QTLs for wilt resistance. Next slide, please. Next slide, next slide. So what happened in the process? We have also, by using these two mapping populations and the phenotyping techniques, we have also identified large number of QTLs actually, and some of them are overlapping with the other people who have worked with the chickpea quitting mapping also. But when we looked at the literature, there are large number of people who are working on wilt resistance, and there are large number of reports are available on QTLs for wilt resistance. So when we went through this, there are nearly about 46 different markers have been reported, which are linked to the QTL, which are linked to the wilt resistance. Then what we thought is, instead of go on doing the same work again and again, what we thought was we wanted to first validate all the QTLs that have been reported for wilt resistance in our mapping populations. So then once after mining all this literature, we have found out there are large number of reports that are available. Approximately about 42 to 46 markers have been reported for wilt resistance. And we have used only those markers in our mapping population to find out whether how many of the reliable QTLs we can be identified. Next one, please. About 42 linked markers for wilt resistance. And we have genotyped all our mapping population using only the markers which are linked to the QTLs. Next slide, please. So, and we have also identified most of these markers that we have identified in our study has also been reported by other workers, and most of them are also reliable, and they have been also they are also being used in case of marker restricted selection also. So once we have identified these stable QTLs which have been exploited by others also, then what we thought was, now most of the QTLs that have been reported earlier and also confirmed by our studies is that they represent a very wide genome area actually. So most of the earlier studies are also, even our studies are also, was not based on the saturated linkage mass, which was based on only very limited number of SSR markers. That's the reason why it was representing a very huge area. Then what the next step, what we thought was, next one please. So next, what we thought was, now since there are so many markers that have been reported with QTL, we thought we wanted to fine map these particular QTL regions. Then what we did was we have physically mapped all the markers that have been identified by using whatever available chickpea genome sequence at that time. It was not a very high reference genome that was available, but it was a very draft genome which was available. And we have in silico mapped all these QTLs onto the chickpea genome sequence. And out of the 46 markers, 23 markers were only mapped onto the chickpea chromosomes, and rest of them either they are not mapped on the chickpea genome, or because it is supposed to meet some certain standards, it did not meet the standards. Otherwise, some of them were like, we have identified RAPD or AFLP marker, which we did not use for mapping studies, etc. So ultimately, we have used about 23 markers physically mapped onto the chromosomes, and we now know the genomic regions that are responsible for this wilt resistance. So once we know these genomic regions, so then we started looking for the genes that are available in this particular region. Next slide. Next slide. These are all the markers which we have mapped, and all these markers they represent wilt resistance loci. Next one, please. So as I told you, some of them mapped onto the chromosome, some of the markers which are also mapped onto the scaffold. Next one, please. So once we mapped these markers onto the chromosome, we started looking for what does this region contains actually. When you look at this when we look at this genomic region, so these are all the chromosomes on which these markers have been mapped actually, and the total genomic length that is covered is about 38.5 MB, and the number of genes which are present in this particular region is approximately about 1,500. And we started looking for SSR markers in that particular gene. That is we started looking only for the genic based SSR markers, not the genomic SSR markers in that particular region. And there are nearly about 2,250 SSR regions were available from the set of nearly about 1,500 genes. From these 2,250 SSR regions, we can design primers only for about 941 SSR loci, and from this 941 SSR, all these 941 SSR, they represent the genomic region where the QTLs are present. But we could only synthesize about 168 primers have been synthesized from this 941, and we have labeled them as UASBC, that is University of Agricultural Sciences Bangalore, and that has been worldwide people are using these markers now. Actually, out of these 168 markers, the 161 showed proper amplification. So that means 160 primers are working. And out of these 161 primers, we looked for polymorphism, about 23 and markers in case of one mapping population, and 24 markers in another mapping population that they have showed polymorphism. This clearly indicates now the remaining markers are not polymorphic in our mapping population. The contrasting genotypes we have, that's the reason probably they may not be validated in the population also. That we have taken considered as out of 161 SSR marker, that only 23 showed polymorphism, only 123 are validated, and the remaining are not validated. Next, please. And using these polymorphic slide, now we are concentrating only in the QTL region. We are concentrating only these QTL regions, and using this polymorphic SSR markers, again we have mapped the we have used the mapping population and mapped these newly identified SSR markers. Next one, please. And we have also identified several SSR markers. Among these things, they are also linked to QTLs of wilt resistance. Next one, please. So these are the markers. These are all the markers which are from the QTL region, and they have also we have also identified. These are the markers which we have identified, which are showing a linkage with the next one, please. Next one, please. In the another cross. So whatever the now markers which we have identified, they are in the genomic region actually. So this is where all our markers. Next one, please. So that is the interval where the QTLs have been mapped. So look at this now. The earlier markers that have been reported for wilt resistance, they represent a region of about 13.5 MB. In that 13.5 MB, we have generated markers, gene-based SSR markers, and the new markers which we have identified, it represents only 5.3 MB. That means the markers have moved closer to the QTL loci. Next one, in all the cases, whatever we have observed, look at this from 6.8 MB, it has gone to the markers which are closely 3.9 MB, 5.8 to 5.46 MB. Next one, please. So in all the cases, we have identified markers which are closely linked to the trait of interest. That is what we call it as fine mapping. Next one, please. So now the QTL has been redefined. It was about 13.5 MB. It has come to 5.4 MB. And all these markers which we have, the redefined QTLs, okay, and hence they represent a very small area. Once they represent the very small area, the reliability of selection for the trait with these markers will be increased. So, and also we try to look at the the genes which are present in this, and some of the nearly about 75 candidate genes are present in the whatever the new QTL region which we have identified, and probably one can also pursue developing markers for these candidate genes also, and look for the gene which is responsible for wilt resistance. And all the whatever the markers which we have identified and fine mapped in the same region, although they are not using our markers, okay, people have used this particular regions also identified. Many people have also identified the same region, not only we actually. And the only thing is we validated these markers, and those regions have with a different set of markers have been employed in case of marker assisted breeding. And there is one variety called a super anagiri, which has been improved for wilt resistance using marker assisted selection using the QTLs, which we also have represented, has been exploited. Next one, please. Similarly, in another study also, people are pyramiding the wilt resistance using the QTL regions, which we have also identified along with others. It is not the only we have also identified the same regions, and we have also fine mapped these regions. So probably in future, probably when they use our markers, the reliability will increase. We have redefined the QTLs to a smaller fragment. Thank you very much.
Thank you, Ravi Kumar. Questions from audience?
I congratulate you for the extensive work. My point is, breeding point of view, you have done this kind of work. What is the biochemical mechanism for a fungi toxicity here? Any information? Because something has to produce, the fungus has to die, otherwise it should not enter, or some mechanism must be there to get a resistance. Because it's a soil-borne fungus, we can't avoid. So what is these genes are doing in biochemical, something that is producing and going in the root exudates? Any information on this?
No, sir.
I have a second question. That's why I'm asking this.
No,
Because in case of banana, whether we can use these QTLs and your markers, banana also very serious problem with the
banana,
Panama
yes.
disease.
Yes.
Whether we can use this in a banana or any other crop, these QTLs, is it specific to chickpea only?
It is specific to it's specific to chickpea only, sir.
Is there any possibility of using?
No, sir. No, sir. Actually, see what's happening is now we probably if we can pinpoint and see this is the gene which is responsible for resistance, then we can extend it to other crop plants.
But if you know the mechanism involved there, probably it can give a lead. What is the mechanism involved to avoid the fungus to infect?
So one thing they have observed is growth is suppressed, sir. Actually, it actually in case of wilt, it is not only the toxin which produces, it also blocks the xylem vessels. Okay, there are many biochemical explanations for that. It blocks and the tissues are damaged, macerated. All those things are there, sir. Actually, okay. But actual mechanism is not known. I think banana, they are also trying to look for a genes that is responsible. And I went through some papers where they're trying also looking at CRISPR-Cas approaches to modify the gene and all.
Because the mechanism is same in banana also. It blocks the.
So, but actually there is a problem, sir. Actually, people thought red gram and that is also again actually. There is some problems, sir. Actually, initially people thought it is the same mechanism that is operating there also, but in case of red gram, we don't get this wilt at the very early stages, like in case of chickpea. So that's why they
probably you have to understand what is the mechanism involved to avoid the fungus.
Yes.
Case of most of the fungal diseases, when we see the biochemical mechanism, it is the glucanases and chitinases which are present in large quantity can prevent these fungal diseases, because glucans and chitins, if you use these genes, glucanase and chitinase genes, it can dissolve the fungal cell wall when we clone this gene and express in the plants. That's what they have observed. But we have to see that what is the amount of glucanases and chitinases present in these resistant varieties versus the susceptible one.
All of them together, they are doing something.
They are doing, sir. It's a quantitative.
So what is
resistance.
that mechanism?
Maybe it may inhibit the pathogen growth at several levels. Sir. Thank you.
Thank you, Dr. Ravi Kumar, for your excellent presentation.
I thank Professor R.L. Ravi Kumar for his wonderful, and I request Chair, Co-Chair, and Rapporteur to give a token of appreciation for his wonderful talk.
Now we are coming to the last presentation by Dr. Ramanjani Gowda, who is a retired professor and head from Department of Biotechnology, US Bangalore, and also he is the Board of Regent from US Bangalore. He will be speaking on problems and prospects of producing recombinant proteins in plants. I request Shamlama to read his brief biodata.
Dr. P.H. Ramanjani Gowda sir is alumni of our US Bangalore, and he has PhD in horticulture as well as PhD. And he has postdoctoral degree from Tuskegee University, USA, and he has a Indian patent for production of rabies glycoprotein in muskmelon, and he has guided 42 MSc students and 8 PhD students, and he received Sir C.V. Raman Award in the year 1997 from Government of Karnataka for the outstanding agriculture research, and also is the recipient of Best Research Worker Award from the Tuskegee University, USA. Besides, he has several other awards, and he has published more than 75 research papers and 33 research articles. We invite you to deliver the lecture, sir.
Thank you, Dr. Shamlama, for your nice introduction. Anyhow, I'm as a genetic engineering, the topic which I am covering. In fact, I am taking an example of our own research. In fact, how we can transfer genes into the plants. For example, here I'm taking an example of Coleus forculi, which can be transferred with which can be transferred with the genes. So when we are selecting for any introduction of genes, the recombinant genes, in fact, we should, for example, like especially we are targeting for the edible vaccines or the recombinant proteins into the plants. We have to look into for the several aspects, like suppose you just introduce a gene into the plant, and that should not become weedy, means invasiveness. It should not be an uncontrollable one, like so that's why we see that when we talk about the introduction of genes into the plant system, we think about the one biodiversity and also the invasiveness. For example, in case of brinjal, for example, like there's a problem of borer caused by the Lucinodes originalis. In fact, when you take the white species like Solanum incanum, which is a relative of Solanum melongena, what happens, like Solanum incanum is an invasive species. In fact, the seeds can spread, and it has got a lot of thorny and thorniness, and it's very difficult to remove this weed. Suppose if you take the gene from Solanum incanum and introduce into Solanum melongena, even though you may get little resistance to this Lucinodes originalis, but it is difficult. If you can take the gene from a Solanum macranthum, which is resistant to borer, you can get successful hybrids. But we have tried, and anyhow that the F1 was sterile. Just I'm giving an example of weediness, how we can introduce a weediness into the nature. And even if you spray any type of weedicides, it is very difficult to kill these weeds. So that's why we should be very careful about introducing the genes into the plants. That's about the gene flow. And the plant pest properties, we have to see whether they become resistant to the pests, and also the impact on other organisms and impacts on biodiversity. All these things, in fact, I have just mentioned that how it can spoil the biodiversity. When we introduce the genes, we should think about these things. No. So here I'm taking an example of introducing a gene into a plant system, like the vaccine genes into a plant system. For example, here I'm talking about the introducing hepatitis B gene and other genes into the plant system. So here I selected the Coleus forculi because it should be an edible one. Like whenever you choose a plant system for the particular purpose, here the purpose is about the edible vaccine. Here we have chosen this plant Coleus forculi because it is edible, and it should be amenable for regeneration. This is a very important thing. Whenever you do, not only for Coleus, for any other plant varieties, if you want to introduce a gene, that particular plant should be amenable for regeneration. That means, like, suppose you want to transform a wheat, if you want to transform rice variety or any other variety, that you should see that whether they are amenable for regeneration or whether they are calcitrants. You have to see. For example, if you take the example of a wheat variety or a maize variety, for example, that recalcitrant, you cannot introduce the gene of your interest. But the other way how to overcome this dependency or introduction of the gene is about, like, if you have a maize variety, the maize variety you may have about 500 varieties, in fact, within the this maize. So you should assess these varieties, which variety is amenable for regeneration. That's a very important thing. So some varieties are not amenable for regeneration, and only some particular varieties are amenable for regeneration. We have seen this in muskmelon. In fact, when we have screened about 150 varieties of
500 to 2000 example, what?
Regeneration. So that is a very important thing. If you want to introduce the gene,
125 ಟ್ಯಾಬ್ಲೆಟ್ಸ್ ಐಪ್ಯಾಡ್ ಎಲ್ಲ ಮತ್ತೆ ಎಲ್ಲ ಒಂದು PI 2 PI 2 CCP ಯಾರಿಗೆ ಲ್ಯಾಪ್ಟಾಪ್ ನೀವು ಇಲ್ಲದೆ
and here in case of this recombinant protein production, this should be a rich source of protein. You cannot select a plant which cannot produce more protein. Suppose if I select cucumber to introduce this plant, it contains 96% mentioned by our previous speakers. It's going to accumulate more protein. It is of no use. You see that accumulate more protein, fast growing and produce enough biomass, and it should be grown under tough conditions. It should not produce much pollen. That's why we have selected here the vegetatively propagated plant. As we know that this in the biosafety, especially in the transgenic, the biosafety is for the pollen transmission, because most of these, suppose you introduce a herbicide resistant gene into a cucumber varieties, they produce abundant pollen. In fact, this pollen may transfer to the other relatives. Right? That is the problem. Like because of this pollen transmission, you should be very careful about when you choose or introduce a gene, especially if you are working on some vaccines or other related things where other related species. So if it's a vegetative one, it is very much safe. Here you can see that we have selected this plant foliage because it contains very high leaf biomass. Vegetatively propagated, there is no question of producing any gene, and this regeneration is very easy. You can grow problem at all. So we have introduced this HPS-AG gene. That's
Shall I start?
Gene which can with the 35
My topic is on omics approach to hazel breeding for downy mildew resistant sick breeds that we are working in IHA.
foliage. You can see that with a BAP 2 milligrams and NAA 0.6 milligrams, you can see that the plant is growing happily with this gene, with its gene, and it can produce.
Share the whole screen. Actually.
It can
So
establish.
maybe only your presentation.
This is a good example to show that you can introduce the genes into a plant system where it is not producing any pollen or a seed which can be dangerous to other related species. See here we have grown this in the greenhouse with transformation, and
very important cultivated crop.
show that the transformation is possible. And with PCR, we could show that
it is having very economic value worldwide, globally, and the use of it also is very oldest crop among the fruit crops which is cultivated. But the great breed is recently hampered by use of fungicides, because whenever we are about to take the grapes, we thought of how much of fungicide is present in that one. Many defer to take
in the plant system. So this hepatitis B protein previously it was
fungicides against
in fact, with
and it is caused by Plasmopara viticola, and plenty of chemicals are applying on this one, for pre as well as the post-infection chemicals is applied. It is estimated that around 68,000 tons per year fungicide is applied worldwide, and it accounts around 65% of about all the fungicides. So you know that how much environmental pollution it creates, and the resistance as well as the residual toxicity creates final implications for
be like particles.
these are the symptoms
You
of
can
this
just see that in the cells, a lot of VLP, virus-like particles which has been collected. This was in collaboration with NCBS. It was done by one of my students.
ಇಬ್ಬರು ಮೂರು ಜನ ಅಷ್ಟೇ ಬೈಲಿಕ್ಕೆ ಕ್ವಶನ್ ಮಾಡೋದು ಆನ್ಲೈನ್ ಇಬ್ಬರು ಮೂರು ಜನ
Studies.
ಅಲ್ಲ ಸರ್ ಇದು ಹೈಬ್ರಿಡ್ ಮೋಡ್ ವರ್ಕರ್ ಸರ್ ಹೈಬ್ರಿಡ್
It was tested for its immune response. The plant produced Coleus forculi protein for HBsAg, which was tested in Bioneat's company actually, and you can just see that this commercial vaccine in 100 dilution it has given 1.12, and you can just see that in Pisha Pasteris you can see in beyond Coleus forculi has also produced a very high immune response 1.7 in the dilution. You can see that it has been the standards of the female ball mice was used in
it's but if it becomes like 2500 or something, then I take on my own phone. But if it is a separate phone, sir, use of product, so we can manage bills and
another thing like
ಯಾವ ನಮ್ಮವೆಲ್ಲ ಯಾವ 500 ರೂಪಾಯಿನೇ ಬರಲ್ಲ ನಾವು ಒಂದು ವರ್ಷ ಪ್ಲಾನ್ ಒಂದು ವರ್ಷ ಅಷ್ಟೇ ಒಂದು ಕೆಲಸ ಈಗ 1800 ಮಾಡ್ತಿದ್ದಾರೆ ಈಗ 2-3 years ಇಂದ 1500 1800 ಮಾಡಿದ್ದಾರೆ ಅನ್ಲಿಮಿಟೆಡ್ ಕನೆಕ್ಷನ್ ಡೇಟಾ ಮಾತ್ರ ಸ್ವಲ್ಪ ಬೇರೆ ಚೇಂಜ್ ಖಾಲಿ ಆಗುತ್ತೆ
ಕ್ಯಾರಿ ಫಾರ್ವರ್ಡ್
ನಮ್ದು
ಡೇಟಾ
ಒಂದು ವರ್ಷಕ್ಕೆ
below the age of 14, about 79,000 diabetes and about
ನಮ್ಗೆ ನೋಡಿ ಸರ್ 2000 ಒಂದು ವರ್ಷಕ್ಕೆ ಅಷ್ಟೇ ಮ್ಯಾಕ್ಸಿಮಮ್ ಖರ್ಚು 1500 ಡೇಟಾ ಒಂದು 300-500 ಕೊಟ್ಟರೆ ಮತ್ತೆ 50 GB ಸಿಗುತ್ತೆ ಖರ್ಚಾಗಲ್ಲ ಅಷ್ಟು ಸಾಕಾಗುತ್ತೆ 30 ವರ್ಷ
they lost the production to identify this disease. CAT65 protein.
ಕೆಲವರು ಈಗ 300 ಅಥವಾ 600 ಅಥವಾ ಎಕ್ಸ್ಪೆನ್ಸ್ ಪ್ಯಾಕೇಜ್ ಹಾಕಿದ್ರೆ ಇಟ್ ನಾಟ್ ಪ್ಲಸ್ 3000 ಹಂಗೆ ಹೋದ್ರು ಸ್ಪೆಷಲ್ ತಗೊಂಡ್ರೆ 3000
infiltration method.
ಹಂಗೆ ಇಂಟರ್ನೆಟ್ ಡೇಟಾ ಅಷ್ಟೇ ಸರ್ 12000 ಆಗುತ್ತೆ ಅಷ್ಟೇ ವೆಹಿಕಲ್ ತಗೊಂಡ್ರೆ ಮನೆಗೆ ಒಂದು 12000 15000 ಮ್ಯಾಕ್ಸಿಮಮ್
700 ಎಲ್ಲ 3 to 4 months ಬರುತ್ತೆ
3 months ಕೊಡ್ತಾರೆ 90 days ಅನ್ನು ಕೊಡ್ತಾರೆ 700
and one multi-purpose
and it has been Western blot has been done and shown that
ಅವತ್ತು ತಲೆ ತಿಂದ್ರೆ ಸರ್ ಪ್ರೆಸೆಂಟೇಷನ್ ಮಾಡೋದು ಅವತ್ತು ತಲೆ ಬಿಡ್ಲಿಲ್ಲ ಅವತ್ತು ಪ್ರೆಸೆಂಟೇಷನ್ ಮಾಡೋದು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ತಾನೆ ಇದ್ರು ಸಾಕಾಗಿತ್ತು
ಇಲ್ಲ
ಹಂಗೆ ನಾಳೆ ಆಸ್ಪತ್ರೆಗೆ ಹೋಗ್ಬೇಕು ಆಪರೇಷನ್ ಇದೆ ಅಂತಾಳೆ ಸುಮ್ಮನೆ ಅವೆಲ್ಲ ಪ್ಲಾನ್
HBsAg gene has been introduced. Other than that,
ಎಲ್ಲಾರನ್ನೂ ರೆಡಿ ಮಾಡ್ಬಿಟ್ಟಿದ್ದಾರೆ 4 ಜನ ರೆಡಿ ಮಾಡಿದ್ದಾರೆ
expressed the rabies vaccine in plant systems, and we had a patent production of rabies vaccine in polio. This is in brief.
Thank you, Dr. Ramanjani Gowda, for the excellent presentation. He is one of the pioneers in UAE Bangalore who started transgenic work and is doing a lot. I think the very bio data Sangama is read. Now I request the audience to ask clarifications and questions.
Sir, thank you, sir. You were my teacher too, and you were all motivated. Even for undergraduation, you came and taught us gene library.
Very
As
first time.
motivation, it made me to join biotechnology. Coming to the topic, sir, 35 as promoter was used. No, actually, except glycosylation step, it must be producing premature protein throughout the system. However,
Actually, project
is there any flesh-specific promoter identified in muskmelon? If so, if it is used, whether efficiency can be increased?
It can be increased. There are various promoters have been used other than 35S promoter. It has been screened for even the fig wart promoter and other things. But 35S promoter was efficient when compared to other promoters. That was the thing.
So this rabies vaccine or any of this health-related things when you produce in plants, won't it be considered as a transgenic plants? Or would you suggest that you extract the protein from plant and make a vials and then give? What is your suggestion for the commercial utilization of this kind of technologies, even though they have potential?
See, there's a one product is already in the market, that was produced in carrot in US actually. That's the only one which we can give as an example. It is a transgenic. Whatever you produce in the plants is a transgenic. And the major problem is purification is the major problem. The other thing is in India, there is a lot of problem about the clearances by the RCGM and GAC because they consider it as a transgenic. Whereas in US, there is a separate policy for production of these type of vaccines in plant system. They consider as another system, like you produce in piscia, you produce in insects, you produce in other bacteria and other things. So that they consider it as in that group, and they consider it separately, and they have got different protocols and different biosafety guidelines. But unfortunately, we don't have the guidelines separately for this plant system, expression in plant system. That is the reason that there is a lot of pitches for production of these proteins, recombinant proteins in plants. Otherwise, proteins you can produce. It's a very good bioreactors.
So, since you are also in other round of the table, so like WHO has released the oral polio vaccines, and recently for the SARS-CoV also Canadian companies released the vaccine for the human consumption from the plant-based, right? So what is the take in India? What is it preventing for the policymakers not to accept this technology or not to go forward for large scale utilization? Because why I'm asking this question, this will create a lot of opportunities for the agriculture students.
Right,
Why it has not been happening?
Yeah, that's a good thing. Like, but I don't know that. See, the thing is about the policy makers. They have to understand that the importance of these technologies, and there is a lot of opposition for even GM crops or gene edited crops. That's
Hello, good evening. Am I audible clear to you? Can anyone confirm from the auditorium whether my voice is clear?
5 minutes ಸ್ಟಾರ್ಟ್ ಮಾಡಿ ಹೇಳ್ತೀನಿ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದೆ ಅಲ್ಲಿ ಆಫೀಸ್ ಮೇಡಮ್ ಇದಾರೆ ನೋಡಿ ಕರ್ಕೊಂಡ್ಬನ್ನಿ Yes, good evening, all. Now we are starting our oral presentation in crop improvement thematic area. Now I request juries Dr. Mohan Rao sir, Professor, Department of Genetics and Plant Breeding to take the chair. And I also request Dr. T.H. Ashok, retired Professor, Department of Plant Biotechnology, GKVK, as a jury. So now I will call first speaker, Dr. T.R. Usharani. So here the time given is only 5 minutes plus 2. So you have to wind up within 7 minutes, including question and answer. Okay. So now I call Dr. Usharani. Start your presentation, Dr. Usharani.
Usharani, just a minute.
Yes.
Good evening, everyone. Before we actually start, I am told that there are 8 speakers in this session. And after the 8 speakers, we also have a speaker. So I request the speakers to adhere to the time allotted. It's 5 minutes plus an additional minute for discussion. Okay, thank you. Ms. Dr. Usharani, you can start your presentation.
Good afternoon, respected all participating in this symposium, international symposium. I'm here to present the work under the genome engineering for developing jointless pedicel in tomato cultivar Arka Vikas. So hope you see an arrow there near the pedicel. So that is what is the jointed pedicel. Covering more slides on that theme in the future slides. So what is this jointed pedicel? So in tomato, we see that the flowers are getting attached or connected to the main stem with this jointed pedicel. And this jointed pedicel is the region where the abscission region exists. So we know that abscission is the point, like, I mean, the very familiar word, which leads to the senescence and the leaf falling and all that. So, well, this jointed pedicel, so what are the other characters it does influence? Like, so it is also, if there is a jointed pedicel in tomato, so the flower stem remains attached to the harvested fruits. So you can see the pedicel portion getting attached to the fruit in the bottom. So that is how, like, that can cause the mechanical damage to the fruits while transportation. And on the other hand, you can see the jointless pedicel. In case if you are able to introduce this jointless pedicel, then the fruits can be harvested without the pedicel portion, and then the mechanical harvesting will also be easy. So with this overview, I would like to tell that abscission is very known phenomena, so which is separates the senescence or damaged portions, and that is where the zone of abscission occurs and the cell wall degrades, leading to the detachment. And in tomato, this gene has been well characterized. It belongs to the Matchbox family gene, and the targeted knockout of this gene can lead to the jointless pedicel. So here with this background, we set the objectives like, first of all, we need to construct the CRISPR-Cas vector for introducing the targeted mutation in this J2 gene, followed by agrobacterium transformation, molecular analysis, and the confirmation in the plants finally. So what methodology? Like initially the designing of guide RNA. So we know that in the CRISPR-Cas construct, the Cas9 has to be guided to the particular RNA in the host genome. So that region is selected just adjacent to the PAM sequence. So this guide RNA is targeting the J2 gene, followed by we need to clone the, so it may be around 22 MERS, like it will be cloned into the suitable vector, which is having a Cas region, the Cas coding gene, and followed by bacterial transformation, then mobilizing it into the agrobacterium for agrobacterium transformation, then agrobacterium transformation to the plant system. So whatever the tomato here, the system. So we will be transforming it into the tomato hypocotyl explants. Then, so we need to, just like any other transgenics, we need to confirm that whether the gene has been mobilized into the plant system as well. So this is how the vector, this is a 16 kb vector, PKAC401. So you can see the right border and the left border, a Cas, this is the Cas region, and this is where the gene has been cloned. So this, it's just a 22 MERS, this is the sequence, just like any of our primers. So these two will be joined together and it will be cloned in this region, followed by the scaffold will be there and the Cas9 sequence. So we select the guide RNA in the exon region of your the target. So here the target is the jointless 2 gene, and so this is how, like, this is the gene sequence, and we need to look into the features like GC content, the off targets it produces, and also the target score, and the target, how best you can target your gene. So with all that, you design the sgRNA targeting the gene, then the oligo complex will be formed just like our primer dimer, and that will be ligated to the vector. So this is the triper. First, the bacterial transformation will be done, and that bacteria will be the donor bacteria, GH alpha, with the helper bacteria. So it will be the vector along with the gene will be mobilized into the agrobacterium LBA4404. So this is the, we need to confirm the colony by colony PCR whether the gene has been mobilized, our sequence is there. So this is how we confirm using the U6 primers or the primers, and the sequence confirmation also needs to be done. And after this, once we mobilize it into the agrobacterium, the transconjugates, so there also you need to confirm your gene, at least with 1 or 2 primers. So these are the slides showing the PCR amplification in the agrobacterium. So this is how, once your agrobacterium is ready, you go for the transformation. So these are the hypocotyl explants, and you transform your transformants are ready. The transformation efficiency was around 18%. And this followed by the confirming these genes in the plant system as well. So with this, so further, when they come to the fruiting stage, you can always see for the looking for the phenotype whether there is a mutation in the particular gene. So with this, I thank you. To summarize, this is how the Cas9 vector, the construction is very important, and followed by transformation. Again, confirmation in your agrobacterium and followed by transformation. You need to confirm it in the plant system and look for the mutation in the gene. Thank you.
Thank you for your nice presentation, Dr. Usha. Can we have a couple of questions?
Thank you, Dr. Usha. It was a nice presentation. When it comes to pedicel, during the evolution of the species, it has been that the plant organ has been produced for achieving certain specific objective, which is beneficial to the survival, growth, development, physiology, biochemistry of the plant.
Not necessary. Okay.
So when you remove it, you are telling not necessary. Are there empirical evidences?
Maybe that we will have to check with the future studies once we get into the the phenotype, whether any changes are
Until
there.
unless empirical evidences are not there, it is not necessary, is scientifically unsustainable claim.
Okay, sir. We'll look into if there is
Yeah.
any cascading effect after transformation.
No,
and
you
get
can
into
look into fruit metabolome with pedicel, without pedicel.
We'll do it.
If we get any specific bands, a protein or something, we can blast against protein database and find out its functionality. Definitely it will be there.
We'll do it, sir.
Yeah, thank you.
Thank you, sir.
Dr. Usha, you said in order to ascertain the targeted mutation, you will have to wait till fruiting. I think it is not necessary for you to wait for fruiting. You can do it at this stage itself. You can do the targeted sequencing and find out the mutation.
Maybe for the phenotype, we have to wait for the.
Yeah, that's appropriate. Yeah.
If there are no questions, thank you, Dr. Usharani, for the nice presentation. We'll have the next speaker.
Thank you.
Yeah.
So next week's speaker, Dr. Arish D, scientist, ICRDF for Pune, Maharashtra.
Good evening, all. Respected dignitaries and dear participants. Today I'm going to the research work on genome-wide association studies in chickpea land races for seed yield and drought susceptibility index. We are witnessing the climatic change effect and also constant increase in the population is the need of developing the food increase in the food production, so that to address this constraint, molecular breeding is the main technique. Molecular breeding is the main technique to address this technique. And chickpea is the major is growing and also consuming. So in order to augment this, we conducted genome-wide association studies. In the chickpea, first we have lagging is that is from 6 decades, the productivity is constant. So, and also drought is the major constraint, which is able to cross yield loss up to 50%. And also some of the genotypes which are growing in India, they are narrow genetic base. The we have already available the we have whole genome sequence of the chickpea because of that is next generation sequencing platform. So it is easy to carry out genome-wide association studies in chickpea. So we are selected the 125 chickpea land races and also 4 varieties which are released under agriculture research system. And the experiment was carried out at IRI and Dharwad under 2 conditions, that is irrigated and rain-fed. In irrigated condition, we irrigated at 2 stages, that is a seedling and flowering stage. It is the critical stage of the irrigation stage to the chickpea. And we taken 2 parameters, that is a drought susceptibility index. It is the difference between the mean yield of the individual genotypes in irrigated and rainfed environment to that difference between the mean of the world genotype in irrigated and rainfed. And in GPS platform, we sequenced all these 129 genotypes with the 16K Illumina GPS sequencing, and we got that 16,983 SNPs. After filtering the that is eliminating the minor allele frequencies, we got 6,367 SNPs. In this 6,000 SNPs we used for molecular diversity studies to know how that SNP sequence data is beneficial or useful for the genome association studies. In this, the peak that is polymorphic information content was average with the 0.25, so that most of the half of the genotypes which shows the above 0.25 peak, so that these are highly beneficial and also these are diverse. And genetic distance is 0.33. In this also we got that is half of the SNPs were more than the 0.33 genetic distance. Genetic distance is mainly indicate the dissimilarities of the genotypes. And linkage disequilibrium. To know the co-segregation of the genotypes, we calculated the linkage disequilibrium. For whole genome level, it was around 0.14. And to estimate the relatedness between the among the genotype, we carry out the kinship and PCA. Kinship is mainly to know the similarities. This is red line indicate the correlated genotypes, and yellow indicated the uncorrelated genotypes. And also genome-wide association we conducted individually using the GUPIT platform in the R environment. We used the farm CPU because it considered both random effect and fixed effect. To eliminate the false positive, we consider this approach. And also to select the significant SNPs, we consider that 1-for-1 correction at the level of 1%. So for both seed-yield and DSI, we got 10 SNPs which are significantly associated. These are the Manhattan plot for DSI and seed-yield. For seed-yield, we got SNPs only for the rain-fed condition. And after that, we taken the that is 100,000 base pair upstream and downstream region to identify the mutative candidate gene which are associated with the significant SNPs. And this we blasted with that is all the mutative candidate genes. And after that, the mutative candidate gene identification, some of the SNPs like ubiquitin protein ligase, which is involved in the ubiquitination, is the most significant SNPs which can be used in the future breeding program for molecular breeding purpose. Conclusion, significant SNPs, what we are identified, and also some of the SNPs are localized in the candidate gene. These genes can be validated and further used in the molecular program. Thank you.
Thanks, Harish, for your presentation. We can take quick questions, if any.
Thank you, Dr. Harish, for a nice presentation. How are you quantifying the drought tolerance?
Quantifying, sir?
Yes. Because only then you can go for marker mapping and all, no?
Yes, sir.
First we have to quantify. Definitely drought tolerance will be in gradient.
Yes, sir.
Yeah.
Actually, we taken some of the literature, sir, based on the that
there are
literature.
standardized
Yes,
protocols.
yes, sir.
Okay, thank you.
That in chickpea.
I have a question. Did you look into the putative functions of those candidate genes?
Yes, sir. some of the genes were that is ubiquitination, and also some of the growth related genes also we identified, sir. But I didn't mention yield and yield related traits, sir. And among that, we identified 63 SNPs which are identified, and almost 36 putative candidate genes, sir.
But you indicated 6 SNPs associated with
Yeah,
yield, right?
yes, sir. We mentioned only DSI and seed yield, sir. We took dash to 50% flowering number of parts per plant in my research study, sir. But
your focus on identifying
Identify,
drought
yes.
tolerance,
Yes,
right?
sir. Yes, sir.
Yeah. How many SNPs were associated with?
12 SNPs which are
Which you did
putatively
not make a
identified.
mention.
Sir,
Did
yeah,
not mention,
yes,
yeah.
sir. Yes. That I mentioned, sir, there in the. Yes, sir. That is only, sir. Actually, I taken that is for any correction 1%, sir. For that ubiquitination, it is exceeding the 0.5%, sir. So it is more, and also we can validate and we can use it. Sir.
It is present in both the. So technically, even though it is showing association or linkage, it should not be taken for granted, because ubiquitin means universal. It will be there in.
But
It is having fundamental housekeeping role in running the physiology of the plant.
Yes, sir.
Therefore, just look at it and you can explore, dig out the literature and come to some logical conclusion.
Thank you, Dr. Harish. We'll have the next presentation.
So thank you, Harish. Next speaker is Dr. Ratnakar Shetty, Assistant Professor, UHS Bagalkot.
Respected dignitaries, this is my research. It is assigning the genomic regions for self-life and other traits in South Indian accessions of Mangalore melon through the association mapping. So Mangalore melon is nothing but Mangalore Sautekai or Mangalore cucumber. It has various names. It has been called in the different South Indian state. In Andhra Pradesh, it will be called as a dosakaya. It is distributed majorly in the South Indian content states as well as the Northeast Indian. It has various uses. It mainly used for the culinary purpose, and it has very nutritional. It has the antioxidant minerals rich in the coat, and it has also medicinal property like anti-cancerans, and also it has the antioxidant. Another important aspect of Mangalore melon is it has the longest shelf life. It even though it has the smooth surface, it belongs to the family, and the ash gourd and pumpkin, it has the hard thick coat. But the Mangalore melon or Mangalore Sautekai is as the thin and smooth skin, even though it has the high shelf life. The major objective of this study is identification of the marker linked to the enhanced shelf-life and fruit trait through the association mapping. For that, we have made the collection of South Indian 6 states, Kerala, Karnataka, Telangana, Andhra Pradesh, and Goa. Total, we have collected 80 accessions along with 2 wild accession in Kerala. And we have conducted the field experiment for these 2 seasons, included in the augmented design. And we have observed there were a lot of variability in fruit size, shape, and color. We also made the principal component analysis in that we have got the 5 groups, and also we got the Waltz method of clustering. In that also we have got the 5 groups in there, and conclude that they have been grouped based on the location where we are collected. Then
the self life is the main important traits in the Mangalore melon, and we have with the observation taken has practiced by the farmers. It has been hanged over the roof by banana fiber, and we have taken the observation on day basis for decaying the lot of variations. So the self life is ranged from 60 to 300 days. MS6 lowest self life, and MS30 is the highest self life, 300 days observed. And since the Mangalore melon is an underexploited crop and genetic limited, for that we have the depending on the other related like musk melon and the transferable musk melon SSR markers and ESTs. Total 84 markers have been used, out of which 84 have amplification, and we got the amplification, and it has been used for the genetic diversity analysis. I constructed the pediatric trees using this genetic dissimilarity. In the Infinity, we have got the 3 clusters. The first cluster has the we have got the 3 clusters. In the first cluster, connected tree was constructed with 3 clusters. In the first cluster, we have 3 Kerala accessions and Karnataka accessions, and it constitutes the 46 accessions. And the second cluster, the Karnataka and Andhra accession, the last third cluster, which is represented 3 accessions, which are Andhra Pradesh and the Tamil Nadu. And we also made to know the genomic constitution of the Mangalore melon. We constructed the population structure, and also we created the Q matrix for the association analysis. In this, we will that it has 2 parental ancestors. One among them is agrestis. The Karnataka and Kerala accessions, which have the wild melon agrestis as the one of the parents, and the another group, which is Andhra and Tamil Nadu accessions represent, they might have the another ancestry, which may be the Makua. It has to be confirmed by using the Makua as the parental in the genotyping. And we have made the association mapping using the TASL3 and 8 markers linked to the 12 different traits, which changing the phenotypic variance 10% to the 39%. Surprise at the 1% probability level. Surprising the self life, 2 markers are linked to the self life, EMS, ECM 181, 182, and SSR, which explains the phenotypic variance of 18 and 27% respectively. And we also we have published the gene self-life gene expression, the food ripening gene expression by using the ethylene biosynthesis pathway. We have used this 9 genes, out of which 4 genes were expressed for the biosynthesis pathway of the ethylene. In the Mangalore melon, this biosynthesis pathway was very low compared to the musk melon at 180 days of harvest. So expression of fruit ripening related genes in the Mangalore melon were significantly lower than the cantaloupe melon at the 180 days after the harvest. Finally, the conclusion, the summary and the conclusion, we have made the potato, we have identified the potato for the self life and other fruit traits, and 2 SSR markers which have linked to the self life will be used for the marker-assisted transfer of self life genes in the cantaloupe through the marker-assisted intraspecific hybridization. And also the candidate gene, which are identified, they are useful for the enhancing the life of the self life of the musk melon. So we have concluded the Mangalore melon is one of the promising genetic resources for the enhancing the self life in the melons. So I will acknowledge my work to it is funded by the Premnath Agriculture Science Foundation, Bangalore. I acknowledge him for the financial assistance. Thank you. It's the genetic diversity which is observed in the crop. Thank you, sir.
Thanks, Ratnakar, for the presentation. Invite questions from the audience.
Dr. Ratnakar, you presented two studies. One was the association mapping and then expression analysis. Is there any link between these two studies?
Yeah, we know the self-life is the potential trait in the Bangalore melon, but why they are high
No,
self-life?
You did association mapping and you did expression analysis. Are those genes were ones that you could map, or those genes are different and association mapping is different?
The genes in the expression, they are the ethylene synthesis, biosynthesis, but the marker linked to the self-life, they are the SSR markers. But these markers have to be validated in the biparental mapping population.
Okay, understood. Second question is, you did phenotyping and wherein you have shown the self-life ranging from 6 to 210 days. Did you maintain the same storage condition while, and the second thing is, what was the age of the fruit while doing the phenotyping?
After immediately harvest of the fruit, we have hanged the every day, or whenever the fruit were decaying, we'll take that as the last day of that shelf life. And we have continuously, it will start from the for example, it is the Kharif season, or in the summer, it will May onwards, we started the harvesting the fruits, and it will immediate on 8 days, all the genotypes are harvested. We have hanged in the roof, in the laboratory only. They are containing the open room temperature. So it has continuous season also in the farmers of our coastal, even Malnad region. They are harvesting the fruits in summer, and they are used that fruit for next year season. Till that they are using. They have great potential in that sector.
They are keeping for a long period to use as a vegetable.
Yes.
Is there any studies on how the mechanism of dehydration is avoided here? Because otherwise it will dry. So the skin must be having mechanisms to avoid the moisture to go out. Any of your marker linked to that?
The is compared to the other cucurbitacea crop, it has a skin. The structure of the skin is very complex. It means they have the more potash. We have studied the nutritional analysis. We have observed they have this coat will have the more potassium as well as the other antibiotics also. So the have the significant correlation. It is around for a period of 1 year. It will lose. There is the marginal weight loss for 100 to 200 grams itself. It weighs around 2 kg fruit, but the loss of the water over a period, it will be only the 100 to 200 grams. That's all.
No, but have you analyzed the water content in the and after a year in that one? So that will tell you how much moisture has gone out.
The fruit is full of 97% of water itself.
Yeah.
The initial weight we have taken at the harvest, at the decaying, we have taken the initial and final weight. The percentage change in the weight also we have noticed.
My only question is the preservation mechanism must be, it is avoiding the water to go out. So you may have any marker or whatever it may be for that. The skin must be having some mechanism to avoid the water to go out.
There is such whatever the comparison with the muskmelon and this in the Mangalore melon, it is very low as that of that compared to the muskmelon. Muskmelon is within they have the very fast ethylene synthesis. As a result, there will be ripening. But here there will be the fruit ripening is very slow because of this ethylene synthesis mechanism. It's very slow.
Maybe it is same in pumpkin and as well as this one. They have a lot of waxy coating also on the surface of the skin.
But difference is pumpkin and ashcot, they have the hard thick coat, but it has a smooth one. Which, the coat is very smooth. We can because of that it has the major vegetable and is very good self-life to
for the transfer of the gene to the musculum.
But have you measured the thickness of the skin at the end of the storage period?
There is no change in the skin thickness.
Okay.
It will remain same.
Okay, one quick question, Ratnakar. Is there any change in the fruit constituents during this period of storage? And is it only the decaying process that you're looking at? You are measuring shelf life.
Shelf life.
Shelf life, is it measured only in terms of number of days taken to decay? Or are you other fruit quality parameters as well?
During the ripening or the shelf life, we are taking the color change of the skin. It will be taking the, especially the fruit will not get the any much color change. These striped one, which are of, they have changed green to the.
Listen. Now the quality of the fruit contents could change over a period of time. That should also be studied, because the fruit may look healthy, but the contents may not be edible after a set period of time.
No, that not that aspect is studied, but we have observed there is no such changes. But the taste, whatever cooked after 1 year also, it gives the same taste as that in the 3 months old. Nutrition status also.
Yeah. You should have mentioned what are the parameters that were studied at 180 days, which is not indicated, because you're talking about shelf life, restricted only to the shelf life parameters or quality parameters of the fruit.
For
Okay,
that only we have the gene expression analysis was done at the 180 days there. During that time, we have also analyzed, selected samples representing our survey, 3 fruits. So for that, we have made the nutrition analysis at 3 stages. One is seed, flesh, and also skin. They have the differential antibiotics and the carbohydrates. We have measured a lot of information coming out. They had to be published.
Okay. Another one is, you said EST SSRs were used from muskmelon to study in your crop, isn't it?
Yes.
Okay. Were those EST SSRs specific for a particular trait?
Not such. We have collected the genomics.
Only 2 of this kind can be preserved for a longer period. Have you come across from your experience, if there is any little damage, it's going to be deteriorated with an idea that the skin must be having antimicrobial activity. If there is any damage inside, any bacteria, fungus may enter and destroy.
This process will be slow, sir. There will be the damage. If damage, it will not deteriorate so quickly, sir. It takes its own time, sir, to take into.
It was earlier studied a lot of the skin has got a lot of antimicrobial activity.
Yes, sir.
That's why it is not allowing to deteriorate. That's why it remains for a longer period.
The insect which are infected in the early stage, the fruit will get affected. If the fruit grows for some attaining some stage, even though the insect attack, it will not harm the shelf life or the deterioration, sir.
Okay. Okay, Dr. Ratnakar, we'll stop at this stage. Maybe we can discuss a little
Thank
later.
you, sir. Thank you, sir.
We'll have the next speaker, Dr. Nagesh, please.
So thank you, Dr. Ratnakar Shetty. So next speaker is Dr. Raghavendra Gunaya, Assistant Professor, UHS Bagalkot.
Good evening, everyone. It's always a pleasure to come back to school and present in front of our teachers as well as the student. Pomegranate has been considered as one of the highly nutritive and medicinally valued crop. But when it comes to the perspective of farmers, it has been considered as one of the rapidly adopted crop by the farmers. So it has been like there is an increase in 133% increase in the area and 289% increase in the production by the farmers in a short span of just 8 years. It's mainly because of it's a hardy crop which can be grown in low fertile soils, as well as it is drought tolerant. At the same time, gives high returns for the farmers in a short period of time. So India is the largest producer of this pomegranate, and major growing states are Maharashtra, Gujarat, and Karnataka. This should be Karnataka. So of course, Karnataka was second in the position. Since last 2 years, it comes down to third position, mainly because the intensive cultivation of this pomegranate has led to eruption of multiple pests and diseases. Among them, the major diseases are the wilt and the bacterial blight. So I'm working on bacterial blight. So bacterial blight is caused by Xanthomonas citri Pathawara punicae. Previously, it was called as Xanthomonas axonopodis Pathawara punicae. It infects almost all parts of the plant, starting from leaves to the stems as well as the fruits. Currently, so it causes around 60 to 80% yield losses. So many times it has made the farmers to change the crop. So currently it is managed by integrated approaches like field sanitization, especially copper-based chemicals, as well as antibiotics and also some biologicals. However, it has not been efficiently managed, and so the recent sequencing has led that the genome has already has some resistant genes for the copper as well as the streptocycline resistant genes. So the only method of the most viable method of developing the management of this disease is the development of resistant cultivars. However, most of the all the present cultivars are susceptible to the diseases. The only tolerance has been seen in some of the wild genotypes such as Nana and Daru. So, but they are associated with a lot of undesirable characteristics, like they produce a number of small fruits with, and we also tested them in association with NRC pomegranate, and some of the derivatives of Daru have shown tolerance up to certain days, like 35 to 50. To use this either in the resistance breeding or else to convert these susceptible elite into resistance, we may have to go for biotechnological methods of breeding, either genetic engineering or the gene editing. However, next. However, so we went for, however, the crop remained to be an orphan with respect to genomic resources. So the genome sequence was published only in 2018, and we started working on that one with two approaches. The first one is identify bacterial pathogenicity factors and then identify the targets in the host so that we can develop the resistance. And second one was identification of candidate genes through dual transcriptomics. The first one, the major so from the previous Xanthomonas and other host studies, it has been proved that the transcription activator like effectors are the key pathogenicity genes, so which mimic host transcription factors. They enter into the nucleus of host and they bind to the promoters of the certain genes, which make them susceptible. Mostly they bind to the susceptible genes, as Dr. Narayanan was mentioned in the morning class, lecture. So those are the mostly the sweet genes. Once they bind to the sweet genes, they utilize them for their susceptibility. So we thought of using identifying these tail genes as well as their targets. However, these tail genes are made up of mainly repetitive variable domains, which is difficult to sequence using short genome sequencers like Illumina. Hence, we went for long read genome sequencing. Next slide, please. We went for long read genome sequencing using sequel, and we sequenced approximately 5.2 MB of the genome sequencing with an highest coverage of 342x for the first time, and it also showed around 99% genome completeness. Okay, 98.87% genome completeness, and we. I'm not okay. So we around 4,757 genes, out of which 4,263 were protein coding genes. Among them, 17 were the type 3 secretion proteins, which are involved in transferring these tail effectors into the host nucleus. And we also predicted two tail effector proteins. Okay, so these two tail effector proteins were having no, I'm not. These two tail proteins were having 17 residues. I'm not changing. Okay, were having 7 residues and 27 residues. So these repeated variable domains bind to the nucleotides in the effector binding elements of the host promoter genes. So based on this preference, we identified 5 targets for each tail protein, and further, next slide. Further, we subjected them for tail and effector binding analysis using molecular docking, and we found that among those 10, we selected 5 genes with low RM and the score low affinity binding scores. So these are the 5 genes which were. So next, we confirmed their expression analysis using. We confirmed their expression analysis using QRT-PCR. To our surprise, we found that the first gene, a BTB match domain contained protein, which was highly expressed in the tolerant genotype rather than the susceptible genotype, where we expected the opposite of it. It mainly mediates in the ubiquitination and subsequent proteasomal degradation of target proteins. But the host also convert these susceptibility genes into the resistant genes. We are studying the role of these genes. So, but the 2 genes which are highly lower expressed in case of the tolerant genotypes, whereas highly expressed in case of the resistant genotypes, we are analyzing them. Those includes, one of them is the sweet genes as well as a transcription, the mitogen activated protein kinase, and a gene transporter gene, which is in response to salt stress. So we are analyzing like what is their role in case of bacterial disease resistance in case of pomegranate. Apart from that, we also started analyzing the dual transcriptomics. So wherein we sequenced the transcriptome of pathogen infected leaf samples from both susceptible as well as tolerant at a very high depth sequence of 70 million reads, and they were assembled to their respective reference genomes of both bacteria and the pomegranate genome. And the data is still under analysis, but we found that in case of differentially expressed genes, we found it. Most of them are involved in, we found that, so surprisingly, we that the genes involved in oxidative stress responsive were low expressed in case of the tolerant genotype, which is indicating that there is a late defense responses in the tolerant genotype. It is the thicker cuticle in the cell walls, which observed in case of tolerant genotype. Apart from that, we are also analyzing the expression on a sugar transporter gene, which is sweet gene, which is also very well studied in case of rice, and their role has to be defined in the future. Thank you.
Thank you, Dr. Raghavendra Gunnaya, for your presentation. Questions from the audience? Yeah.
So, Raghavendra, you did a dual transcriptome.
Yep.
And I could see there are only 2 of the tail effectors in your sequencing from the pathogen side.
Yes.
So because Xanthopus species know about 18 tail effectors are secreted. What is the problem? Is the DNA extraction or any problem with the inoculation?
So no, we identified around 6 tail effectors. Out of them, 2 are complete tails, whereas the another 4 are truncated in one or the other way. So a parallel study was done by NRC pomegranate. They got the complete 6 tail effectors. So we are suspecting that there may be some problem with either the assembly or sequencing. So we are resequencing them only those genes through cloning process.
No, my question is whether you enriched the pathogen genome after infecting the plant.
No, not really. So nothing was in. Just we went for high depth sequencing so that we also get more of bacterial.
So in that case, you will be high chances that you will miss a lot of genes which are not expressed, right? Because the amount of bacterial count will be very low when infected to the plant.
So the only reason is usually like 30 million reads is sufficient for any plant transcriptal sequencing. We went for high depth sequencing.
No. Million reads is just for the bioinformatic analysis.
So another
right?
one is
just to get a realistic picture. When pathogen is infected to plant, you need to have a proper enrichment of the data, or else your old data is a false positive. It will generate.
So just to check about the bacterially expressed plants, so we have sequenced the RNA extracted from the culture itself. That will act as a control to efficiently looking at all the genes, or partially we are getting them. So that analysis is still underway. So we have sequenced that one control also.
Dr. Raghavan,
sir,
one quick question. Identifying several differentially expressed genes.
Yes, sir.
Between susceptible genotype and tolerant, right?
Yes, sir.
Did you also do the experiment without infestation, infection with infection?
Yes, sir.
Okay,
so we have the control.
Second. If
yes,
that
sir.
is the case, when you identified a group of or a plethora of differentially expressed genes, who do you attribute them? Because you are taking two different genotypes.
Yes, sir.
There's another one integrated to that question is, how do you attribute whether because of infection they are differentially expressed, or because they are differentially expressed infection is prohibited or controlled?
Okay, sir.
So is it a cause or effect?
Things I'm going to tell. First one, we have always used control without any infection. So in both the genotypes, susceptible as well as the tolerant. So the genes which are highly expressed after pathogen infection are the effect, not the cause. That's one clarification. Then shortlist those 696 genes is. So we have done two things here. One is one way we are targeting only the tail targets. So one end in silico docking, we have done shortlisted some candidate genes. So if those candidate genes are also there in the differentially expressed genes, so we are mainly targeting those genes as the potential candidate genes. So further, we are sequencing them to find out if there is any polymorphism. Then we are going to ascertain why there is a susceptibility. Yes, sir. They are absolutely specific to pomegranate.
You have mentioned some of the B2B.
Yeah.
So are you going to work all those different genes?
Now we are shortlisted around 9.
Okay.
So now further we are going to go them. So in vitro protein DNA association studies. So maybe of those 9 genes we may come down to like 2 or 3 genes, which will be using them as the candidate genes for further gene editing.
Those genes are tolerant mechanism, right? They're attributing towards tolerant.
So right now most of them are associated with susceptibility rather than the tolerance.
Okay. So if you controversially, in contrast, if you could be able to identify some of the debucquidinating enzyme, if you target them for resistance or susceptibility, that will be fantastic rather than looking at that particular gene, because that is the mechanism reverse the susceptibility or resistance or tolerance.
So initially we thought of that. Problem with the wild cultivars is they shows resistance only to certain period of time. So after that they also become susceptible. So we thought that better to target the susceptibility genes rather than the resistant genes. So that's why we are moving in this direction.
Okay, Dr. Ravindra, thanks for your presentation.
Excellent talk, Dr. Raghu. So I have 2 quick questions. Number one, how many sugar transporters have been annotated in pomegranate genome? Number one. Number 2, are there any homologs of sweet 11, 13, and 14 which were found in rice, which are the tail effectors?
Yes, sir. That's an excellent question which we are answering right now in our research. So from scanning the pomegranate genome, we have identified 15 sweet genes. So out of 15 sweet genes, only 2 genes were upregulated during bacterial blight infection. So that's one. And surprisingly, none of these two genes are homologous to rice sweet genes. So they're still studying like why there is, whether they are totally different genes or how they are related ancestrally.
Okay, thank you, Raghvendra. We'll have any
Thank you,
further questions, probably outside this hall, any discussions further. We'll have the next speaker, and after that, we'll have the invited or the lead talk.
Okay, next speaker is Dr. H. Kumar Swami, scientist, ICR Indian Institute of Oil City Research, Hyderabad.
First of all, very good afternoon to. Okay. Illu change ಮಾಡ್ಬೋದಾ? Fine. Okay. Very good afternoon to the big audience here. And nothing can be more heartening and pleasant than appearing before my own teachers. My guide T.K.S. Gowda is there, Dr. T.K.S. Gowda. My beloved teachers are there, Dr. Ashok, Dr. Mohan Rao, and so many teachers within this auditorium, without this auditorium. To name a few, Professor, I think is no more, Professor Uday Kumar, Physiology, and Dr. Chandrayappa. Having said this, I am here to present before this task given to me by the Plant Variety Authority, PPV-FRA. They gave me a task to develop a method, scientific method, to rule out it is not a variety, and also to ascertain, yes, it's a new variety. Why it is happening will be there behind birth of this objective. Yeah, you can change it. Okay. Actually, sesame is a wonderful crop, and its cultivation history is known since 2,800 years, both in the eastern epicenter of civilization, that Mohenjo-daro, also western epicenter, that is Egypt and Rome. And this has multiple utilities, name it cosmetic, pharmaceutical, industrial, culinary, you name the need of there, the sesame will stand in the front line. However, the hiccuping issue is here. The seed yields are stagnated for very long time. I will tell you, per hectare, it will be 400 kilo only. That is why no farmer is taking up this sesame cultivation. In order to circumvent this situation, greater number of varieties are being released. In a year, 10 varieties, 20 varieties. But you also know, variety release publications are part of the criteria for recruitment, assessment, selection, and all this. So in this race, farmers should not be further confused because they are already discouraged due to stagnated yield level. Now varieties are coming in different names, whether they really contribute to any trait, unique trait they are claiming, or enhancement of seed yield or oil yield. So Government of India has a PPV-FRA and also variety release committee. They gave me a project. In that, my task was to develop a molecular evidence-based technology for ascertaining distinctiveness of each variety, claim it to be newly developed. So methodology is not any unique, methodology is not unique in any way, except one thing. I screened 1,500 microsatellite markers and 50 I could fish out which are able to distinguish varieties. Released varieties I have taken. Totally, there are 96 publicly released varieties in sesame. I have taken 30 of them so far. It is a 6-month-old project. So far, I have reached 30. I will be completing all of them. And I developed a variety marker matrix, first in the world. In no variety, nobody has developed. And this also is a technically demanding procedure. Simply, we cannot get any marker and distinguish varieties like that. Here, as an illustration, I am showing before. Better, I will not touch this. You operate. Next slide, please. Yeah, as an illustration, I'm showing here. There are 10 different public release varieties. These are all. The DS series are from Karnataka, the Harvard Sesame series. You see there, one marker here I am showing, that is SIM 123 marker. To search SIM 123, it is not easy. I have to analyze thousands of markers. And after we can find out this. And here, for example, this is distinguished, this is distinguished, this one and all, these are also distinguished. But here you see, they are claiming publicly released varieties, but vigacity is same. Whether genetic purity is lost, these are all the subsidiary questions and corollary doubts. But my objective here is to say, this is able to distinguish this, and this, but not this. Next slide. So in that situation, yeah, press it. But time loss should be taken into consideration. After minusing these delays, 5 minutes. It's cumulative 5 minutes, nahi, effective net 5 minutes, please. 30 varieties and 50 markers. I have taken in the entire matrix, the top left corner portion I have taken. I will explain in relation to previous slides. For example, SIM 123 could distinguish these 3 varieties, but failed to distinguish this. So in combination with SIM 114, you can see here it got distinguished. So this marker either alone, singly, or in combination with 2 or more can distinguish all the 30 varieties studies so far. Okay. And marker variety matrix is a starting guide for selecting marker for DNA fingerprinting. And if somebody want to find out for new variety, claim it to be new variety, whether it is really new or not, no need to start reinvent the wheel. It can act as a guide. From here, one can commence. Next slide, please. Yeah, here is a tricks actually. Okay. Whenever we use markers, SSR markers, I will tell you one more thing. In spite of all the SNPs, indels, sequencing, resequencing, genotyping by sequences, nothing can match with the SSRs because of their easy to use and easily observable scoring techniques. See the marker, you see, for example, this is one variety, this is another variety. Every whole genome may be same except this portion. If the marker what we are using is lying in this portion, definitely it will be a functional marker also. But if the marker we are using is here and there, even the marker is showing these 2 varieties are same, but they may be actually different. Okay, which in fact is a distinct one. So in this context, until unless we sequence entire genome from end to end, base by base, it is difficult to say same. I will tell you, it is an underscoring statement. It is difficult to say different because if one difference is there, we can say 2 are different. But it's it is easy to say different, but difficult to say they are same. Telling 2 varieties are same based on set of marker is a wrong statement. But even one marker is enough to claim these 2 are different. Okay. Based on this, I want to say that marker even today, whatever may be the advance in the technology, DNA technology, is a really a handy tool. And what the matrix I developed is a starting point. And any new varieties developed, if it is difficult to be distinguished, then the only way is to analyze in the background of their parents. If they are hybrids, against the parent. If they are variety based pop, release all the release rates and their parents. Even if we want to develop foolproof DNA fingerprinting, then large number of SNPs and indels are required, and it cannot be performed in any small laboratories. Thank you very much. I concluded my presentation.
Thank you, Dr. Kumaraswamy, for the nice presentation.
Welcome, sir.
We'll just take one quick question because we have the lead speaker waiting to present his talk. Just one question.
Yes. Thank you, Dr. C.S. Prakash, making my job easy.
Yeah, we have no questions. Probably I'll discuss with you a couple of things a little later.
Fine, sir. Thank you.
I'll hold my questions back. Yeah. Thank you. Thank you, Dr. Kumaraswamy.
Thank you, one and all, for your.
Yeah, it's an honor to have Dr. C.S. Prakash, one of our alumni, and also welcome, Dr. Prakash, for this international conference. Sorry for keeping you waiting. Dr. C.S. Prakash, one of our alumni, very, very distinguished alumni from US Bangalore. More will be said about Dr. C.S. Prakash by one of our colleagues, Ms. Preeti. Yeah. Dr. Preeti Singh from IHR. Yeah.
Yeah, I'll give a brief introduction about our speaker, Dr. Channa S. Prakash. He is Dean of the College of Arts and Science at Tuskegee University, Alabama, USA, where he is also a professor of crop genetics and biotechnology. His research expertise is on genetic improvement of food crops, which are important to developing countries. His lab was among the first to develop genetically modified sweet potato and peanut plants, and also initiated genomic studies on peanut. He served as an editor-in-chief of the Journal of GM Crops and Food, published by Teller and Francis. He's also winner of the prestigious 2015 Ball of Cast Communication Award, and He has been actively involved in enhancing the societal awareness of food biotechnology. He was also recognized by Huffington Post as among the top 30 social influencers in biopharma and biotech. So from this brief introduction, we all can understand his immense contribution in the field of agriculture. We are very happy to have you, sir. So now we can start.
Thank you very much for the nice introduction. If you could please turn the video on for me. I'm unable to turn it on because it's been blocked. So audience could see me speaking. And so I'll just go ahead and start sharing the screen. So I hope everybody could see my screen. Okay, good morning. Namaskara. US Bangalore alumni. ನನ್ನ ಭಾಷಣ ಕರೆದಿದ್ದಕ್ಕೆ ನನಗೆ ಬಹಳ ಸಂತೋಷ and so ಎಲ್ಲರಿಗೂ ಧನ್ಯವಾದಗಳು and good it's a good morning for me here. It's just at 8 o'clock in the morning. So I thank Dr. Veena Anil and Dr. Ramanjani Gowda and all others for including me in this panel, in the seminar speaker. And it's a real pleasure for me to talk to my alma mater and share my knowledge, give a very general, broad overview on this very emerging area of gene editing with tremendous potential in advancing Indian agriculture. And to put the context of gene editing, we plant breeders think of this as one of the long series of techniques that we have used to breed crop plants. As you all know, our food crops have evolved. All of our food crops have evolved through domestication and slow selection. And only recently we have started using more scientific breeding, mutagenesis, hybridization, and for more recently, the GM crops. And as you can see, I've just listed a few of those techniques here: traditional breeding, mutagenesis, and then with the advent of biotechnology, variety of tools such as RNA interference, transgenic technology, and gene editing that has been in the vogue for just about 7 or 8 years now. And the GM crops have made an impact in wherever they're accepted, including in India, where we grow BT cotton. And they are primarily been released by private companies, and just mainly two traits, that is essentially insect resistance and herbicide tolerance. And in contrast, when you look at gene-edited crops, I believe it's going to have far more impact than GM crops for a couple of reasons. One, gene editing involves a minor tweaking of the nucleotides, unlike a transfer of foreign genes, which was subject to a lot of regulation and a lot of misperception from the public and the policymakers. While gene-edited crops are more like mutagenesis that we have been using, either chemicals or radiation, but in a more precise manner. And this started with the discovery of one type of gene editing called CRISPR-Cas technology by Jennifer Doudna and Emmanuel Charpentier. And many of you may recall that 2 years ago, they got the Nobel Prize for that. And this has a really very transformative technology that is making a big impact in biomedicine, in gene therapy, and a variety of other tools in biomedicine. And so agriculture, for the transforming crops and livestock, we benefit from all those emerging technologies over on the other side of the biomedicine. Essentially, how gene editing works is that when a cell is transfected, in this case, a plant cell, with a guide molecule that is complementary to the gene sequences to be altered, and then use a DNA cutting enzyme, those guide molecules, when they pair with the corresponding sequences and end up changing those sequences while the DNA replicates. That's in a very simple way to illustrate. It's kind of, you can think of this as doing a text alteration on your smartphone when you make a mistake. you use using the editor, and it's very similar to that. We literally change the language, the alphabets of life here, and but it still has profound implications. And I just wanted to show a few examples very quickly. Many of the examples I draw are from tomato, which we can easily relate to, and is one of the crops that easy to transform to. And here you see a gene-edited tomato on the top, which is susceptible to powdery mildew, and the bottom, where the changes have been made, is with a tomato gene, the leaves of tomato showing a resistance to the powdery mildew. And again, this is similar work that has been done in rice. I know US scientists, including Dr. Shailaja Hittalmani, have done, and Dr. Shashidhar have worked on bacterial blight resistance in rice. And now Chinese scientists showed that that one could easily develop resistance to this deadly disease that affects rice in all the rice-growing regions of the world. And one other trait that has been shown to be changed due by gene editing is the slowing down of tomato fruit ripening. And as you can know, in India, when tomato season comes, there is a glut of tomatoes, so much so that farmers don't get any value for their tomatoes. Then they simply throw those tomatoes on the highways. But if you are able to slow down the ripening of this tomato, like we see in the bottom panel here, and then we could keep these tomatoes for a long time. We could harvest it when they are green but not fully ripened around this stage, and then because they are still going to be resistant to bruising, we can transport them to longer distances, and we don't necessarily need cold storage to keep them for a longer time. And so like this, there is a tremendous potential for us to alter all the climatic fruits and vegetables that we grow in India today. And another application of gene editing is to improve the nutritional value of our croplands. Here it shows lycopene content being increased in tomatoes. And in fact, just a couple of days ago in the United States, they approved one of these tomatoes with a very high antioxidant content. And that, I think that was initially developed through genetic modification at Sainsbury's lab, but the similar alteration is being done through gene editing. And this is again just to illustrate an example of how we can improve the nutritional content. But gene editing is yet best in removing some of the undesirable content. As we know, we have neurotoxins. In our case of dal, we have cassava has cyanide, and so many of those undesirable are in our own laboratory here. We are working on removing allergens from groundnut, and those are the type of deletion type of traits are more important, more easily done through gene editing. And talking further along the nutritional improvement, here is a diabetes-friendly rice that was developed through gene editing to alter the starch quality in a way that it is more resistant to digestion and just makes it a more low glycemic index rice. And there's also example of increasing the seed size in genome editing, because genome editing today is still confined to changing a few genes, although multiplex gene editing is coming along. And so quantities, traits such as yield, which are controlled by polygenes, are not as easily amenable. But nevertheless, by going for certain important transcription factors that control many genes, and by changing that changing the regulation of such regulatory genes, we are able to even improve many of the yield traits. And those are just coming along. And almost every day I see papers coming along where they are now able to increase the yield, for instance, by affecting going after genes involved in photosynthesis, they've been able to improve the yield. And I'm quite confident that beyond disease resistance, beyond pest resistance, and beyond nutritional qualities, we will see application of genome engineering in crop plants directly relevant to yield. And one way that is achieved also through plant architecture. As you all know, the whole green revolution was based on bringing dwarf architecture to wheat, at CIMET, and later in rice through at Erie. And now they have recently done that even for maize. And here it shows an example where we can make dwarf plants by editing the genes related to plant height. But I believe one of the most important applications of gene editing is going to be in improving our crop plants to be more resilient to the climate. The current drought in many parts of the world, ironically, along with flooding that we see today in many parts of India. In my hometown of Bangalore, we had big floods last week, as you all know, but 1/3 of Pakistan is currently underwater. And so making plants tolerant to submerging and even drought and heat are going to be very critical. And that is where I think gene editing has tremendous potential. And just a couple other examples, going back into the nutritional improvement. This was banana that was done in India with metabolic engineering, where they showed a 6-fold high beta-carotene content through gene editing. And similarly, as you know, golden rice was initially developed with transgenic technology, but now it is being developed through gene editing by simply turning on some of the regulatory genes related to beta-carotene synthesis in the endosperm. And Japan has already released a super tomato that is edited for increasing certain compounds to help control the blood pressure when you eat it. It's called the GABA tomato. And who can resist this? Gene editing technology to make an improved beer. And this has been done in Australia by simply controlling the premature germination that barley seeds have in a way that they can improve also the malting quality of this barley. And so there are many, many applications, and in my brief time, I won't be able to go through, but a snapshot of this scene from a friend of mine, Shakil Ahmed, put that online in one of his papers, grain quality, stress tolerance, heavy metal accumulation, photosynthetic efficiency, root architecture as a way to improve drought tolerance, and shoot architecture as a way to improve productivity, and survival of submergence that I mentioned regarding flooding. And so a tremendous application, many, many different areas. And so gene editing is more precise, it's faster, but most importantly, it's not subject to a regulation as much. In most countries, including India, has recently passed a law that if you gene edit and if it's STN 1 and 2, which essentially means that it is a change of nucleotides and not involve any foreign genes, then it could be considered and regulated as conventionally bred crops, in so much so that it brings in opportunities for institutions like UAS and IIHR and all the ICR institutions and our agriculture universities to work on this technology and then release them, because you don't have to have big companies like Monsanto, Bayer, BASF to spend hundreds of millions of dollars to help to showcase the safety of this technology. So it's essentially like a conventional breeding, and so much so that you see there are literally hundreds of traits being developed all in all the labs all around the world, including India. And again, this CRISPR-Cas technology has many applications for basic research because you can knock out the genes, you can even replace genes. You could bring transgenic technology into this, and you can activate or repress the genes so that you can alter the regulatory mechanisms. and the newer technology of base editing that makes it more faster and precise, and epigenome modification. There's a lot of research coming along where the methylation of DNA can be altered. So, and again, to unrelease some of the regulatorily suppressed expression. And it's also being used in imaging in a way to study the localization of gene expression within cells, and so on and so forth. And as I mentioned, there are many countries now consider gene editing as classical breeding without, and that would not require the huge burden of regulation that we see otherwise for GM crops. And I'm really glad that India is among those countries that recently came up with this proclamation. So gene editing can do many things for Indian farming. It can enhance the nutrient levels of our crops. It can bring climate resilience, disease resistance, pest resistance, and it can improve the food safety and food quality of our food, increase the shelf life of fruits, vegetables, and even flowers, improve the oil quality, especially like, if you have a mustard with a lot of unpleasant odor in the oil, which is not really acceptable for us in South India, for instance. We can remove that. And castor oil is very productive, but it also has one of the most potent toxins, ricin, and that could be removed. Neurotoxins in case of dal. And so just a couple other things. I've recently come up with a book on this area, and so just wanted to plug that here. It's published by Springer Nature. And I just end, if the chairman permits it, I just have another 3 or 4 minutes. I would like to just show a short video just to show what Indian scientists think of gene editing. So if it's okay with you, sir, I'd just like to go ahead and show this.
Indian agriculture is facing formidable challenges, which need to be addressed urgently, keeping in view the fast-changing climate. Genome editing provides sustainable solutions and needs to be effectively used for introducing climate resilience in the newly developed crop varieties while maintaining their high yield potential.
For harnessing the full potential of new plant breeding technologies, India has adopted science-based regulations and has recently announced exemptions of genome-edited crops from biosafety assessment for the benefit of farmers. With this positive development, India is poised well for the next revolution in agriculture through the use of genome editing tools for crop improvement.
Gene editing technology is a game changer, which has the potential to revolutionize agriculture in terms of improved production, improved productivity, improved nutritional status. And today, we have a lot of research which is going on. Priority crops that we need to focus on are oilseeds, vegetables, pulses, fruits. We also have now a very well-structured regulatory framework, which is giving a special impetus to the researchers from industry, academia, and the startups, and giving them an opportunity to be able to take their research through translation to improved and excellent products for the market.
The recent policy guidelines declared by the Government of India on genome editing in plants has encouraged product developers in this area. Companies with know-how and skills to utilize these technologies can bring products to the market effectively. The opportunities are many: climate-resilient crops, pest and disease tolerance, plants that have increased yield and productivity due to changing their architecture. All these are possible and will make India globally competitive.
India needs to increase oilseed production to cut down on our edible oil imports, which are running into thousands of crores of rupees annually. There is a lot of scope for improving oilseed crops like soybean, mustard, and groundnut for disease resistance and nutritional enhancement using gene editing.
Gene editing, it enables de novo domestication of nutritionally superior and climate resilient wild relatives across species at a much faster pace, thus enabling their production and sustainability in agriculture.
The exemptions are in line with the global assessments that a trait will not be regulated if there is no foreign DNA. It's especially benefit for small seed companies in India to develop traits for local needs. It's an opportunity for India to be a hub for global seed production, for seed movement and trade.
Genome editing has a tremendous potential in breaking yield ceiling, enhancing climate resilience, and improving nutritional quality in crops. Realizing its potential, Government of India initiated work in this area 5-6 years ago. Several institutions of the country are already working in various crops. With the right kind of policy of the Government of India in place, I strongly believe that in another 2-3 years' time, the fast genome edited crop variety should be there in the field.
Well, I thank you all for your attention. And if you wish to learn, follow me and more about some of this exciting development that are happening in genome editing, I suggest you to please follow me on either on Twitter or Facebook. And I put it in the chat, my handle, it's called AgBioWorld. Or just look for Channa Prakash. And you should be able to find me online. Thank you.
Prakash, thank you very much for enlightening and also reinforcing the concept of science-based regulatory tool in the form of gene editing. You also mentioned about the huge potentialities of this tool in delivering or giving to the world edited crops like tomato, rice, barley, and so on. And thank you very much for your wonderful presentation. We now have time for questions from the audience.
Sir, I have one question which has been asked to the other speaker as well. When we edit a particular gene in a plant or an organism, what would be the relative effect on the other associated genes? Because many genes are interlinked together, and what will be the effect on other genes? Can we maintain the same, expression pattern, or it will be altered?
Right, that's an excellent question. Thank you very much, because in the this has always been one of the central tenets of plant breeding, whether we use mutagenesis or hybridization. You see, I remember when I was a student in UAS, we had a breeding program going on where tomato was very susceptible to root knot nematodes. And our tomato breeders there were trying to introduce the root rot nematode resistance by crossing with a wild tomato, like a Persicum pimpinellifolium. And while doing so, we were bringing many other traits, not just the nematode resistance, but many other traits. And it took many generations of back crossing to remove that. And so while the problem has always been there in plant breeding, that presence of unnecessary traits, and what we call this in genome editing is the non-target or off-target changes. So in the beginning, with some of the early versions of CRISPR-Cas and other related technologies, there were changes in the other areas, but they were minor. But as I mentioned, base editing and some of the more revised versions of Cas, we are able to reduce such off-target or non-target changes. What we do is, we just don't end with gene editing. The gene editing is just the beginning. And once we edit, we edit several different lines, and when they go through the same testing as all other plant breeding process, and we make sure that there are no surprises, that there are no undesirable effects of any gene editing. But so far, with some thousands and thousands of publications in this area, we recognize that such changes are most minimal with gene editing. To give you an example, if you just take a wheat or any seed and replant it again, they have noticed from 600 to 800 mutations are seen. We heard the speaker previous SSR markers. By looking at those markers, we can tell by scanning the whole genome that such mutations happen naturally. And when it comes to gene editing, you are just changing just primarily 1 or 2 targeted genes and almost 0 non-target changes. Thank you.
Sir.
Next question.
Yeah. I thought disconnected, that's why. Sir, Dr. C.S. Prakash, thank you very much for an illuminating talk on latest developed technology. Sir, my question is, for the past 25 years, we have reached from hit and run to catch and captivate. That means we can precisely target where the changes in the ocean of genome has to take place. With this technology, we are only dabbling with the proof of concept and developing tools and technique, achieving success of editing, but to harness it for the benefit of medicine and food, we need to understand the plethora of cascade of biochemical pathways. We need to have a map of biochemical pathways, their network, crop-wise, developmental stage-wise, and economically important part-wise. So based on your intuition, I just wanted to hear from you, how long do you think we would be able to harness this technology for the benefit of food and medicine?
Thank you very much. I think that's an excellent point. Gene editing can only move forward if we have a good knowledge of the genomics, the proteomics, the metabolomics, and all of these omics. And that's why my book was titled Omics and Genome Editing. And so you can only change the genes and edit the genes for those for which you have good knowledge of it. And so for India to move forward in harnessing gene editing and all the other newer technologies that are going to come as we move along, it needs to have a very strong basic infrastructure, promoting the basic research and understanding the mechanisms of in that. We must understand the biochemical architecture of that, and then only we could develop products that are useful and stable. And so I hope that the continued promotion of plant science and all other aspects of plant science, plant biochemistry, plant physiology, plant genetics would all move forward in a manner that India could harness from that. And to answer that question, I think it will go forever. The science we have seen, is continuously improves our quality of life. And if we continue to support science, it will benefit our technology. India would not be the 5th largest economy in the world today if not for all the science and technology that it has promoted. And Bangalore would not be the epicenter of the IT and the biotech that we see today if not for all the investment that our elders made in the development of the city from 50s and 60s.
Thank you, Dr. Prakash. Do we have? Yeah, there's one more question.
Sir, my question is, I am Dr. Satyendra from Indian Institute of Rice Research. It's not a question, rather extension of our previous question. In addition to the information on genes and the pathways before moving to editing, I think the other major impediment is having efficient regeneration and transformation protocol of several crops. Except for few crops or few popular grains, we don't have very good efficient transformation and regeneration protocol, and that is one area I think in the years to come, if we want to harness the CRISPR technology, we will have to address. Yeah,
I agree, because that's much of my initial research in my career was spent on optimizing the transformation efficiencies for the two crops that I worked with. That was on sweet potato and groundnut. And Dr. Ramanjani Gowda, who was department chair in the biotechnology there and now the esteemed board member, was a postdoctoral scientist in my labs. I recognized that and spent a lot of time not only working on those areas while he was here at Tuskegee, but also when he went back as a professor. So many of his students continue to work on that area. So you make an excellent point, and that must be continued. But one caveat though, you don't have, we recognize like in soybean, for instance, we still are cotton. There are only few genotypes that can be transformed. And what we do is we transform those genotypes and then through classical breeding transfer those traits into some of the other genotypes. And so let the impediment not hold you back, where you can focus on a few model varieties for your transformation.
So Dr. Prakash, my question is about selection of CRISPR-Cas9 and targeting any nucleotide. It is not it's blindly, whole world is looking like blindly targeting some Cas9, designing guide RNAs without knowing what is the nucleotide to be targeted. It's like most of the time, most of them are targeting for a knockout and then selecting for the trait of their interest. Do you think we need some more basic research to understand the basic functionality of the gene, where the mutations, what kind of mutations can cause and what biochemistry it can change? It's like you cannot understand, like mutation means non-functional. It can be a better, it can be a weak. So in this context, what is your view on the selection of CRISPR-Cas9 for crop improvement?
Right. I think CRISPR-Cas9 was one of the very first iterations of this technology, and as you know, the technology is developing almost on a daily basis. We are at some of the versions that have come about are far more precise, and understanding will always continue. Remember, we never knew what was the gene that controlled the dwarf architecture in wheat, what was the biochemical mechanisms behind it. And Borlaug and Swaminathan went ahead and developed it, and some of the knowledge came later. It's like aspirin, which is one of the most popular drugs, was invented 100 years ago, and we continue to use it. And even today, we are trying to understand some of its effects on the body. And so science will always go on. Science will always improve things. And so we don't have to wait for the 15th version of iPhone to come up before to start using the smartphone, you see. And so let our basic research and translational research go in parallel while the society can continue to benefit from the earlier technologies. Let's continue to improve and generate knowledge and then adjust as we go along.
Yeah, thank you, Dr. Prakash. We are now aware that there's just a few tens of genes that have been edited so far, and I'm sure there's going to be continued research efforts in the field of genomics, and also the omics field is going to be be explored more and more, and the technology will be used far and wide for editing crops for the benefit of the society. Thank you very much for your insights and also clearing a lot many doubts among the participants of this international symposium. We are extremely happy that you could make it and also be a part of the symposium. We thank you very much, Dr. Prakash.
Thank you very much for having me.
On behalf of the organizing committee and being part of this conference. So accepting the invitation and being part of this conference. So now I would like to call upon technology to hand over the memento to Dr. Mohan Rao, who accepted to chair this session. Yeah. Please, sir. Inaugural. And also you had your time for the last session also. Thank you. Yeah, so now I would like to be given it to Dr. Preeti. Yeah. Preeti Singh. Thank you. Coordinator for the poster session of crop improvement to felicitate the jury members, Dr. Preeti Singh from IHR. Yeah, and to also felicitate Dr. Ramesh for also accepting to be the jury of poster session. It's okay.
So thank you, the organizers, for giving me an opportunity to evaluate the posters. So when Dr. Veena called me and asked me if I ready to evaluate, I immediately said yes, because it's an opportunity for me to learn, right? So different scientists will in different ways. Same concepts will be thought different ways. It's really educating for me. I enjoyed evaluating the posters. So thank you once again for giving me the opportunity to evaluate the posters. Thank you.
So this brings us to the last session, almost done for the day.
We will continue.
Sorry. So there are 3 more presentations, oral presentations left out.
Okay, now we are continuing our oral presentation. I will request Ashok sir to chair the.
We can have the next speaker.
Yeah. Next
Dr.
speaker
Nagesh.
is Dr. Yes, Senior Scientist, ICR Sugarcane Breeding Institute, Coimbatore.
Okay. Good evening, everyone. Myself, Dr. Suresh from Sugarcane Breeding Institute, working as a senior scientist in the discipline of biochemistry. My topic of today's presentation is on overexpression and vacuolar targeting of invertase inhibitory proteins to improve sucrose accumulation in sugarcane. The basis of work is, if you look at sugarcane as such, sucrose is a very important trait in sugarcane breeding. So, among the commercial hybrids, if you look at the two prominent varieties of sugarcane in India, one is the subtropical variety CO2038, and in tropical variety CO86032. The average sucrose content is around 20%. So the theoretical maximum of sugarcane sucrose accumulation is around 25%. It can sugarcane cell can hold zinc cell stem parenchyma cell can hold 560 millimolar of sucrose. There is a tremendous scope to enhance sucrose yield in sugarcane. So based on this work, I chosen this topic to overexpress the specific invertase inhibitory proteins which can downregulate the invertase enzymes at post-translation level to improve sucrose yield in sugarcane. So as we all know, there are three major invertase enzymes, types of enzymes based on the location where they are functioning in the cell. So one is vacuolar soluble acid invertase, which is localized in the vacuole, and the cell wall bound invertase, which is localized in the apoplasm region, and the cytoplasmic neutral invertase. The major biochemical reaction is catalyzed by the invertase enzymes is hydrolysis of sucrose into glucose and fructose. So in sugarcane, sucrose accumulation is controlled by this group of invertase enzymes, but when at early stages of cane development, sucrose hydrolysis is required, and the action of invertases play important role in development process of a plant by providing the carbon pool for the vegetative and other plant growth development. So when the plant gets matured, the action of invertases, especially in the zinc tissue stem parenchymal cell, where the sucrose is stored in the vacuole, is getting deteriorated, or it is not stabilized. So due to the action of vacuolar acid invertase. So this work mainly concentrate on targeting these specific inhibitory proteins to the vacuole and study its effect of overexpression to stabilize or to avoid the deterioration of sucrose at maturity and post-harvest period. So earlier work on these aspects on downregulation of these enzymes through RNAi approach was not effective. So the most effective alternate approach is on post-translation regulation of these using these specific invertase inhibitory proteins. So what we did is, if you look at the first plant invertase proteins, which was cloned from potato, where they have used this as a candidate to prevent the cold-induced sweetening of tubers by suppressing the action of invertase enzyme in potato tubers. So in the monocots, the first invertase inhibitor was cloned from maize, where it was involved in it was found to be expressed during kernel development by inhibiting the activity of apoplasmic invertase enzymes. Based on this work, what we have used these genes to to identify the sequence available from the sugarcane gene. We use these genes as a candidate to identify the inhibitor gene homologs in sugarcane genome. So we genome identification has identified 18 homologs of these genes and studied the expression of these 18 homologs of sugarcane invertase inhibitor gene homologs, and there was significant variation among these 18 homologs. And based on this expression data, we classified these invertase inhibitor proteins to two groups. One is apoplasmic localized and the vacuolar localized. And we studied the function of these invertase enzymes by in vitro assay and fixed the inhibitory activity up to 22.5 nanomolar. It can inhibit 50% activity of invertase enzyme. So, and we also validated these invertase inhibitory proteins, how they are localized in the cell by fusing the GFP reporter protein and doing transient assay. We could able to validate these genes are localized. One is in apoplasmic region, another is in vacuole, sugarcane vacuole. So the system which was developed at the institute, vacuolar targeting system, by using this system, we developed the gene construct which can target different cellular organelles in the sugarcane cell, and we developed a transgenic events, overexpressed lines in sugarcane, and confirmed through PCR. And also we validated these transgenic events by mimicking the same construct, doing the transient assay and studying whether that is localized in the different cellular organelles in the sugarcane stem parenchyma cell. So based on the RT-PCR expression of these transgenic events, we could able to found up to 10% enhancement in the expression of these genes. And interestingly, these lines which have shown the improved sucrose up to 3 to 4% compared to the wild type control. So from this study, we could able to conclude that we have successfully developed high sucrose invertase inhibitor overexpressed lines, which can accumulate 3 to 4% high sucrose than wild type control. And we also demonstrated the functional role of these invertase inhibitors in sugarcane for the first time, which can be used to prevent the post-harvest, pre and post-harvest deterioration of sucrose. Thank you. Yeah.
Production, is it low or high is required?
It is depends on the which type of technology, whether it is a first generation ethanol or second generation. If you are going for a first generation ethanol production, I think higher the sucrose content is better, because the government of India has initiated, has given a policy that we can convert the sugarcane juice directly into the ethanol because of surplus sugarcane production.
Yeah, but still, why it is not initiated so far?
No, it is already initiated.
So,
direct conversion of sugarcane juice to ethanol.
No, is farmers sugarcane is taken for production of ethanol?
Factory, mainly factory, sugar factories are using that.
Yeah, for production of sugar right now they are using.
Yeah.
Are they producing bioethanol?
Yes, yes.
They are producing.
Yeah.
Okay.
Yeah. Now 20% blending has come to the place now. 20% blending to the petrol.
So instead of overexpressing the inhibitor, can we do the genome editing to the invertase?
Yeah, actually, this is because why we go for a post-translation regulation is invertases early stages of the plant development is required for the growth of the plant. So if you knock out the genes it would be more deleterious effect on the plant growth. That is one aspect. Another aspect is due to the complex genome. It is minimum 10 copies of each gene is there. So it is very difficult to tackle all the alleles. I mean, in genome editing. Yeah, that is one.
Thank you. Nice presentation. You see, this is a cold inducible event, right? That sweetening.
That is a potato. Yeah.
That's what.
Yeah.
But which you are working on sugarcane, taking a gene inhibitor from potato.
Potato, there was a study that cold-induced gene, cold-induced sweetening.
Okay. In sugarcane, it's a universal event. Irrespective of the temperature condition, there will be sweetening.
Yes.
Okay. Yeah. I wanted to tell you,
Yeah.
Why don't you use cold inducible promoter?
No.
Okay, fine.
Okay, thank you, Dr. Suresh. Thanks for the presentation. We'll have the next presenter.
Thank you, Suresh. So next presenter is Dr. Garima Paul, Regional Center for Plant Biotechnology, Haryana.
Good evening, everyone. I'm Garima Pal, PhD student from Regional Center of Biotechnology. So today I'll be talking on exogenous application of double-stranded RNAs to improve plant growth and resistance against bacterial disease. So the known available plant growth regulators, their targets are unknown, and with increase in bacterial diseases, the instantaneous crop protection is needed. So for this, we are using, we wanted to exploit the plant endogenous gene through the dsRNA approach. So in this dsRNA, it will be processed into siRNA through dicer-like protein, and it will form a RIS complex by binding to the ergonaut, and it will lead to the silencing in the local as well as the systemic tissues. And this RIS complex can bind to the DNA, leading to the epigenetic modification. But the challenges associated with the stability of dsRNA is in external environment, it can be affected by UV light, rain, or microorganism, or it can be pH and nucleases in the internal environment. So to effectively deliver the dsRNA to the plant system, we use cationic polymer, which is known to deliver the nucleic acid to the mammalian cells. And we have fluorescently labeled this polymer and infiltrated into Nicotiana benthamiana and Arabidopsis. And after 48 hours, we could see the signal in the upper leaf suggesting the systemic movement of the polymer in the plant. And the root uptake was checked in the rice leaves. And further, the stability of the complex, that is dsRNA with the polymer, was checked based on the size, that is hydrodynamic diameter and zeta potential. And here we can see up to 25 days, there is not much variation in the size, suggesting the formed complex is stable. And this polymer could be used to deliver the dsRNA in the plants. So to initially check the effectiveness of this dsRNA approach, we generated the GFP transgenic line and infiltrated the dsRNA against the GFP. And here we can see in the dsRNA infiltrated plant, after 1 hour, there are no signals for the GFP. And after 24 hours, the signal starts reappearing. But when we have given the dsRNA along with the polymer, the effect was prolonged. Like up to 48 hours, we could see a weak signal. And further, we check the mRNA expression level and the protein level in the same leaf. And here also, similarly, we can see the level of the GFP transcript as well as the protein has been reduced. Here, what we found out, that even in the distal leaf, we could see the reduction in the GFP protein level. So further, since it was functioning, we wanted to target the plant endogenous gene, that is FT, which is responsible for the transition to the flowering. And here we have done the foliar spray of the dsRNA against FT. And after 7 days of post spray, we can see a reduction in the bolting length in the sprayed plants. And as there is a delayed transition to the reproductive phase, we could see more number of the leaves in the sprayed plants. And further, we checked for the transcript level of the FT. We found out that in case of flower, after 7 days of post spray, there was a reduction in the FT transcript level. So after that, we wanted to check this system in case. So we targeted PDS gene, that is phytoin desaturase, and it's been very well known. If we target this gene, it will lead to the stunted growth and the white phenotype. So based on that, like after 10 days of treatment, this was given through the root uptake, and after 10 days of the treatment, we could see in the dsRNA treated plants, the growth has been reduced. And when the dsRNA with the polymer was given, the yellow phenotype as well as the stunted growth was visible. And after 45 days of the treatment, we see that dsRNA treated plants, they could recover back to the normal phenotype. Whereas when the dsRNA was given along with the polymer, we could still see some yellow phenotype compared to the control plant. And further, we checked for the gene expression level of the FT. But here we could not found, even though the phenotype was visible, we could not find out the reduction in the PDS transcript level. So we synthesize maybe this inhibition is happening due to the translation at the translation level. So we checked the in vitro translation efficiency with the polymer plus dsRNA, and here we could find out that the translation efficiency has been reduced when the dsRNA was along with the polymer. So further to target the, we wanted to target the negative regulator of the defense system. So this SDR1 gene, it is known that when this will be mutated in the plants, that will lead to the resistance in the plant against the Pseudomonas.
Mic test. Mic test.
Growth. And the studies have shown that if we target this sweet 14 gene, it will lead to the resistance in the plant. Based on that, we took the infected rice plants and sprayed the dsRNA, and we could see the reduction in the disease symptom, bacterial growth, as well as the lesion length. S. Vemanna, our collaborator, Professor Avinash Bajaj, who has given us the polymer, and the Laboratory of Plant Functional Genomics, RCB, and UGC for my fellowship. Thank you.
Otherwise, you will not be learning. Yeah, a nice presentation. My question is, what is its persistence, or how long it will be there in the environment when we spray? How long it will be stable?
Sir, like in
That
case
polymer encapsulated composition.
Yeah, that will prolong the effectiveness. That's why like we are using a polymer.
No,
like
for application in agriculture, it's very paramount important. Study that when you spray, how long it will be in a condition sufficient enough to deliver DNA, double-strand RNA. That is very much important.
Okay.
Stability in open environmental system, not in a controlled condition. Just spray it at different point in time.
Okay.
And after spray, considering that as 0 point, at different interval, you just confirm whether it is able to deliver double-stranded DNA or not.
Okay. So, sir, if you ask for the stability in the temperature and pH, that we have checked in the in vitro condition.
No, they are all single component based stability. In nature, pH alone will not function. Temperature will not function. Ambience. In that condition, you can study.
Okay.
So you cannot do this because in open environments, you cannot use a recombinant molecule. Biosafety will come into picture. The thing is, you can take plants, rice outside with the presence of illoplane microbacteria or microorganisms. That can be studied inside a contained environment only. You have to study. You cannot take up such experiments involving any recombinant molecule outside the container. It is not recombinant.
Is it recombinant molecule?
This will not.
No. DNA, RNA, they are all biological molecules. They are present everywhere. RNases are there. RNA is there. If you sneeze, so many RNA will come out there.
Okay, we can further this discussion later. Thank you, Ms. Garima, for your presentation. Please do keep in mind that when experimenting with rice like a crop system, okay, we need to test, but other precautions need to be taken care of. Okay, we'll have the next presenter.
Thank you, Garima. Next presentation is Dr. Nandish P, Senior Scientist, IHR Bangalore.
Respected jury, Dr. Mohan Rao and T.H. Ashok sir, my dear friends and scientist, agriculture biotechnology in the division of basic science at ICR Indian Institute of Horticulture Research, Bangalore. So before starting my presentation, I would like to express my deep condolence to Dr. Tirth Prasad, who was my MSc mentor. I was the third batch MSc student here. And in addition to Dr. Anita Peters' presentation in the morning with regard to the contribution of various teachers, I again add here Dr. Chandrayapa's contribution, because he was the one who taught us basics of molecular biology. So with this, I would like to start my presentation. It is on hybrid embryo rescue in some of the horticulture crops. Few of the crops we have tried it. Next slide, please. So as you all know, breeders are always hunting for the novel genes so that crops can be improved for various biotic and abiotic stresses. In that process, since most of the cultivated crops are already saturated, he always looks for the gene in the related or the wild germplasm. So during that process, making a compatible cross and getting a fertile hybrid is will be a difficult task, because there will be some physiological and biochemical processes which inhibit the embryo, proper development of the embryo, and getting a successful hybrid out of it. So several, in parallel to the breeding technologies, several in vitro technologies have been developed using the tissue culture techniques. One such technology is an embryo rescue technique. This was way back in 1925 itself. It was demonstrated by Lebach using the crosses between Linum perenne and Linum ostricum, and he successfully recovered the hybrid embryos. So this embryo rescue holds a great promising effect in the crosses involving wire parents and generation of applied plants, and shortening the breeding cycle, and also overcoming the seed dormancy. So these techniques were laid out using these objectives of like aseptic isolation of the hybrid embryos from incompatible crosses, and then in vitro regeneration of the rescued embryos, and hardening and recovery of the fertile hybrids. Next, please. So It's a edible papaya species. So IIHR is involved in the papaya crop improvement. So we have developed a variety called Arka Prabhat, which is very good in all other aspects. It is a gynodiasis species, and then it is TSS levels are very good. It is very well accepted by susceptible for an virus called as PRSV, P strain of the virus, which causes the ring spot disease and which makes the fruits unedible. But when we look for the wild species, there is another species called as Vasconcella cauliflora, which is not edible papaya, but it has a gene responsible for resistance to PRSV. In this process, our breeders are continuously trying to progress this PRSV P resistant gene into the Arca. Are always suffered by getting the fertile hybrids. In this direction, we have made the crosses. We have taken the pollen of Vasconcella cauliflora and tested into Arca Prabhat. So after certain days wherein the embryo abortion may take place at the 90, 120 and 150 days after pollination, the immature embryos were harvested and they were cultured aseptically on different media with the different hormonal combinations, and the developing embryos were further transferred to an APMS, and then after rooting, they were subjected for hardening process, and then they were established in the greenhouse. Next, please. So this is the process which involves the surface sterilization, then inoculation them onto different media, then the regeneration, that is germination into a whole plant, their hardening process. So next, please. So further, these hybrids were confirmed using the SSR markers for the confirmation of hybridity with the polymorphic markers between the parents, and then that way they were handed over to the breeder for further evaluation. Next, please. So another crop which we are working is seedless crosses in grapes. So when we are using seedless as a female parent, then again the breeders will suffer because the resultant progenies will be also be seedless. Under such cases also embryo rescue will have a greater role to play. So here we are using one of the parent, the donor parent called as Bayanga, which is having resistance for the powdery mildew and downy mildew diseases. So when we are making crosses between these two, again the seeds are not properly developed. Under such case also we have taken the berries, and then after 40, 45 and 50 days after harvesting, and these berries were, after removing the surface sterilization and removing the seed coat, they were inoculated into different medium. Among them, woody plant medium was giving us very good result. And then those which have developed on this woody plant medium were further transferred to APMS for rooting, and then rooted plants were next further hardened and then transferred to the field for further evaluation. So this is another crop we have successfully done the embryo rescue. So next, please. So in this case, tomato, we don't have much problem as far as hybridization is concerned. But Dr. Prasanna, while working with some of what we can say sterile germplasm, introgressing some sterility genes, so he had held up with some of the plants dying in the field. So fruits were developed, but they were not subjected to maturity. So there also we have tried, since most of the Solanum species, as you all know, a routine tissue culture worker will know. So they highly respond for the tissue culture protocols. Simply putting them onto off-MS have developed and germinated, and these germinated seedlings were further hardened, and then further they were given back to the breeders. So this is how in these three crops we have successfully in vitro cultured the immature embryos and developed them into a whole plant, and then the hardened plants were further subjected for evaluation. Next, please. So this is all about the work we are carrying out, a part of our work. So as you all know, the tissue culture requires a lot of hard working, and we need the constant support of students for working on the laminar. So contamination major problem. These are all the students. They are from US GKVK and ASEN campus, and also few of the students from the traditional universities. So these guys have contributed in successful culture of these plants. And I thank you all for your patience hearing.
Thank you, Dr. Nandish, for your presentation on hybrid embryo rescue. Questions from the audience? So finally, Kumar Swamy decided not to ask any question, is it?
He was my classmate and roommate in masters. Yeah, please. Alkodappa. Yeah, embryo culture can be done. So it is a rare case where there are difficulty of getting the fertile hybrids in the normal process. We are intervening. Also, woody plants, especially like grapes, they don't respond with your MS alone. So woody plant media will help. Like different media for different.
So your hybrid rescue method compared to your CRISPR technologies, how do you foresee your technology will be helpful for improving the crop enhancement? And the second question will be like, how fast it will take to fix a trait of interest for genetic enhancement of a trait?
Of course, as far as breeding is concerned, the traditional wide hybridization breeding always lacks because of this linkage drag. So along with the trait of your interest, there will be negative characters coming out, and fixing them will take a lot of time, especially in horticulture crops which are highly heterozygous. It is very difficult to get a homozygous line. That is one problem with wide hybridization. So we have to work with the time only. As far as the other genome editing tool is considered, of course, as on today, it is light of the day, and it has most promising technology, and it will be more precise technology. So amino acid at individual amino acid level you are working, so it will be more precise breeding technique rather than the wide hybridization. That is what I would like.
So can you use that CRISPR line, which is edited one, to develop in a similar hybrid rescue method to fix a trait of interest to develop a pure line?
We have also initiated few work on the CRISPR-Cas9 mediated genome editing also. It is still in preliminary stage.
Yeah, that will make a wonderful progress actually, because that is missing in CRISPR technologies, because CRISPR alone will not be helpful for genetic enhancement.
Yes.
It is not out of.
Teacher, genetics teacher. Yeah. Yes, sir.
Thank you, Dr. Nandish. To one of the questions that you asked. Now, gene editing has its own advantages. Interspecific hybridization and hybrid rescue has its own merits in certain crops. Gene editing cannot be used everywhere. Okay, genes are very well characterized, and in certain crops, we have to follow invariably hybridization and hybrid rescue
In
whenever
addition
required.
to that, the in vitro regeneration and transformation. So that is what one of the audience has asked that question. So we have not worked out the basics. So parallelly, we have to work out the basics. So unless and otherwise we have a reproducible regeneration and transformation protocol, whatever the technology you have, it will not find the light of the day. So that has to be done. That basic work has to be institution like us or universities have to do this work. Even though it is painful, we may not be getting high impact factor papers in those works, but still we have to work out those papers.
Yeah, thank you, Dr. Nandish.
Thank you, sir.
We'll have the next presenter.
Thank you, Dr. Nandish. So next speaker is Dr. Parmesh D, Rice Pathologist Laboratory, US, Raichur.
Very hard time to present now. I think everyone is tired since morning. I'll try to justify the time given and opportunity. Respected jury members and distinguished scientists from the different parts of the world who joined offline, and as well as the scientists joined online. I'm Dr. Pramesh, working as a plant pathologist at Rice Pathology Laboratory, Gangavati. So now I would like to present the our work, what we have done in for the past 5 years, the emerging diseases of rice, that is false mud. Next slide, please. Rice is one of the important crop. I don't go to the too much of introduction. It is infected with many biotic stresses. Among them, one of the minor disease is becoming major in nowadays in almost all the rice blooming ecosystem of the country is false mud. Though it was considered as a minor disease, now the epidemics of the disease has been reported in different parts. In addition to causing the yield loss, this disease is also producing some of the toxins in the grains. Some of the toxins have been reported to be harmful to the human beings as well as animals. As I told, the disease has been first reported in India. Most of the studies were targeted to the cultural and other studies, and many of the things with respect to disease has been not done. That include distribution of the disease in different ecosystem, because in India, rice being grown in different ecosystem, including coastal ecosystem, rainfed ecosystem, as well as hilly ecosystem, and different ecosystem, the condition will be different. And the extent of the disease distribution, whether this disease present in all the ecosystem is not known. Such studies has not focused in ecosystem level, as well as with respect to population structure. The population structure is unknown, whether any variation in the population level at the field is not known, as well as sexuality of the pathogen, because these are all belong to the Ascomycetes fungi. They reproduce sexually, and sexual reproduction is one of the factor that will give rise to the emergence of the races and others virulence. So those things are lacking. With this objective, we have taken some of the work to address those gaps in India by extensively studying the different ecosystems of the southern India, including Karnataka, Tamil Nadu, and Telangana state and Andhra Pradesh, for the distribution of the disease in different ecosystems, and also collected the different eco-distinct isolates of the pathogens to study the population structure, and also to study the genetic diversity, and also mating type. Local distribution means this is a Ascomycetes fungus. This is a heterothallic fungi. This requires 2 different types of mating type to reproduce it naturally. Therefore, the extent of distribution of different mating types in a particular field or location is very essential to to understand the potentiality of the this fungus to become more virulent. And virulence profiling is also done. Because for this pathosystem, no differentials are available. Therefore, we used our local differentials using the 4 varieties with different degree of resistance, but to profile the virulence. Among the after virulence profiling, we selected the 3 different types of isolates having different degree of virulence for pathogenomics, to sequence them completely, to study the difference between them as they're showing the phenotypically difference in virulence, to study any genotypic difference between them to cause the difference in virulence. Next slide, please. This is some of the glimpses of the survey we conducted in different parts of the country, and these are the symptoms we observed. Next slide, please. These are the different ecosystem in the different states, and covering the both irrigated as well as upland, coastal, and hilly ecosystem. And we studied we have taken the sample from more than 120 locations, and we mapped the hotspots. Different statistical analysis has been done, and potential risk areas has also been identified. And next slide, please. Next slide. Next slide. So this study is identified that many of the irrigated ecosystem present in Tamil Nadu, in Karnataka, especially in Karnataka, the Tungabhadra ecosystem, as well as the Kaveri ecosystem, and in Tamil Nadu, Bhavani Sagar ecosystem, as well as Kaveri ecosystems are highly risk areas prone to this disease occurrence every year. And also, this pathogen is, although reported previously, a very slow growing pathogen, very shy on the media, very difficult to isolate. It requires minimum 30 to 40 days to get the minimum size of the culture on the media. To address this, we conducted some of the basic studies to identify the different spore type and different medias for isolation as well as for multiplication. We could standardize that yellow colored spores on the potato sucrose agar is very good for quick isolation, and as well as yellow colored spores in a potato dextrose cloth is very good for multiplication quickly. Next, these are some of the studies we conducted. Next slide, go fast. This is the different diversity at the morphological level of the pathogen. These are some of the pictures showing the diversity of the pathogen. These are all the isolates collected from the eco-distinct locations, ecologically as well as geographically distinct location. Next slide, please. Next slide. So, and also here, one of the infecting agent is conidiaspores. Conidiaspores are responsible for secondary spread of the disease, and we should also study the chlamydospore as well as conidiaspore variability present in the different isolates. Next slide. Here, to study the variation at the genetic level, we just studied the one of the marker was used is ITS, that is universal marker was used, and that was all the 61 geodistinct isolates were sequenced and phylogenetically were studied. And one of the interestingly, most of the with respect to ITS, most of the populations are homogeneous. We could able to identify more than 90% of the strains collected from different locations are similar. Only few isolates are diverse out of the main cluster. And also, as I told, in the field, so that that will contribute to the generation of different races. We could we identified the mating type loci present different isolates. We selected the two idiomorph MAT1, MAT2, and we identified that more than 60% of the strains were heterothallic for MAT11 loci. Another 40% of the strains are heterothallic for MAT12 loci. Means none of the strains are homothallic. These strains, this pathogen required opposite mating type. Means sexual reproduction is occurring in the field. That will be a threat that in future the emergence of more races will be a possible event. Next. And you studied 61 isolate. Among them, we selected all the 61 isolates for virulence profiling, because no data available any part of the world with respect to the virulence of this pathogen. As I told, morphological also diversity is there, and with respect to ITS, most of them are similar. But with respect to virulence, any difference is there to check that we do not have any differential system in this pathosystem. But we use the 4 different varieties like BPT-5204, IR64, IR28, and J. These are local differentials we used to study the variation in their level. And next slide, please. This is the next slide. This one, please keep it here. On most of the strains, more than 40 strains out of 61 are showing less virulent, whereas 7 isolates we found that they are highly virulent. They are infecting even IR28, Jaya, IR61, BPT-5204. IR28 is considered as a tolerant to resistant type of genotype that is being used in the different part of the world to study the virulence profile now. And among these different phenotypic strains, we selected 3 strains for whole genome sequencing: EVGVT, EV3, and EV8. And we sequenced using Illumina, and assembly has been done using Denoma. Denoma assembly has been done. This is the genome statistics of one of the strain I'm explaining here. That is EVG80. The approximate size was 27 MB, and it contained next slide. Go to next slide. Previous slide, please. Come back. Around 6,627 mapped. Most interestingly, we could able to identify 422 genes which are essential, which are involved in host pathogen interaction. Means they will be involved in causing the they're involved in infection process. And also, we could not able to map or identify the carbohydrates dehydrogenase enzyme like cellulases, amylases, and pectinases. This is one of the reason that this pathogen is unable to infect any other plant organ. It only infect the floral organs, because floral organs like stamen and stigma contain less cellulose or hemicellulose, because this pathogen do not have any enzyme inventory to degrade those. Therefore, it will specifically confine to the only floral organs. Next slide. Next slide. Next slide. Go fast. Go fast. Some of the, and also we could also identify the some of the transposable element and also diversity within the genomic level to study the phylogenetic analysis, because this is a false smut pathogen, belongs to the Ascomycetes fungi. We do also have the true smut fungi that belong to the Basidiomycetes. When these Ascomycetes smut causing pathogen was evolved out of those true smut fungi, we have taken the sequence to genome of all the smut fungi as well as along with some of the Ascomycetes. We could identify that these Ascomycetes are false smut fungi as emerged diverged out of the true smut fungi around 780 million years ago. This was we used some of the advanced biometric tools to deduce that that evolution. In this work, I conclude that a spatial distribution has been done, molecular diversity, virulence diversity has been done, and sexuality of the pathogen has been identified. And also, this is the complete genome sequence of the one of the virulence has been done. I would say that this is the first sequence coming from our country, and comparative genomics has been studied. phylogenetic analysis as well as clustering pattern and approximate divergence date also been identified. Next slide. This is the part of the project work funded by the DST-SCRB. I'm thankful to my collaborator, Dr. Prasanna, US Bangalore, and also Dr. Manjunath from NBIR. Thank you, Anandal. Thank you.
Thank you, Dr. Pramesh. It was a lengthy presentation.
It will not drag. Your answer also should be in one sentence.
I would try, sir.
See,
My level best.
you attributed so many sequence, no variations as variants. How do you rule out bioinformatic and sequencing errors?
Possibly that could be one of the good questions, sir. But I'm not a bioinformatician by profession. I'm a plant pathologist. I look after the phenotypic work. You are right that some error would be there, but not saying that 100% error lead to the different in SNPs, because we use the advanced tools for analysis. I don't know whether that going to be the cause for error. That could be a sequencing error. I don't know, but that may not be going to cause the 100% variation for SNPs. Yes, sir. Yes, sir. With respect to disease reaction, most of the having virulent, less virulent. Sir, virulence is not caused by whole genome. The error may be because of the few genes, as I told, around 420 genes are involved in causing infection. Those genes, these variation may not be there. There may be variation, maybe in the some repeated elements and in other maybe other reasons. Okay. Okay, sir, we'll consider. But this is a part of our work, sir. Still, bioinformatic information, analysis of other two strains is going on, along with some trans work. So I think those things will be addressed in our future study. Thank you.
I think this is the last speaker, Dr. One more. Okay. Thank you, Pramesh.
Thank you, sir.
We'll
Thank
have
you for the
last
opportunity.
speaker. Dr.
So we have a last online presentation. Dr. Neha Kumari, College of Agriculture, Palampur, online presentation.
Yes, sir.
Neha Kumari, please share the screen.
Yes, sir. Sir, is this visible for you?
The slides are not visible. Could you kindly share them?
Okay, sir.
Hello, please share the screen.
Yes, sir. It will take time. Sir, it will visible to you.
No, slides are visible, so you can present.
Good evening to all of you, all the dignitaries and the participants. Today I am here to present or presentation on the of the haploids in broccoli by efficient embryogenesis system. First of all, introduction. As we know, as the broccoli is important vegetables grown throughout the world, the development of double haploids through anther culture is the most successful technique for the broccoli improvement by providing the instant homogeneity. It leads to fixation of the desirable character of recombinants as well as the reduction in the number of generations required to achieve the success. In methodology, we have used the planting material. These studies were conducted in the Department of Vegetable Science and Floriculture.
Ms. Neha. Okay. Will you be able to continue? Ms. Neha. Ms. Neha, we are not able to hear you.
Sir, it is audible to all of you.
Can you
Hello.
please continue?
Okay, sir. All the phases of anther culture, including the growth of the donor plants, anther staging, and the bud selection, bud surface sterilization, will be carried out. For intro, callus inductions, these anthers were excised and incubated under the dark condition for the 2 weeks on Gambok B5 medium with different concentration of oxygen and cytokinase was done. For in vitro shoot regeneration, multiply callus culture on B5 medium with different concentration of oxygen and cytokinin to induce adventitious shoot regenerations. For chromosome doubling, Cortisone at 0.05% for 6 hours were applied to generate haploid plants in vitro. These double haploids were rooted on half-strength media containing the 0.1 mg per liter of IBA. Well-rooted were successfully hardened, which were further used for the confirmation of the ploidy assessments. These are the results. Figure 1 showing the florets of broccoli, which were used as a source of explant. In the next figure shows the flower bud of different sizes which were collected, and the best size of 3 to 4 mm of the flower bud was used as which formed to be suitable for the callus induction and differentiation. In figure 3, we show the highest percentage of crossover viability and the pollen development at late to early biolate stages, which are found to be the most suitable for efficient embryogenesis.
No questions.
Neha, are you done with your presentation? Thank you for your presentation. Okay, okay. If we have no questions, and we'll call it a day. And
Sir, now Shamlama Madam, organizing secretary.
I should make a mention here. I should make a mention here. The organizers team who have selected blend right from traditional plant pathology, ending up with molecular plant pathology to gene editing. We had a number of or a spectrum of topics, including probably 100 years old to the latest gene editing. Thank you, and thanks to the organizers for giving the opportunity to be here and judge the presentations. I hand this mic to Dr. for his remarks.
I don't have much to say. It's already time, and I would like to thank the organizers for arranging this excellent presentations. And the presentations were quite diverse, and in preparing for the presentation, and the slides that are prepared were also very good. Their presentations are also highly appreciable. Many have done put in a lot of efforts in the preparation of this, and particularly mention the active participation of the audience also, led by Dr. Komi. So
Now I request Dr. Madam, organizing secretary, to hand over the momentous to juries. Madam. Monroe, sir. Please. So Ashok, sir. Thank you, sir. Please arrange that budget. All of you join for dinner.